A lot of e-posters on YouTube for this conference.
Yes.
Oh, good. So people really stepped up and made sure that they
Yeah,
uploaded everything.
there's a good half a dozen of them on here.
Yeah, Laura did a good job.
E-posters on YouTube for this conference.
Yes. Okay.
Oh, good. So people really stepped up and made sure that they uploaded everything.
There's a good half a dozen of them on here.
Yeah, Laura did a good job.
So, Nathaniel, if I wanted to connect to this stream, what do I have to search for on YouTube?
Good. So people really stepped up and made sure that they
Hold on.
uploaded everything.
There's a good half a dozen of them on here.
Yeah, Laura did a good job. Okay. Sorry, there's some feedback there, both audio and visual feedback. Okay, so to get onto the YouTube stream, you should be able to, let me get my chat window up here. There's a chat. Send this out to all panelists. You should be able to connect to the YouTube live stream there.
Except I have it on it. It's on a different computer, so that's not going to be too convenient.
Okay, I'll send it out to the, I'm going to send out the link to everybody shortly. Let's get this configured first.
Okay.
Okay, so if I go to edit video, no, it's not made for kids.
Nathaniel, we
Yeah.
should also try to capture how many people are on the YouTube for the NSF report.
There are analytics that happen on YouTube, so that's okay.
Okay, thank you.
You're welcome. Now, what I need to do is I need to get the chat. I was working on this last night. It's a little tricky to find. And then I found it, manage moderators. Live streaming.
Hey, Nathaniel, morning.
Good morning, how are you, Gareth?
Good
Awesome.
morning, Gareth.
We're into 3 timeouts already this morning with Bennett, so
Oh my gracious. Oh.
we just introduced him yesterday, so
Ooh.
you'll figure it out.
Ooh.
When
You're brave.
Could I get a moment to try and share my screen just to make sure my audio's good? I'm going to be sharing a bit of a WAV file, a WAV file.
Okay, yes, that's fine.
I can do it now?
Yes,
Yeah, I see you. Yeah.
I think, and Diego's trying to call me now too, so.
Okay, I'll go ahead and see.
Give me a
I have all
minute.
The audio stuff. Oh, man. All right. Keynote, is this the one I want? Guess so. Okay.
Good morning, everyone.
Good morning.
Morning.
If you hear me coughing, I'm not sick. I inhaled a grape nut.
Ooh.
But you're outside. That's nice.
I am. It's beautiful out here.
By the way, I do want to remind everyone that right now we are on YouTube Live. I don't have the link shared yet, but this is
Okay, so if someone went to the
Just-
link, they'd see it. Okay.
Yeah, so just be aware that this is going on, so you don't know. I'm trying to figure out certain things, which I thought I figured out last night, but apparently I didn't.
Sure. Nathaniel, do you mind if I spend about 10 minutes dealing with a couple of other things and I'll be back by 9:15?
Go right ahead.
Okay. I'm going to stop my video momentarily.
Okay.
Everybody see this, I suppose?
Yes, looks good.
Okay, let me just go to the one with the audio clip. 1 second. You hear that all right?
Sounds great.
Good. Act like you've never seen that before. Later on.
Okay.
Or heard it, at least.
I forgot it already.
Yeah. Thanks.
Okay, I have the live stream enabled with there are no, the live chat is disabled, but the live stream on YouTube is running.
Fantastic. Do you guys mind if I screen share really quickly to get that software download?
To get what software download?
My the audio package
Oh,
for.
go right ahead.
Thank you. All right, perfect. Thanks. Can you see my screen?
So far, just a black screen with your name.
Perfect.
And tweeting in the background,
And tweeting, yes.
but from somebody.
It's a live Twitter.
Yeah, there you go. Okay. Live Twitter.
Once you get this going, Nathaniel, shouldn't I be able to search for it?
I don't know.
For the live stream.
Yes.
That's what I'm searching.
Yeah.
All right. Did you guys see my screen?
Yes, I did see it. It went by there.
I did see it also.
Okay, everybody. I think the live stream is working. I'm gonna put the link in the chat again, and I would like some people to test the YouTube live stream. And you should not be able to comment, and you should not be able to comment, and you should not be able to do any chatting on the YouTube live stream.
Yep, it looks like it's working here.
I see
on
it,
the,
Daniel.
on the same computer as Zoom is, which is pretty amazing.
All right. So good. So we have great, and Rachel says it's working. That's really good.
It's whole day. It's conference.
I'm going to post that. And no one can comment or do anything like that, right?
No, can't comment.
Good. Okay, so I'm going to go to HamSCI.org, and we're going to go to edit. So let's see.
I'm not going to leave that running at the same time as everything else because I'm afraid that's kind of like tempting fate with regard to system capacities and stuff. So
especially if you're speaking on the Zoom chat, it'll provide a feedback loop. So yeah, you don't want to do that.
Depending on your internet connection, you could also start getting packet loss. So I don't know that I would try and watch that YouTube video at the same time as the rest of the conference.
It's not, mommy. It's not bothering me.
मैले भन्नु मेरो भनाइ के हो भन्दा तिमी दुईजनामा आँखा राख्नु
हुन्छ अनि try.
झगडा गरेर आउँछ कहिले के गरेर आउँछ उडेर आउँछ खाना खाने ब्रेक लिन्छ हो त्यसमा पनि खाना पाइदिनु फेरि मैले भनिरहेको छु दे तिमी अहिले सुन्दैनौ फेरि मेसेज
त्यो मेसेज पठाउनुमा के छ
मेसेज पठाउन समस्या छ नि म त्यो काम गर्दै ती एउटै
त्यो WhatsApp
I'm gonna mute everybody. Okay, there we go. So you can unmute yourself if you need to participate. And people who are moderators, if you find that someone is loud and I haven't muted everybody, you can go ahead and try and solve sound issues. You can also watch YouTube live and register. I'll just leave it like that.
Nathaniel, may I try the screen share one more time to make sure that it works?
Go right ahead. Okay, there is now, so I haven't made the YouTube live link prominent, but it is easily accessible on the workshop program page and under participation. Great. So that way I'm still encouraging more people to sign in as attendees, but people who need the YouTube live broadcast, it's there.
Thank you. I'm going to try streaming one of the, just a couple seconds of one of the posters to make sure that that's working. Can you guys let me know if you hear the sound okay?
Hi, my name is Jonathan Rizzo.
Yep, heard that fine.
Perfect. Thank
Sounds
you so much.
good.
Put it fine.
Okay. That looks good. So let me send an email out to, I'm gonna send a couple emails out and then we're gonna open up the everything for the general public. Let's see. Okay. We're going to say, workshop. Okay, everyone, are we about ready to open this up to all participants? So I have, let's see here. Gareth, would you do me a favor and give Diego a call?
Okay.
Yeah, he tried calling me. I just can't do that right now.
Okay, I'll chat to him. Yeah.
Okay, that sounds great. And then, so our opening moderators are going to be Diego once he gets on, but Bill, you're already here, right? Bill Lyles?
Yeah, I'm here. I was just muted.
Okay, are you ready to start your Zoom moderating duties?
Yes.
All right.
Nathaniel, can you hear me?
Yes. Hey, Diego, how are you?
Hey, very good, thank you.
Good,
Yeah,
welcome.
I was here, sorry.
Oh, okay, great. I'm glad you're here. So you are also on Zoom moderating duty. Your job is to watch the chat window from the attendees, and yeah, and Bill Lyles is working with you. Okay, and I'm going to get.
You can't see me, but I can see you.
Alrighty. I want to slideshow, use presenter. Okay. Everyone can see that? Yep. So we got one thing. Okay, everyone. Are you ready for me to open it for attendees? Here we go. Good luck, everyone. Thank you. Okay, we are live. Welcome, everyone, to the HamSCI workshop. We are so glad you could be here. So everyone, you can feel free to chat among yourselves for a few minutes as we wait for people to come in. People who are joining as attendees, feel free to use the chat window to talk with the panelists and the moderators, and we'll have people watching the chat window there. My name is Nathaniel Frizzell. My call sign is Whiskey 2 November Alpha Foxtrot, and I am a professor at the University of Scranton. We have a number of panelists on the line here and a number of attendees. We're up to 30 panelists and 40 attendees so far. So welcome everybody. We'll be starting at 9:30. So yeah, just feel free, panelists, you can chat among yourselves. I will be right back. And we will start the meeting officially at 9:30 or Eastern time, 13:30 Zulu.
I started looking into whether I had a camera so that I could participate and be a talking head. But the only camera I could find is Windows XP dependent. It won't run on anything newer than Windows XP. So I actually just chunked it in the trash. So no camera, except on my little old laptop, which is not really capable of doing, providing this kind of feed. So no camera on this end, but my screen sharing works, so I can do the presentation fine.
Yeah, the laptop on my Dell here is an up the nose webcam. It's way down by the keyboard. It's not very good. So I have a on the top of the screen webcam now. But it's much newer than yours, Bill.
Trying to figure out when did I actually buy that webcam. I'm thinking somewhere around the year 1998, something like that, maybe. So I like to get my use out of equipment.
Does it have vacuum tubes?
Well, I didn't open it up and look at it, but
maybe if you added a few vacuum tubes, it'd run under Windows 7.
Possible.
Maybe.
This is Phil. While I have a moment, I wanted to thank Jason, who I see is back in his chair now, for doing all the hard work of receiving the live streams and kind of manipulating this after the fact into something that looks good. If you haven't seen Jason's work, make sure you check it out. He does a really excellent job, and I know has a lot of followers out there. So thanks again, Jason, for being willing and able to do this. We're very grateful.
Certainly, yeah. This is going to be fun. I'm looking forward to seeing how it's going to work out on a session like this.
Me too. We got a reasonable number of eyeballs, maybe not as many as some YouTube, guys who have more simultaneous eyeballs, but the number of interactive people in here is reasonably large. So it's going to be an interesting data point, for sure. But yeah, thanks for being available to do that. It's very much appreciated. So that, for example, I don't have to worry about that because you wouldn't want that.
Right. No worries.
I see, John, you're here. I sent you an email earlier today with some clock information on it. So hopefully you get it sometime after the session. And you're muted.
There we go. Finally uncovered the right part of the window. I'm one display short of what you really need to do this. But yeah, I did get your email, Scotty.
Okay. By the way, Alt-A mutes and unmutes for the keyboard shortcut. So anybody who can't find the button, just do Alt-A and it'll toggle it.
Yeah, I'm currently trying to figure out the magic to get my presentation up on the monitor that I want it to be on, and it's taking some experimentation. So I'm going to go back on mute so that you don't learn new words.
Okay. And Phil, for those using Mac, what was the key for mute and unmute? It's like Command M or something?
Yes, for those of you using the Macintosh client, mute audio is Shift Command A. So kind of hold your Shift key down, and then that wonderful looking command thing. And then I believe the same command would then unmute. So that's a toggle, just like Scotty was talking about for Windows.
It works.
Oh, hello, David.
Hi. Those of us on Macs.
That's right.
And for video, it's Shift Command V. For once, it's logical.
On Linux, it's alternate A.
Yes, the lovely thing is that Zoom works on all three platforms, unlike things like WebEx. Not to disparage WebEx, but it does not have a Linux client, really.
Well, I certainly appreciate this choice.
Although, Phil, I discovered that the Linux client doesn't really work with the virtual backgrounds unless you've got a green screen. So I had to turn that off because otherwise it looked like I was a Borg with USFS6, on the left side of my head.
Yeah, well, John, Steve Hamilton, who was testing this out last night, for whatever reason, half of his face was missing. I mean, literally, you could only see from above his eyebrows to his chin. It was really disconcerting. So that floating background thing is.
Yeah, let me turn it on, and you can see how bizarre it is, and it's because apparently they don't have the processing power to get
Oh yeah,
the green
I see what you're talking about. Yeah.
Yeah. So if I had a green screen behind me, it would work, but without it, it
John,
can't deal with the background.
It also helps, John, if you have more light.
Probably, which my
agreed.
office isn't well set up for. So
Yeah,
we're
that's
going
what
to
I was
turn this
say.
off.
If you have better lighting, front lighting facing your face,
yeah,
it does work a lot better that way.
I believe it.
The color choice is important too. Scotty's actually works quite well compared to some of the others, but with red hair against an orange background.
Look for the stem through the head.
Yeah, well, the tree growing out of your head is interesting. But.
Sure. Okay, folks, just a reminder that we're about 1 minute away from the nominal start, so I'm sure Nathaniel will be back momentarily. So
I'm here.
Ah, there you are.
Hi, welcome everyone. Audio issue. There, how's that? How does it sound?
Sounds
Great.
good.
Wonderful. Well, it is, my watch says 9:29, so we still have maybe about 30 seconds before we actually get started. But I'd like to start by just welcoming everybody who's here. I'm very excited that we're having this HamSCI workshop still, even in the midst of all of the challenges that we are facing right now. Our participation is excellent right now. We have 43 panelists and 95 attendees signed in right now, and I just think that's absolutely wonderful. Thank you everyone for joining in. I'll be talking a little bit more about how you can interact as an attendee. For the moment, what you can know is that you will be able to chat using a text chat window to the moderators, who will be able to read your chats, ask questions, interact with you, and it can even enable talking for some people as well.
Nathaniel, you might move your mic a little closer to your mouth because we're getting a lot of room echo.
How's that?
Yeah, a little better.
A little better. I'm going to mute everybody now. All right, how's that? That should be good. Okay, I'm going to try to keep everybody muted. So if you are not talking, please mute yourself. Otherwise, you can just just unmute yourself when you want to talk, and then remute yourself when you're not talking, and that will help a lot with the audio. Okay, good morning everyone, and welcome to the 2020 HamSCI workshop, the Auroral Connection. So this workshop is today and tomorrow, Friday, March 20th through Saturday, March 21st, 2020. And it was originally supposed to be held in person at the University of Scranton, which is where I'm a professor. This is the Loyola Science Center at the University of Scranton. So hopefully we will be able to meet here next year. We will work on that. But for now, I'm very grateful that all of you have put in the effort to make this transition to an online workshop and meeting. And I'm very excited about our program for the next couple days. Now I'm going to start with some slides that might be a little bit funny to some people, but might make some sense to a lot of other people. And that is, what is ham radio? And you might say, well, why are we saying what is ham radio at a ham radio conference? because many of you have been involved in ham radio for years. But in fact, this is the HamSCI workshop, the Ham Radio Science Citizen Investigation. So many people here are already ham radio operators, but we have some people who are joining us from the science community and are less familiar with ham radio. And we can also have some people who are coming in and watching this from other fields who this might be their first exposure to ham radio, or they may have just heard about it. So I think it's worthwhile spending a few minutes to just say what ham radio is. So ham radio, this is a hobby for radio enthusiasts. It includes communicators, builders, and experimenters, all sorts of people, anyone who's interested in how radios work, interested in communication via wireless signals. We have a very wide-reaching demographic. It covers all ages and walks of life. There are over 760,000 ham radio operators in the United States and about 3 million worldwide. And what makes a ham radio operator? It does take a little bit more than just having an interest. You actually need to be licensed by your federal government. So what do you need to do to get licensed? There's an exam series. In the United States, there are 3 different exams you need to take in order to get your full amateur extra license. And these exams, they cover questions about basic radio frequency, electrical engineering knowledge. And the nice thing about these exams is they provide a path to learning, and it ensures a basic interest and knowledge level from each participant. So
Nathaniel, can I interrupt you? We cannot see your slides. You did not share them.
Oh my gosh. Thank you very much.
No problem.
Here we go. How's
That's better.
Okay,
That's good.
So yes, so here's the University of Scranton. There's Loyola Science Center. That's where we're all supposed to be meeting. Here is the HamSCI Workshop 2020, the overall connection. So yes, so what are ham radio operators? They need to be licensed by their federal government, and this licensing process ensures some pathway to knowledge. It's actually an educational process, just getting your license. And each ham has a government issued call sign. So you will see that throughout this presentation. So my call sign is Whiskey 2 November Alpha Foxtrot. Those are phonetics that stand for the letters W2NAF. So here we have the 2 Joshes from NGIT. They've got KD2JAO and WB2JSV. They're over here. We'll be hearing from Bill Engelke, AV4EJ later. That's his call sign, and there's his home ham radio station. And we'll also be hearing from John Ackerman later, N8UR. He's interested in constructing devices that have very precision time measurement capabilities. So ham radio operators, all ages, walks of life, and interest, but brought together by the common interest of radio engineering, communication, and experimentation. So here are some examples of ham radio communications. We cover emergency and public service. So if there's an emergency and communications break down, ham radio operators have the ability to set up in the field and communicate over long distances without any public infrastructure. So that's very important. I've participated in other field operations through the scouting program. So here's the K2BSA Scout Jamboree system. We will be hearing from the very well-known contester, Tim Duffy, later today, K3LR. So here's his station. Now what contesting is, this is where you're really gamifying ham radio. You're saying, how many people can I talk to in a very short period of time and in how many different places? And what's really interesting from the science perspective is there's a lot of science that goes behind this. You can learn something from watching how the contesters behave and how their signals propagate. And conversely, the contesters can help the ham radio operator, can help the scientists by providing a data source for the ham radio. For the scientists, there are his antennas. We have some participants all the way up in Alaska. This is an actual research station, but they also have a ham radio station up there. So sometimes we go to faraway places, and ham radio operators like to talk to people in these faraway places. And that could include what we call DXing, or talking to places, faraway places. DXing stands for distance. Now, on the other side of the field, so that gives us a little bit of an introduction to ham radio. On the other side of things, we have people who are space physicists, space scientists, and space weather people. And these people may be like me. I came into the field because I was interested in ham radio, and space weather and space science affected my radio. But some of these people came into a different path. They were just interested in how the world works. What are the physics behind how the sun interacts with the earth? What are the physics of the atmosphere? And so some of these people, they may not have ham radio licenses, but they may have very strong expertise into how radio signals actually propagate, or what affects these radio signals. So there are two main systems that are actually coupled together, but for various reasons, we separate things into two different thoughts here. We have the geospace system, which includes the sun, the solar wind, the Earth's magnetosphere, and then that connects down into the ionosphere. And so here with the geospace system, you get a lot of input from the sun and the solar wind, and that affects how radio waves propagate on Earth. We also have, looking in the atmosphere on Earth, we have the neutral atmosphere down here, where there's no electric charges, and that's connected with the ionosphere, which is electrified, and all of these things can also affect radio waves. So by looking at how the ham radio operators' radio signals travel through these layers, we can also remote sense or see the effects that the physics here has on this, and we try to understand what the physics is by looking at how the radio waves are affected by these systems. So we'll be talking a lot about space weather, personal space weather station in this particular meeting. So hams, they often think about operations, ham radio operators. They often want to know what the best frequency is for operating DX or talking to that faraway station. They might want to understand the radio frequency and interference environment. They might want to communicate better during emergencies. So often ham radio operators come at things more from an engineering type of perspective. How do we make this thing work? Whereas on the research side, the scientists, they often want to better sample the environment, better understand the near Earth space environment. And that's a really key thing. Scientists are very interested in just understanding how the physical environment works. And then the space weather people often take that back and try to apply it back to operations. I should note that we currently have a fairly good understanding of space climate, how things behave in a long term. So we understand something about the 11-year sunspot cycle. You can call it either the 11-year cycle or the 22-year cycle, but we understand something about that. And we can understand how there's day and night variations, which I'll talk about a little bit. We don't necessarily understand space weather very well. How do things change on a short-term scale? What is the variability from this? And this is where a lot of the research is right now. How do we go from just this understanding of space climate to space weather? So the Ham Radio Sciences Investigation, or HamSCI, tries to bring these two groups of people together, the ham radio operators and the scientists together. So we're a collective that allows university researchers to collaborate with the amateur radio community in scientific investigations. And so we have three main objectives. One is to advance scientific and research and understanding through amateur radio activities. And you'll hear lots of presentations about that in this workshop. Two is to encourage the development of new technologies to support this research, which we are doing with the personal space weather station, and you'll see many presentations about that. And then three is to provide educational opportunities for the amateur community and the general public. And this is one of the main reasons why we're making this HamSCI workshop so widely available in this webinar format, is to provide those opportunities and meet this third objective. So we're trying to meet all of these objectives here. So this is our third HamSCI workshop, and it's really important to have a theme. And so the theme for this workshop is going to be the auroral connection. Now, why do we pick that? Well, there's a couple reasons. So one, if I jump back to this slide over here, you can see that these magnetic field lines all pile into the polar regions of the Earth. And that allows charged particles in space to flow easily along these magnetic field lines and end up precipitating into the upper atmosphere. And that causes very interesting dynamics. if you look in what we call the auroral zone. And so this auroral zone is essentially a way of remote sensing into space. It also provides very interesting propagation phenomena. So I've been very fortunate. I've been able to go down to McMurdo Station and help service some of the scientific equipment down there. And while I was down there, I was able to operate their ham radio station, KC4 USB. So here's a recording that I made while I was down there. Were you able to hear that? Let me just reshare my screen here.
Yes, came through no problem.
Okay, great. So what you heard was all sorts of variability in the signal. Let me play that one more time. And that, I believe, is caused by the aurora. So that's my side tone. It's nice and pure. Now listen to the variability here. So it's that sort of variability that we can see in our ham radio signals that's also of interest to the scientific community. And we'll be hearing quite a bit more about that tomorrow. The other reason we picked the auroral connection is there is another citizen science project called Aurorasaurus. So Ham Radio Science Citizen Investigation is a citizen science project where we aim to advance science by interacting with the community. And we do that through ham radio. Dr. Elizabeth McDonald from NASA, she founded Aurorasaurus a number of years ago. And she focuses on doing citizen science with the aurora. And so by teaming up together, we're able to investigate both the optical aspects and the radio aspects of the aurora. And so this is where our theme comes in and where we're going to have our Saturday morning tutorials tomorrow. Liz will be talking about Aurorasaurus and the optical aurora. Dr. Jim LaBelle from Dartmouth College, he'll be talking about auroral radio physics and how you can observe natural radio signals from the aurora. And then we'll have and so Liz and Jim, they represent the scientific side of things. And then Dave Halliday, K2DH, he's going to represent the amateur radio side of things. And he's going to talk about how you can actually use ham radio and the aurora to communicate. So that'll be tomorrow morning. Okay, this year we're virtual. So there's a few things that are different about this workshop than your typical HamSCI workshop that you might attend in person. So I want to cover a few things. So every session is going to have a session chair, and that will be me for the oral talks, and it will be Laura Brandt for the poster and demo session. So the session chair is the person responsible for introducing talks, controlling the flow of questions, and keeping track of time. We also have assigned Zoom moderators. These are panelists who are assigned to monitor the Zoom chat window and interact with attendees. The presenter, of course, is the person giving the presentation. The panelists, this includes both presenters and invited participants. Presenters can share video, talk, and ask questions directly. So you'll be hearing, when you see people's pictures on the screen, they're serving as panelists. Attendees are people who've signed up for this workshop through the internet on the hamsci.org website, and they can watch and listen to the workshop, but they cannot directly talk or share video. You can, however, you should ask questions and make comments through the Zoom chat window, and the moderators will be watching that chat window and they can ask questions on your behalf. You can also raise your hand to get the attention of a moderator. There's a button on the bottom of your video screen that says raise hand, and then if you do that, the moderator should chat with you via that window. We're also live streaming and video recording this. There is a YouTube live stream account address that's posted on hamsci.org/hamsci2020. You cannot chat in the YouTube stream. You need to log into Zoom for that, but this is an easy way to watch the workshop without having to have Zoom installed on your computer. And the meeting is also being recorded, and it will be post-processed and edited by Jason Johnston, KC5 HWB of Ham Radio 2.0. So thank you very much, Jason, for helping out with this. Okay, are there any questions right now? Any questions from the panelists or comments? You can raise your hand. Bill Lyles, are there any questions from the attendees?
No.
Yeah, no questions from attendees.
All right, thanks. Okay, well, thank you very much, everyone. We'll get started with the rest of the program. So my first talk is going to be an overview of the Personal Space Weather Station project. So in addition to the Auroral connection, HamSCI is also funded to develop something called the Personal Space Weather Station, and we're funded to do this through the National Science Foundation. So this HamSCI workshop serves a dual purpose. One is to have this Auroral connection theme and talk about ham radio science in general. And the second part is to serve as a team meeting for the Personal Space Weather Station team, the people working on this particular project. So I'm going to do in the next 10 minutes or so is just give an explanation, an overview of what this project is and a general project update. And then after my talk, for the rest of the morning, we'll be hearing talks from other team members about specific parts of the project. So we've already mentioned that ham radio operators are able to communicate long distances, and their signals can be affected by the ionosphere and by space. So how exactly does that work? So over here on the left, these are frequencies that ham radio operators often use. I especially have a particular interest in these HF frequencies between 3.5 and 30 megahertz. Other people have more of an interest in maybe medium frequency and low frequency bands. Other people might have an interest in high frequency bands, but they're all affected by the ionosphere and the atmosphere and other effects in different ways. So if we look at the HF band, ham radio operators routinely use HF and VHF trans-ionospheric links. What does that mean? Well, the ionosphere is a layer of the upper atmosphere where you have electrically charged particles moving in what's called a plasma. And you can have gradients in the plasma density in the ionosphere with a peak somewhere between 200 to 300 kilometers altitude above the Earth's surface. That's what we call the F region ionosphere. Ham radio operators will often use roughly 100 watts into a dipole antenna. This is a fairly modest station, and you can see we have a number of different modes. We can use digital modes, like FT is very popular these days. You can use Morse code or CW. We also have a single sideband phone. If you have a transmitter located in one place and a receiver located in another place, you can have what we call, this is a ray trace diagram using 14 megahertz. You can have that signal go up, be bent or refracted by the ionosphere, and then come back down and reach that signal. Anything that happens in the ionosphere will modulate or cause an effect on this signal that we can see over here. Also, you have to have the frequency that the frequency that you're using be just right in order to get this sort of refraction. If you go too high in frequency, you'll escape into space. If you go too low in frequency, you could be absorbed by the ionosphere for a particular ionosphere. So there's a lot of things, but the basic idea is you get this refraction of the signal. How is the ionosphere created? To the most basic level, the ionosphere is generated by X-ray and ultraviolet energy from the sun hitting the upper atmosphere and ionizing neutral particles, meaning that you're knocking electrons off of neutral molecules and atoms, and those electrons are now just free floating and they have a negative charge. And then you also have positive ions left over, and they work together. During the day, you have a stronger ionosphere because it's constantly being driven by the sun, and you often have more layers during the day. At night, you have less layers. The electrons, they'll recombine. You don't have the external drivers as much, but it doesn't totally go away. This is a simple day-night relationship of the ionosphere. We're going to skip that in terms of time. Where do ham radio operators get their data right now? We have some very nice observation networks right now that you can use. This includes the reverse beacon network, which is monitoring Morse code, WhisperNet, which is monitoring the weak signal propagation network. We have PSK Reporter, which is monitoring FT8 and PSK31 and other digital modes. And so these networks are great. They're quasi-global, they're organic and community run, and they provide a good picture of what's going on in ham radio data. And so you can actually take observations from these systems. So these are observations from from PSK Reporter. I'm sorry, from WhisperNet. These are observations from WhisperNet and the reverse beacon network showing the effect of a solar flare. When you have a solar flare, that can cause a radio blackout. It can cause the ionization to go so high in the D layer that it absorbs the signal. So this is before the solar flare. You have lots of signals, lots of communications. This is after the solar flare. And we can see that in the data. And if you lay it out right, you can measure how long it takes the system to recover, and you can see multiple disturbances. We can see traveling ionospheric disturbances. We'll be hearing more about that later today in Diego's talk. And here you have these wave-like structures that move through the ionosphere. So here you can see this is 14 megahertz band. This is how far away you can communicate with respect to time using WhisperNet and RBN observations. And you can see these wave-like structures move through here. So you can see all of this in the ham radio data we have right now. These are examples of Doppler shift observations taken during the eclipse. So here you're listening to WWV near 10 megahertz, and you can see that as daylight comes and the ionosphere becomes more dense, you get these positive Doppler shifts. As night comes, the ionosphere recedes, you can get these negative Doppler shifts as the path length increases. And here, this is taken during the eclipse. You can see the effect of the eclipse on here as well. So you get all these different effects. So this is all great, but the ham radio receiver networks we have, they weren't designed for science. So we could create a network. What if we could create a network of personal space weather stations that were designed for both science and ham radio from the ground up? And so that's the idea behind the HamSCI Personal Space Weather Station project. So the idea was first told to me by Ward Silver. He said, well, you have all these personal terrestrial weather stations that are multi-instrument internet connected and easy to set up and a reasonable cost. Can we do something like this for space weather? And that's where this idea came from. We want something that can be useful to ham radio operators, useful to space science and space weather communities, have a modular instrument design, small footprint, nice user interface, and standard format to send data back to the central repository. And so that's what we have over here. This is a block diagram for what we're planning the personal space weather station to be. At its core, there will be some sort of software-defined radio, which that is what Tapper is primarily designing, the Tangerine SDR. And this software-defined radio should be capable of monitoring all the things we just saw with RBN and PSK Reporter and WhisperNet. It should also be able to characterize HF noise, be able to possibly detect lightning, detect traveling ionospheric disturbances. It should be very stable using a GPS disciplined oscillator. We'll have a single board computer to do the processing, send it back to the internet. So that's the basic idea. We actually are going to have both a low cost and a performance-based personal space weather station. Case Western Reserve, we'll hear from later. They're developing a low cost station. Tapper is developing the Tangerine SDR performance-based station. We have a number of teams. These are the different teams we'll be hearing from today. I am Nathaniel Frizzell at the University of Scranton. I'm happy to announce that we have just hired a postdoc, Dr. Dev Joshi, who will be working with us working on the radio science. He'll be starting in May. University of Alabama, they are designing the software and the database. Tapper and Zephyr Engineering, they are designing the performance-based software-defined radio, the Tangerine SDR, and they're also doing the ground magnetometer design. Case Western Reserve University is doing the low-cost system. New Jersey Institute of Technology is supervising the magnetometer science, and the MIT Haystack Observatory is providing additional scientific analysis and advising on the project. So we have all of these people involved here. We are well on our way in terms of progress. We already have mock-ups. There are some boards already in place. You can get the specification documents at tangerinesdr.com, and we will hear from each of these team members that will give their own updates. So thank you very much. Are there any questions? Do the panelists have any questions? Okay, no. Any questions or comments from the attendees?
Nathaniel, there is a question. There was at least one question. Bill, have you got that?
So I don't have it worded as a question. I'm trying to figure out the question.
Well, there's more than one that has come in. Alex Christ here just asked, are there cost targets defined for the low cost and performance-based stations?
Yes, roughly we'd like the low cost to be sub $100 and the performance space to be around $500.
Can I ask my question, Phil?
Sure.
Okay, Nathaniel, this is Liz McDonald.
Hi,
So
Liz.
I was wondering how large those databases are already, if they're gigabytes, or if you have any number on just, I'm just curious, the total amount of data that's already built up, or the rate per year, that sort of thing.
Sure. Bill Engelke, are you there? Can you answer that question?
As far as spots that have been collected from WhisperNet, Reverse Beacon Network, PSK Reporter, and the DX Cluster, it's just somewhat less than 5 terabytes at the moment. We are interested, we're hoping we can figure out a way to put that into the Madrigal system. We still need to do some work to figure out how to do that, but the idea is to make it that publicly accessible, organize it so it doesn't work very well as a hierarchical database. It's too big, it takes too long to search. So we're going to take a big data approach and just store the files in a publicly accessible format, basically allow people to download at will and do things like sequential search.
Thank you.
All right, thank you very much. Okay, it's now time for our next speaker. So I'm going to stop sharing on my side, and Scotty, you can go ahead and take over the sharing while I introduce you. So next we have the overview of we have the Tangerine SDR data engine and overall architecture. And this is going to be by Scotty Cowling, WA2 DFI of the Tapper Group. So Tapper is an amateur electrical engineering organization or group. And Scotty can explain a little bit more about what Tapper is. And Tapper is responsible for developing the performance-based side of the personal space weather station. So take it away, Scotty.
Okay, can you hear me okay?
Yes, but we can see your presenter view, not the full screen view.
Stand by 1 second here if I can. Okay, how's that? Does that work better?
That looks good.
Okay, well, thank you, Nathaniel. And I've got a lot of slides to cover, so my apologies if I go kind of fast. A couple of them do dwell on what Nathaniel had said, or they're kind of copies of them, so I can go through them pretty fast. But we'll get started now with kind of a hardware overview of the architecture and the way we split the board up into modular pieces here. In fact, I'm going to move my camera over here. Be a little bit better so I can look at everyone instead of looking over at the wrong screen. Okay, see if I can advance this. Okay, so what is a Tangerine SDR? You may have heard of heard the term Tangerine SDR. Basically, I'll go over the features of the Tangerine real quick here. And personal space weather station is only one of the use cases we have for the Tangerine SDR. The idea being that the more use cases we can come up with, the more of these we can build, and therefore the cheaper they'll be. And of course, we've got the $500 price target for the SDR, which I think we're going to be able to beat. And we may have some less performant versions that will be close to the $300 range if we can do it, as in shown down here is the second bullet item. But the idea is if you want high performance and you want lots of features and sensors, you'll be able to add them on, and you could easily, as we all know about ham radios, you can buy the low end one, or you can buy the stripped down one that has no options, or you can load it all up and you can spend a lot more money, get a lot more performance. Will be all open source hardware and open source software. And hopefully when we get done, it will be advancing the state of the radio art. So what are we going to have? Like Nathaniel said, a small footprint, reasonably low power consumption. Modular is the key word here. So you can add features or delete features to basically build the kind of station, kind of software-defined radio that you want, that does the functions that you want without having to pay for things that you don't want. Web-based user interface for ease of configuration on a local display, and the built-in networking interface to the data cloud, which is the big data that Nathaniel was referring to be able to store multiple formats of data. So here are some of the other target applications. Of course, the HamSCI Personal Space Weather Station is what we're going to talk about today. It's the first one on our list of target applications, but the idea is to keep it modular and flexible enough and programmable enough to fulfill these other use cases. For instance, a satellite ground station or academic uses, or just a regular amateur SDR that you might want to put together. I know there's lots of them to choose from, so we like to have a nice feature set for amateur experimenters. Okay, so for general amateur use, what we're planning to do here is not only provide the personal space weather station functionality, but provide more functionality that average hams might want. So you're going to lay out $400 or $500 for the station. You know, you're probably going to want to do more than just collect personal space weather station data. So we're going to build in WhisperNet and reverse beacon network functionality and digital modes, at least monitoring digital modes, because the first unit out of the door is going to be just a receiver. So we'll be able to monitor digital modes, but we won't be able to actually transmit beacons. And since this is software-defined radio, we're going to be able to concurrently collect data for the Personal Space Weather Station project, as well as FT8 and the other amateur radio modes. And we can do this on multiple bands simultaneously since the architecture is a direct sampling receiver. Okay, so this is kind of a enhanced version of the block diagram that Nathaniel showed. And so we split this up into a data engine and a single board computer. And the idea is that I can build the single board computer functionality into the data engine, but it costs so much and single board computers are so cheap. Why do that when you can buy a Raspberry Pi or an Odroid for well under $100 and get functionality that you couldn't get any cheaper way? So what are we going to build now after all that talk? This is the basic block diagram, the data engine board on the left, and these RF modules and clock modules, these are plug-in modules here. You can see my cursor going over them. And we connect this with a 3-port gigabit Ethernet switch to a single board computer. So we have a single Ethernet connection to the local network. So the Tangerine SDR system really is going to require a single board computer to do all of the networking and a lot of the data crunching, whereas the data engine and the RF modules and the clock module are going to be responsible for acquiring the data and applying timestamps to it and formatting it. So now we go into lots of details, which I hope I don't go too fast, but these slides are up on the net. So Nathaniel can, when we get done here, Nathaniel can tell you where you can get those. The PDFs of this presentation are up online. So the data engine, I'm going to talk about different pieces of it. We'll start with the FPGA, a field programmable gate array, and a 3-port gigabit Ethernet switch. We're going to use an Altera Max 10, 50,000 logic elements, the largest Max 10 FPGA that they make in a 672-pin package. We're going to have some SD RAM and some flash memory. The flash memory is chiefly going to be used to store additional FPGA configurations, while the SD RAM is likely going to be used to buffer data. And then some serial EEPROM, and lots of people laugh at me, but when you see a part like this and it costs 30 cents, you don't ask too many questions about why you might put it on your board. Because it's cheap and we need additional configuration memory. We may need this, so this is what it's there for. Okay, a wide voltage input, so we're going to have a station supply to be able to run it. Again, I told you about the 3-port gigabit Ethernet switch, which allows you to connect up a single board computer and connect the Tangerine system to your local network without having to have an external switch. We're also going to have a cryptographic processor with key storage. The main thing this part brings to us is a 72-bit unique serial number. Temperature sensors and power on these are just standard things that you put on most every board. Very inexpensive. And so now get into the more the meat of it is how are we going to acquire the RF? And we're going to have 2 RF module slots, and they're going to use 140-pin MEC connectors. You can either use one for transmit and one for receive, or you can use 2 receivers. The first module we're going to make is, I'm going to show you in a second, is a dual channel receiver. So even not using only one slot, you're still going to get 2 synchronous receive channels that will cover 100 kilohertz to 60 megahertz, 55 megahertz. Okay, so Tom McDermott is going to talk about this in a few minutes in much more detail than this, but basically it's going to be a 14-bit, a dual 14-bit, 122.88 megasample per second ADC. We're going to have a selectable or switchable attenuator and a 20 dB low noise amp. The amp is in circuit all the time, and the attenuator is ahead of the amplifier. So it saves us the problem of switching the amplifier in and out. A fixed 55 megahertz low pass filter, but then we're going to have an optional user-defined plug-in filter that's going to be on headers. So if you live near a broadcast station, you could put a broadcast band notch filter in. We've actually run power to it, so if you really want to build an active preamp on the user-defined plug-in filter block, you can do that also. We also are going to have, we have an onboard switchable 50 ohm calibration noise source that can be switched in and out with software, so we can calibrate the front end of the radio. And this is a block diagram of the RF module. Now again, I said these are modular, so this is the first one of many is what our hope is, and we will be able to tailor these to whatever application where we're trying to implement. Okay, so future ones might be, like I said, for satellite. Some of these ICs made by Line Microsystems, and this one's made by Analog Devices, the 809361. These are complete transceiver systems on a single chip. And we've tried to make the connector pinouts as flexible as we can so that we have allowed these particular chips to be implemented in an future RF module. So look for these coming along in the future to give you a lot more expanded capability. And Tom McDermott will be providing more detail on the RF module. It's special thanks to Tom for his RF expertise in designing this module, as you'll see when we get to his presentation here. Okay, moving along, the clock module is next up. So the clock module is one of those variable things that if you want just a regular simple receiver, you don't need a particularly high performance one. but generally on a direct sampling SDR, the performance of the SDR is not only defined by the A to D performance, but by the performance of the clock module. In other words, how clean is it, how jitter-free is it, etc. So, and usually it comes down to the more money you spend, the better clock you get. So we want to make the clock module good enough, but not generally better than necessary, because it just is going to cost more money. So the first case is no clock module. So for the low-cost version, we have an onboard TCXO that we can use that will replace the clock module for general purpose use, not particularly stellar, but adequate, and certainly low cost. If you want more performance than that, then what you do is you plug in a modular clock module. And the idea is to build several versions of these, one of them to satisfy the requirements of the personal space weather station, and other one to satisfy other use cases that we have mentioned earlier. And this is really a work in progress at this time. And I'll show you, this is kind of a basic block diagram. Thanks to N8UR for this, for drawing this up. But this is basically the performance clock module. And the idea here is that we will take this board, this design, and we will depopulate pieces of it to make different clock modules in different price ranges and different performance ranges. So we can perhaps use one copper layout to satisfy several different use cases. And John will be talking about the clock module later on today. And again, thanks to John too for taking on the clock module design. He's very well versed in clock and timing. He belongs to a group called Time Nuts, which explains a lot, but I'll let him go into that. Okay, a little bit different view of the modular solution here. The center board here is the data engine with gigabit Ethernet off to the side to the single board computer. Also, we have low speed connections to the single board computer like UARTs and SPI ports and things like that. And we also include, and I think this is the only board that I know of that's made that includes USB 3 and gigabit Ethernet both for their communications ports. And you can see that we also have a low speed I/O. I call it low speed I/O because it's low speed compared to the RF modules, which are down here on the lower left. The MEC has been deleted, and so I won't go into that. But the idea here is we get low speed Raspberry Pi level I/O like I2C and SPI ports, but then we have also have some high speed I/O from an expansion card that's a little bit bigger than the Raspberry Pi hat, and I'll get into that in just a second. Okay, so communications interfaces, a true 5 gigabit per second, full duplex, one lane in, one lane out, a USB 3 device interface. We also added a USB 2 host interface. So if you have an RTL SDR dongle, you'll be able to plug that into that port, and you'll be able to do things with the RTL data that you can't really do on a Raspberry Pi because you'll have an FPGA at your disposal to process the data and format it. And again, dual gigabit RJ45 ports. And they're aggregate 1 gigabit because it's a shared switch. So, okay, and I'd like to go into a little bit of detail on the low speed I/O. We can handle standard low speed I/O connections like you're all familiar with on the Raspberry Pi, UART connections and I2C connections. Typically, they're below 4 megabits per second. Some of them are a little faster than that, but it's generally used for sensors and things like that that don't have to be read at high rate of speed. And for things like PTT and a keyer paddle and the power amplifier key, things that are relatively low speed. So what we've done is we've said, okay, you can plug a Raspberry Pi hat onto the expansion connector and pick up all the low speed I/O that is on this blue connector here. But if you want to build it, we will build a custom board that has an extension on it that has a high speed connector down on the bottom. So now you not only get all the Raspberry Pi low speed connectors, all the data, but you get a high speed, some number of LVDS lanes that are high speed coming in on the high speed connector. So that really expands the capabilities of what you could put on this Pi hat leaf type format of board. So again, low speed direct support for Raspberry Pi type connectors. And then what you can do is you can take, we can build a leaf board that will have all of these different shields. Shields, I guess they call it a shield or a cape, or there's lots of different names for them. But you basically just make it a connector translator. And then you can use any of these option boards that are, and there's thousands of them available. And these will be generally for low speed IO and sensors and things like that. So what are we going to have in the future for Tangerine? Larger, faster FPGAs, more RAM, maybe an SSD port for storing data locally, perhaps higher speed data ports, because gigabit Ethernet scales very nicely to 10 gig E and then 40 gig E, et cetera, et cetera. So that's kind of a look at the future. But the idea is to preserve the clock module and RF module ports so you can use the same acquisition boards that you use now and the same clock module that you use today. This is kind of a mechanical layout. This is kind of hard to see on a flat screen, but the red here is a leaf board. The orange subset of it is the Raspberry Pi hat. Then down here in the green is the clock module, and the RF modules exist on the back side of the board. You can see the blue outlines down here. These are the RF module connectors, and the RF modules are behind the data engine. And the black outline here is the data engine. And to give you an idea, this is roughly 100 to 120 millimeters square. So 4 to 5 inches square. So now this is probably the question you're all wanting to ask, but when can you get one? I think this has already been asked. So this is kind of the schedule that we have, and we're trying to beat this schedule, but I won't promise that I can come out ahead. And since Hamvention is canceled, and in fact, almost everything is canceled, but this great convention here, it gives me more time to work on this, so we may be able to accelerate it some. But certainly by the Digital Communications Conference in September, we will have all of these pieces in, if not in production, at least prototypes that you can look at. And again, tangerinesdr.com for more information. Pretty much everything is put up there by our awesome webmaster KV0S, who's got videos and specs and links to TeamSpeak sessions, which are here. And actually, you don't really need to know this because on tangerinesdr.com, this information is all up there, so you can find it there. And we have a TeamSpeak session every Monday evening at 2100 Eastern Time, 9 o'clock Eastern Time. You're welcome to join, listen, talk, whatever you like. Everyone's welcome. And that's all I have here. So any questions? We'd be willing to take them.
All right. Let's see. Thank you very much, Tom. I'm sorry. Thank you very much, Scotty. Thinking about the next presentation already.
Yeah.
Thank you very much, Scotty. That's very good. I think let's hold questions right now and let's get Tom on because we are running out of time. We will have the webinar open during the break, so maybe some of the presenters can stick around during the break and answer questions then if we run out of time for the individual presentations. Okay, Tom, go ahead. And Scotty, what you can also do is you can look through the chat window and you can answer some of the questions directly in the chat window too if you see them. Okay, so next we have Tom McDermott, N5EG, and he's going to be talking about the dual receiver RF module design for the Tangerine SDR. And Tom is also with the Tapper group. So go ahead, Tom.
All right, thank you very much, Nathaniel. Can you hear the audio okay?
It sounds great, thank you.
Oh, okay, very good. This presentation dives in a little bit deeper on the first receive module that Scotty talked about, which is a dual channel receiver. At HamSCI 2019 last year, there was a presentation on the requirements for the receiver. And at tangerinesdr.com, there is a requirements document that discusses a little bit of the details. So if you have particular questions, you might want to look back to the videos that Jason, I think, has put up on HamSCI 2019, or look at tangerinesdr.com for documentation. So in this presentation, we'll give a little bit of a high-level diagram, which Scotty covered on the receiver. an update of where we are on the receiver design at this point, a little bit of discussion on configurable settings for the receiver, and then some notes on characterization and calibration that we will plan to do for the receiver. This is a high-level diagram of the receiver. It's slightly unusual in the way that it's laid out, and we'll talk about that. This single module is a dual channel receiver, and as Scotty showed, there's room for 2 modules on the data engine, and so in fact possible to have a 4-channel receiver by putting 2 of these modules on one data engine. This module has a couple of SMA connectors for receive. The receive signal comes into a relay, and that relay either passes the signal into an attenuator or it selects a wideband noise source. Right now, the noise source is set up to provide 5 dB excess noise ratio. That's 5 dB over the thermal noise, and that could be changed with some resistor value changes. Right now, we think 5 dB ENR is probably the right amount. It then goes to a relay switched resistive attenuator, and then the optional pluggable filter that Scotty talked about. The entire RF section is isolated and ground from the digital and from the system ground. And there is a bonding strap, which is shown, I don't know if I have a mouse here, there's a bonding strap here in the center, where if you choose, you can bond channel 1 analog ground to the digital ground, and the same thing on channel 2. If that ground is not bonded, then the channel 1 analog ground will float with respect to the system ground. Each of the channels then goes into a dual ADC driver, which is a 20 dB gain driver. The noise figure of the driver is spec'd at about 6.2 dB. And then that dual driver feeds a dual 14-bit analog to digital converter. And that ADC is clocked by a 122.88 megahertz signal from either the data engine or the clock module. There are some options to select where it's clocked from. And in return, it provides a double data rate interface to the data engine. There's enough bandwidth coming off a dual converter and enough pins that in general, you need a DDR interface to the data engine. There's options to bond or to isolate the antenna ground from the digital ground. The noise source is relay switched. What all of that means is there are no active components ahead of the dual ADC driver chip. And so everything to the left of that transformer is passive, or in the case of the noise source, transformer coupled. And this is done in an attempt to preserve dynamic range and to keep spurious noise sources out of the front end. There is a passive pluggable filter option. We'll talk about that a little later. Right now, we've designed an analog, an AM broadcast band stop filter. Others could be designed, but we have that as the first design. There is an option for an active pluggable filter where we can pick up not only the RF connections, but also power and ground if in the future we want a active filter that has a preamp on it. There are no active components in front of the dual ADC unless we plug in an active pluggable filter, in which case there obviously would be. The attenuator is a relay switched attenuator, selecting 0, 10, 20, or 30 dB attenuation modes. As of March 16th, we've completed the schematic. There's still a few tweaks. The layout of the engine of the RF module is very dependent on the exact details of the data engine. And so there's been a few pin swaps going on. So the schematic, I'll say, is complete, but we'll make a few tweaks depending on the requirements of the data engine. The printed circuit board layout is complete, but also being tweaked for dependencies on the data engine. And right now, this is down to a few pin swaps on the data side. Nothing has been fabricated or built yet. The future tasks we have on the receiver are to assemble the first prototype of the receiver units, to complete the data engine, to do checkout, to build a FPGA test firmware load so that we can talk to the analog to digital converter on the RF module, and to start acquiring test buffers. And the test software will retrieve test buffers, configure the ADC, and then we'll have to make measurements and start the characterization process for the receiver. We're anticipating that we'll have a layout spin or two on the receiver. There's almost always something that has to be modified or fixed on the receiver, since not only is it a digital device, but it's a very sensitive analog device at the same time. This is the preliminary layout of the dual channel receiver. It's 115 millimeters long. It's about 48 millimeters wide. The MEC connector that Scotty talked about is on the back side of this module. The back side is primarily two ground planes, the digital ground plane and the analog ground planes, one for channel 1 and a separate one for channel 2. And those are on the back side to try to shield this from the data engine signals. On the top side here, you can see the channel 1 antenna on the top left and the channel 2 antenna on the bottom left. Those go through the relays. And then in the center, you'll see a pair of the filter modules, the plug-on filter modules. If you don't use a filter module, there's a bypass, and so you can put in a strap to bypass the filter module. If you equip a passive filter module, you just remove that strap and then plug on the filter module. And then goes through a U2 filter, which is a filter that is a roofing filter. It's a 55 megahertz low pass filter module. The spec says 40, but the roll off is pretty gentle. It then goes through a power and ground header. The active filter module will plug on to not only the filter input and output connectors, but also the power and ground connector. So the active filter module is larger than the passive so that it can pick up the power and the ground connectors over here. Then there's a strap here if you want to bond the analog ground on channel 1 to the digital ground. You can plug on a 0.1 inch clip, and the same thing for channel 2, where you can plug on a shorting strap if you want to bound the two grounds. Then U6 is the dual AD converter. I'm sorry, the dual low noise analog to digital converter driver chip, and then the dual channel ADC chip. There's a few power regulators to derive the low noise voltages for these circuits here. And then where the Tapper logo is, there's a lot of double data rate interfaces to the MEC 140 connector, which connects it down to the data engine. This is the layout of the AM broadcast band passive filter. You can see it's a fairly small module. It's about 10 by 20 millimeters in size. The active version of this will be longer, about 30 or so millimeters to pick up that power and ground connector. Modules can also be wider than 10 millimeters. The module width can go up to about 20 or so millimeters if you have a particular filter that you need to design that takes more space. The width limit is due to the fact that we have, of course, to accommodate two of these, one for channel 1 and one for channel 2, and so we would need a pair of these. Getting a message, my internet connection is unstable here, so let me know if I have an audio problem. So in terms of configurable options, there's an option to bond or isolate the grounds. Isolated grounds help reduce common mode noise signals, and that can be very important in some applications. Some of the folks on the team have noticed a problem with common mode noise and have had to implement common mode noise chokes. Those come at the cost of a little bit of increase in attenuation. And so we've tried to provide a lot of common mode isolation on the receivers to avoid the need for common mode chokes. There may be severe cases where both are needed. If you use a powered remote external antenna, some antennas, for example, small powered loops or small powered dipoles may need power. And so I'll talk in the next slide or two about how to do that. Bonded grounds may be needed in some jurisdictions. There's some places where the input ground is required to be bonded, and so there is a bonding jumper for those particular applications. The noise source has a couple of options. There is a strap so that the noise source can be completely disabled and power removed from the noise source. I don't think that that'll be necessary, but there is a strap option to do that. If the noise source is strapped on, that is, power is applied, then the noise source can be turned on and off under computer control. So the noise source can be turned off and the relay connects the RF signal into the attenuators, the filters, and the low noise amp. Then the computer can turn on the noise source independently on the two channels, channel 1 and channel 2. That disconnects the receive signal and instead connects the 5 dB excess noise ratio signal to the attenuator. One would probably want the attenuator set in the 0 dB setting at that point. And this allows switching back and forth between the receive signal and the noise source, which will allow, for example, looking and trying to measure the background noise level. That's called a Dickey switch, where you can rapidly switch between those two. It also provides a way to calibrate the receive amplitude settings by looking at the broadband noise source and looking at the signal level from that compared to what's expected. So it provides a couple of different functions. In a lot of cases, we anticipate that folks will want to use a powered antenna. And so if you want to have a case where the receive ground is isolated and yet DC power is applied to the antenna, then one would probably hook it up like this, where the receive channel has its ground bonding disconnected so that its ground is isolated from the system. You would then power the antenna through a common mode choke so that you can have a DC power ground reference. You then need to have a bias T, which provides the differential mode choking so that you don't short out the receive antenna signal, and then a DC power. So this is how you would provide power remotely to a powered antenna while yet maintaining an isolated receiver system. And again, if code requirements are that you bond this, then you can bond the ground, and you'll have to provide a second common mode isolation choke. So we've tried to provide a lot of flexibility in how the receiver can be connected. This is a simulation of the AM broadcast band passive band stop filter. It's optional. The attenuation is in blue here on the left, and you can see that it notches out over a pretty wide frequency range. The AM signal, broadcast band signal, it's a reflective filter, which is shown at turn loss in red here. One of the issues with any kind of reflective filter is that there is a lot of group delay. And so here we can see two large group delay spikes at about 500 kilohertz and about 1.5 to 2 megahertz. And so if you equip this filter, then there will be a substantial phase nonlinearity in the AM broadcast band. In terms of characterization and calibration, we know we need design characterization, and what we mean by characterization is those RF parameters we think are likely to be similar across a wide production range of units. So that would be things like the noise source level from the onboard noise source, the frequency response of the noise source, the sensitivity and noise figure of the receiver, the frequency response of the receiver, the phase response of the receiver, channel isolation, phase noise, spurious responses, other things associated with the receiver, and the receiver channel group delay, which is primarily due to the 40 megahertz, very soft band limiting filter on the front end. Per channel calibration, where we anticipate likely significant differences between units, are primarily related to the filter group delay of the pluggable filter, and that group delay is orders of magnitude larger than the 40 megahertz band limiting filter. And so if we need precise group delay measurements and we need an AM broadcast band filter then likely that will have to be calibrated on a per filter basis. Independently removed by either the data engine or the host software will be group delay. And in the case of multi-channel interferometry or polarization discrimination, if we've equipped, for example, a broadcast band filter, then the data engine is going to have to subtract out that group delay. And so also noise first level and frequency response may have to be slightly calibrated by the data engine. We're hopeful that with no optional plug-in passive filter, that the amount of group delay variation will be fairly small. One of the objectives of the receiver is to provide the capability for interferometry. And to do that, there's a couple of considerations we need to take into account. That the numerically controlled oscillators on separated receivers, these may be receivers separated by 10, 20, or 50, or 100 kilometers. Those NCOs need a common time and frequency reference for interferometry. The quality of that reference needs to be agreed upon by the science community. John Ackerman, N8UR, will talk about that in the next talk. The down conversion oscillators on separated receivers will have a static phase difference. That is, when you start the oscillator, its phase will be different than an oscillator on another unit. And so the phase offset will jump whenever that NCO is reprogrammed. So the static phase offset of that oscillator will need to be taken into account when doing interferometry. We may need compensation for things like RF filter component tolerance, antenna cable length differences, antenna preamp differences if we use an active receive antenna, antenna phase center differences, things like that. Wideband measurements may incur phase dispersion in some cases. Not using an AM broadcast band filter is desirable for wideband measurements. An active receive antenna may present some complications. There is a 3 antenna closure phase method called self-calibration that can be used to compensate for static phase differences at multiple antennas, and the references for those are here. And I think we're about out of time, so are there any questions?
Thank you very much, Tom. Yes, moderators. Bill, are there any questions?
Oh, but I don't know if we have time for them. But one of the questions is, how good is the reliability of the relay switches, a particular temperature range? Like if we use this very high up north, below zero temperatures.
Yes, we have not looked at the temperature reliability of the relays. The relays are specified as 1 million cycles, and so they should have a fairly long reliability. I'm not aware too much of the temperature limitations. I think there are other temperature limitations in the entire package related to capacitors. There are electrolytic capacitors all over the data engine and RF receivers. And I think those will have their own temperature limitations of around 0 to -20°C. So in extremely cold locations, it may be required to put the data engine and RF receiver module in a heated enclosure.
Thank you very much, Tom. Okay, quick announcement. We are learning as we go along how to manage all of the questions that we're getting asked in this virtual environment. So Liz McDonald of Aurorasaurus has kindly set up a Google Doc, and that link is now in the chat window. I've also just posted it to the agenda page on hamsci.org. And so what you can do is if you have a question and you don't get to ask it in person, you can put your question in the Google Doc, and then we will have the presenters go back over the Google Doc later and answer that. So that is now a live document that you can access. The link is on the top of the agenda page on the website. Okay, thank you so much, Tom. I really appreciate it. Next, we're going to hear from John Ackerman, N8UR, talking about the clock module design for the Tangerine SDR. Take it away, John.
Okay, thanks, Nathaniel. Let's see if I can get the sharing to work here. Okay, can you see the screen?
No.
Hello?
See you.
Oh, okay. Well, then need to figure that out. It worked before. How's that?
There you go.
Okay. Alrighty. Well, Scotty's given a good introduction to the overall Tangerine STR concept, and I'm going to talk about the clock module, a little bit about the design and architecture, but I'm going to spend most of this time talking about one of the design challenges we have, which is understanding what the real requirements are uh, in terms of performance for the clock system, because that has some very tremendous impacts. And then I'll also, along the way, talk a little bit about some comparisons of different GPS modules that I have been doing as part of our goal to find out which is the optimum cost performance ratio. So as an overview of the clock module, it's a GPS disciplined oscillator that has a set of minimal outputs plus a couple of optional ones depending on the requirements. Its main purpose in life is to provide the 122.88 megahertz required by the receiver module ADC, analog to digital converter, and the transmitter module DAC, digital to analog converter. It also needs to provide 1 pulse per second for time stamping, because one of the important features, particularly for interferometry, as well as other purposes, is that we can align samples across radios. And a time of day message, so we can take that pulse per second and convert it to what time it actually is. Optionally, we can provide a 10 megahertz output for external use. And also optionally, we can provide a number of synthesized outputs that could be anywhere from 100 hertz to over 1,000 megahertz in frequency. One of the key features of the module is that it is designed to be extremely modular, and all of the components talk primarily to a single FPGA that's on the module that acts as a switch matrix as well as doing other processing tasks. And we can populate the circuit board with the components that are appropriate for the required performance or functionality. Also, it's going to be usable separately from the Tangerine SDR. As Scotty mentioned, the more use cases we have, the higher volume we can build, which means the lower cost. So by using a daughter board, we can plug the clock module into, for example, a Raspberry Pi and do the Raspberry Pi, or allow the Raspberry Pi to do the control loop processing and whatever other activities the user might want. So we really are thinking of the clock module as ultimately being sort of a time nuts toolkit that can be used to build all sorts of capabilities at different cost points and provide different performances simply by using appropriate components on a single board, which again gives us more volume and lower cost. Here's the overall hardware block diagram. And as you can see in the middle, there is the FPGA that every component talks to. There will be a GPS module, and that will provide both a serial data stream as well as a pulse per second signal. There'll be a phase detector, and that's an important part of a GPS disciplined oscillator because it's going to tell you how different the local signal timing is from the GPS, and you use that as part of the control loop. It will have the capability of providing using a 10 megahertz oscillator that can be controlled via a digital analog converter to get the more traditional 10 megahertz GPSDO capability. But again, for the Tangerine SDR, the key thing is the 122.88 megahertz. And that is this module on the left, which has a crystal oscillator running at that frequency and a distribution. We need 4 separate outputs. So there's a buffer driver that provides 4 sets of differential outputs. And again, that oscillator is steered by a DAC so that it can be controlled either in terms of the 10 megahertz or potentially directly by the GPS. There's another alternative in the design that instead of using a crystal to get the 122.88, we can use a synthesizer chip that's driven by 10 megahertz. And there's some trade-offs in that that I won't go into now, but that will provide us the option of generating either the 122.88 or other frequencies as well. And then the FPGA will output communications, pulse per second, and 10 megahertz to the rest of the data engine for use as needed. So the key thing and the question that I have for you today is exactly what requirements the science community has. So we'd like you to tell us both what you want and what you need, because there is a price delta between the two. And if you're as old as I am, you are now immediately thinking of the Rolling Stones, and you can't always get what you want, but if you try sometimes, you just might find you get what you need. So we're hoping that the conversations that will happen perhaps during and after this meeting will lead us to an understanding of what those requirements are. And there are really 5 of them in the clock module, and I'll talk about these in more detail in the next slides. But first is the absolute frequency accuracy and the long-term stability. In other words, how close is the frequency to the cesium clocks in Boulder, Colorado? And how much do we know that we are on the same frequency as everybody else? The second is short-term stability, which is how much the signal wanders around. The third is phase noise, which is how much phase modulation is on the ADC, DAC clock source, because that modulation is in effect pollution, and it will cause a muddiness of the timing edges from the samples that we receive and reduce our ability to precisely measure them. Then there are 2 other aspects, which are the accuracy of the timestamp. In other words, how closely does the time on the tangerine track U.S. Naval make my mouth work, U.S. Naval Observatory, which is the U.S. time standard. And then finally, just as with frequency, there's accuracy, but there's also stability. How much jitter is there on the timestamp signal? And so those 5 characteristics are the ones that we need to understand in order to do the final design of the clock module. So talking about them in sequence, the first is the frequency accuracy and the long-term stability. And when we have a GPS controlling the system, that's typically the limiting factor. But if we're freestanding, the crystal oscillator aging is dominant. If we're running a GPS system, it's realistic to have parts in 10 to the 13 of absolute accuracy and stability when measured over 24 hours. And parts in the 10 to the 13 is effectively about let's see, that's I think 100 microhertz at a gigahertz. And I may be off a little bit on my scientific notation there, but you get the idea that that's pretty darn good. But in addition, there's a question about the short-term frequency stability and how much does the signal wander around over seconds or minutes or hours. And that is controlled more by the oscillator that's on the local system and is very much dependent on the quality of the oscillators and therefore dependent on how much money you're spending. I'm sorry, that was a okay, there we go. Sorry, for some reason it went backwards. So here is what a GPSDO does in one slide. Those of you who might be studying this, you now have a semester that you can take off because all that's happening in a GPS disciplined oscillator is that we are taking the performance of a local oscillator, typically a crystal of some sort, and using that in the short term for stability. But in the long term, using the GPS signal, in other words, we're locking the local crystal oscillator to the GPS. And on this chart, and I'm going to spend a second talking about how this chart should be read because it's used extensively in the time world. This is a chart of Allen deviation, which is sort of like like standard deviation, but for reasons that I barely comprehend and certainly cannot explain, standard deviation doesn't work well with the type of noise sources that we find, or the noise processes that we find in clocks. So Allen deviation is used instead, but it's very similar conceptually. The y-axis of this chart is the amount of wander or noise that we would expect to find in fractional frequency terms. So in other words, 1 in 10 to the 7th is 1 hertz at 10 megahertz. Or it would be 1 microsecond at 1 second. So it's a fractional representation of the carrier frequency. And lower is better. These are orders of magnitude apart. On the right-hand side, or the x-axis is the time. So what we're looking at on this chart is that if I take a sample every 10 seconds of the GPS signal, I would find noise of about 1 in 10 to the 9th, or about 1 nanosecond at a 1 hertz pulse per second signal. If I average at every 100 seconds, if I take a sample, I'm an order of magnitude better, because that's the way the noise in the GPS system works. That's essentially a straight line with a -1 slope down until we get into the low parts in 10 to the 13th or even lower. So what we're looking at here is how much noise I would expect to find on my signal. This is the GPS. This is a very low cost, temperature controlled or temperature compensated oscillator. This is a somewhat better oven controlled oscillator. And you can see that the GPS is quite noisy at short measurement intervals. And it keeps getting worse if we look further to the left, whereas the TCXO is pretty good and the OCXO is much better. Well, what I want to do in a GPSDO is have a control loop. It's typically a phase lock loop that has timing constants, so that I get this performance in the short term and this performance in the long term. And you can see from this that depending on the quality of the crystal oscillator, I have different time periods before that intercept point happens. So by choosing the crystal oscillator, and to a much more limited extent by choosing the GPS, I can design for different levels of minimum performance across any measurement time. That is the key challenge and what we need to understand. Here are several oscillators with typical short-term stability. And again, we're looking here 10 to the -8th at the top, 10 to the -14th at the very bottom. And going from, this is actually a current HPSDR, the Hermes system, the Tapper and the Open HPSDR group designed several years ago with no special oscillator design at all. This is that TCXO again. This is an inexpensive oven controlled oscillator. This is a rubidium oscillator, which is a different type. It's an atomic oscillator that is sometimes used. And this is an extremely good crystal oscillator. In fact, this crystal oscillator is so good that the only thing I can compare it against is a hydrogen maser. So you'll see there's a huge performance difference here. These are orders of magnitude. And unfortunately, the price is almost at that rate. This is about a $5 or so component. If you want this, it's about $15,000 and you have to wait 6 months to get one. So depending on your budget, we have very different criteria.
5 minutes, John.
Okay, thank you. This is the receiver performance of a number of u-blox GPS modules. And there's basically about half an order of magnitude difference with a price difference. The cheapest one is about $25 in quantity. The best one is about $150 to $175. So there is some difference in performance here. It's not huge, but we have a decision to make in that regard as well. In additional performance criteria, which frankly are easier to deal with, are the phase noise, which again is the modulation that's imparted onto essentially the local oscillator. And in the Tangerine, that's really dominated by the 122.88 source. And there are realistic targets that we can achieve for about the same amount of money. We can't go much cheaper and have a system that works. That's about minus 100 to minus 115 decibels reference to the carrier at an offset of 100 hertz, and about a noise floor in the minus 145 to minus 160 range. There's not a huge difference in price between the better and worse points, but there are differences in capabilities, and we'll need to make some decisions about what is the minimum phase noise that's required. But that's a much simpler issue than the frequency stability issue. And finally, there's a time module, I'm sorry, there's timestamp performance. And again, we have accuracy, which is when our clock ticks, how accurate is it compared to the US Naval Observatory. And with these low-cost GPS modules, it's extremely easy to get 100 nanoseconds of accuracy. To get 10 nanoseconds is difficult with consumer grade equipment, but with good user care, which involves measuring cable lengths and delays and possibly some temperature control, 10 nanoseconds of absolute accuracy is achievable. Better than that is frankly not practical. In order to achieve those levels, you need to use satellite time transfer or fiber optics and temperature controlled antennas and lots of other things. So really, I think we can assume that the 10 to 100 nanosecond range will be able to achieve in the Tangerine, with most of that difference being dependent on the care with which the system is set up. Now, the raw the timestamp, how much noise there is on that pulse per second signal, depending on the receiver you use, there's about 4 to 20 nanoseconds of peak-to-peak noise that we'll see on that signal. So that may or may not be sufficient for the timestamp that gets put on the data. And there could be occasional excursions that are 10 times that much. But if we use a pulse per second signal that's smoothed from the GPS disciplined oscillator, that we can get well below 4 nanoseconds, which is getting into the amount of time that it takes a logic gate to switch. So we should be able to achieve pulse per second stability in the handful of nanoseconds range for use in the time stamping. To the extent that I have time left, these are a few more pictures of the relative performance of the GPSs that I thought you might find interesting. First, this is a zoom in of the jitter on several of the receivers, and it's probably a little bit hard to read, but these are different generations of the U-Blocks receivers, and you can see that there is a range from this green probably being the noisiest, which is also the cheapest receiver, to this red, actually this red is one of the an interesting units that's more expensive than some of the others, but it has a much lower jitter level. And you can see in ranges in between. You'll also see that some of these are very much a straight line. The GPS itself has some temperature compensation to keep it more accurate, where others, like this purple line, you can sense there's a frequency cycling trend, a bit of a sine wave going on here. I don't know quite what it's from, but that's because of the lower quality oscillator in the GPS unit. Now, there's an interesting aspect to the modern GPSs. They will tell you in advance what some of the noise characteristics of the next pulse per second signal will be. And if you use that correction information, you can get better short-term performance. And this is an example of the same receiver module. The red line that's got the straight slope is the GPS running by itself. This one is from a CNS systems clock that uses a hardware system to correct for that noise that the GPS is telling it is coming. And you can see that out even to 100 seconds, that is providing better performance. And we can use that correction in our design as well. So the plot that I showed you earlier is actually a little bit less than we'll be able to obtain. We can get some amount of improvement like this simply by using the and again, here's a difference in the yep in the GPS timing between that smooth version and the raw, and that's it. So I will unshare, Nathaniel, and hand it back. Thank you.
Great. Thank you very much, John. I really appreciate it. As a reminder to all participants, there is a link to a Google Drive doc that you can go and you can ask questions in, and we'll ask the presenters to also go in there and answer the questions. Please write your name down when you are either answering or asking a question so we know who asked. All right.
Okay, one last thing. Yes. I will be posting a much updated version of this presentation to the shared site to replace the one that's currently there.
Wonderful. Thank you very much, John. I really appreciate it. Excellent presentation. Okay, and now we have David Witten, Frankie Bonte, and Hyomin Kim with magnetometer support for the Personal Space Weather Station and related projects. Are you there, David?
Yes, I'm here. I believe that Hyomin was going to lead off with some introductory slides, if he's there.
Nathaniel, isn't Bill going to go first?
Oh, I'm sorry. Yes, I skipped one. So we're actually going to Bill Engelke. Tangerine, I'm sorry about that, David. Bill, Tangerine SDR Database and Control System Architecture from Bill Engelke at the University of Alabama. Bill's AB4EJ.
Yeah, I was just getting ready to go look at the agenda, thinking maybe something had changed. Is the audio coming through okay?
It sounds great, Bill.
How about the screen? Can you see my front panel?
No, I just see it says Bill Engelke.
But you should be. I'm sharing my screen. Let me try it again. Share screen. Okay, how about that?
Coming up in a moment. There you go.
Perfect.
All right. Thanks, Nathaniel. This is Bill Engelke, AB4EJ with the University of Alabama. And we're going to talk about the Tangerine SDR database and control system architecture. The point is, I want to get across what will the Personal Space Weather Station network be. To build up to that, we have to talk a little bit how the system is architected and designed and how the Tangerine SDR will work within this network. And that's kind of in the reverse order I'm going to be talking about it. I'm going to say a few things about the Tangerine's design and how it is relevant to how you use it within a network. So our goals here for the network itself is to build a network of receivers that can observe the ionosphere by watching Doppler shift and WWV and other stable signals. There are plenty of other things you can do with this as phase one of a multi-phase project. So we got to walk before we run. At the same time, we want to give hams a way to closely monitor propagation at their own stations. The idea here is we would like hams to be interested in this system even apart from the scientific objectives. And so maybe folks would like to get some real good propagation information at their own site and at the same time help out the scientific community by providing data. This is the network of receivers is very similar. If you're familiar with SatNogs, that's a crowdsourced system for observing telemetry of things like CubeSats that are not monitored by any nation state. So the only way you get 24-hour-a-day information on what your CubeSat is doing is by using the SatNogs network. Our idea here is to do something quite similar to that for the Personal Space Weather Station network. So what will this network be? Well, we've got a group of universities and research facilities. You've already seen all their logos. What we hope to do is have several hundred and maybe thousands of inexpensive software-defined radios. And when I say inexpensive software-defined radios, I'm also including these Tangerine SDR in that, because you can buy software-defined radios that cost up to any arbitrary amount. But this basically the two major systems that we're designing: the Case Western Reserve system and the Tangerine. So the idea is we expect to have these in ham shacks, but also at institutions, schools, universities, any research institutes that are interested in supporting the work. So each one of these, the Tangerine SDR includes a single board computer. Now, it doesn't necessarily have to be a single board computer. We're architecting the software that runs on that system to run in Linux. So hopefully any box that runs Linux should be able to act as a control system within a Tangerine. Obviously, if you want to connect the low speed Pi hat kind of things, it has to be something compatible with that. So the idea is we want to get data analysis for science objectives plus a personal propagation monitor for each user. Here's a top level view. The station locations here are just examples. The emphasis is on North America, but users in other locations are also welcome. If we're going to focus in phase one on what's happening in WWV, we obviously have to focus more on North America than anywhere else. And again, this is a phase one thing. We foresee that this could be rolled out in other parts of the world, and everybody has their own set of stable signals that they could observe. Phase one, we'll put the database at the University of Alabama. That's also a cost decision. As I've joked, only semi-jokingly, we have quite a server farm. Our friends in IT found out that Auburn University had a little bit bigger data system than we did. So we had to put in a bigger server farm so that our system can be just some few percentage larger than what they have at Auburn. And so they have some excess server capacity that they make available at very reasonable cost. And so we will be able to use that. And I'll talk a little bit more about how we're going to deal with that in a minute. So let's talk of the personal space weather station network. On the left, you see the Tangerine SDR, which includes both the data engine that Scotty has talked about and the local host. That's what I call the single board computer. For example, Odroid N2. There's more than one way to design that. You could also use various levels of Raspberry Pi, although if you take a look at the kind of speeds that the data engine will be providing, especially when monitoring more than one channel at a time, you can quickly swamp some of the really cheap devices. So I've been doing all my testing with an Odroid N2, which is fairly powerful. There are other comparable ones. One or more local sensors, a magnetometer you see here, and this would be at your location. And it'd be connected through the internet to the space weather network. What we define as there will be a control system. I'll talk about how you use that in a few minutes, and a database. And we expect to make clones of this database at multiple sites. We'll initially build this up at University of Alabama with the idea that it can be replicated in other locations with a minimum of mirroring the database in at least one other location. So in case we have a problem with something at UA, the database will not just go dark on us. So what is in the Tangerine SDR? That's been talked about quite a bit, so I'm not going to spend a whole lot of time talking about it. But the idea is you have a couple of ports, antennas that you can monitor, and that's connected to this single board computer via Ethernet, gigabit Ethernet, using a GPSDO clock and a magnetometer. Again, there's more than one ways to connect these up. This is just for illustration purposes. And that is what your Tangerine is. That's what you'll have at your local station. As far as the software that runs on the single board computer, there is this dotted line here indicates the content of what's running on the single board computer. There's a couple of parts to it. There's something called main control. That's something written in C. It uses the asynchronous package libuv, in case you're familiar with that. It handles commands from a local web server. Well, I'll talk about that in a minute. It also handles a high-speed data feed from the data engine. The data comes via UDP. We're not using TCP due to the overhead of it. The plan is that it will save data in the digital RF format. There's several different formats. I'll talk about that in a moment. Our idea is we want the thing to be able to decode FT8 and whisper signals and manage uploads to the central control system and also interface to GNU radio. There will be a browser-based system. The idea is we don't want you to necessarily have to be some kind of world-class expert to use this thing. We want it to be able to get set up and used via a web front end that's fairly user-friendly, so that in schools where you don't necessarily have a high-end IT staff, they'll be able to get this thing up and running and use it. So this web-based system is using Flask and Flask WT forms for any nerds and geeks in the audience. Just certainly. So as far as data collection, our idea, and this is aspirational, whether we actually end up achieving this is still to be determined. We want to be able to monitor up to 16 band segments at a time, and hopefully maybe more. We envision 4 different types of data collection. Let me talk through those. First, what I call a snapshotter. That is a once per second waterfall snapshot of the FFT, that is the spectral content of one of the channels, that you take a look at that once per second. That is good if you have low internet bandwidth. We know that a lot of home users especially, they're very limited on how fast a data rate they can upload. So if you have that situation, the snapshotter is what you would probably use for data collection. Second item is what we call ring buffer. That is continuous local storage for 24 hours. That stores the data in digital RF format and uses the digital RF ring buffer function so that it deletes anything older than 24 hours when new data comes in. And then the capability to upload based on a request from central control to upload a time frame of that, like give me from this time of day to that time of the day, not necessarily the entire thing, because that would take an awful long time to upload. Third type of data collection we envision is what I call fire hose. This is for places that have a local supercomputer or local server farm right on the same local area network with everything hooked up with gigabit. That is just the entire content of whatever channels you ask for, just spooled directly out to wherever. And that, by the way, I should mention, the central control database does not play a role in this. Finally, propagation monitoring. This is once per minute decode of, I shouldn't say JT8, FT8 and whisper on up to 8 bands. This is quite similar if you're familiar with the similar functionality on the Red Pitaya using the Pavel Demon software. It works very much like that, in that once a minute, it does a decode of whatever channels you have configured, and it gives you a list of what things it's heard and in terms of spots. So what stations have I heard? That allows you to determine their location, and from that you can determine propagation.
Okay, 4 minutes.
4 minutes?
Yeah, so we're going to try and get into questions.
Yeah, so handling of collected data, it goes through local storage on request and gets uploaded. Snapshotter, local storage, goes through GNU radio. That's how we do the FFT, and then upload from there. Local propagation is decoded and local display and storage, and then upload spots to PSK Reporter and WhisperNet. That doesn't go to the central data system. And then finally, Firehose just goes to a local supercomputer. There's not very much more to talk about on this. The central control system is, that's going to be a CentOS-based system which has a web front end and database management. We're using Django, Celery, RabbitMQ, and MariaDB, again, for the real geeks in the crowd. How you'll use it. You'll build your dream. You use a browser to connect to the central control system and sign up for an account. The account will allow you to get a security token from Central. You paste that into the Tangerine web interface that will identify your Tangerine to Central. Again, we've stood on the shoulders of giants here. This is very similar to the way the SatNogs network works. Then you start collecting data. And you can also at the same time do local propagation analysis at the same time. Data analysis, Tangerine SDRs collecting data using Snapshotter or Ring Buffer. The central system will request data, which then gets uploaded. We save data in a database for analysis. Spectrum data will be stored in digital RF format. Science users will be able to run analyses and download. Anyone will be able to download data. It's going to be all open source and open data. And you'll be able to get local propagation reports by FT8 and Whisper. Why would anybody want to do this? You get a chance to be part of new science, compete for wallpaper like SatNogs. Everybody gets a kick out of seeing how high they can get their station up in the rankings of how much data has been uploaded. And you also get a chance to see an ongoing snapshot and ongoing trend information on what propagation looks like at your location. So let's take a look at the front end as it is so far. I will, well, submit questions via the chat window. I'm going to hop out of this and show you the front end. This is what I have so far. I have built a simulator for the data engine that I talk to through a gigabit Ethernet switch. It's all laid out on my workbench here, and running on the Odroid is a system like this. It gives you this front end. You go in, you tell it to make its connection. It'll crank for a minute, and then this is basically restarting the main control program and reestablishing communications with the data engine. It tells you we're up and running. Some of the configurations you're able to do, you can go in and set up various components, put your token in here, set up the data engine, pick up what frequencies you want to monitor the channel, turn the channels on and off, pick which antenna port, center frequency, and bandwidth each channel is going to have. Set up throttling of upload data. And this is something that's a particular favorite of mine, where you can put in a bunch of call signs that you want to monitor. And when these call signs happen to occur where your system picks them up, they have occurred in Whisper or FT8, you can get a notification. And then you can get an email. And if you happen to have one of those email services that can send text messages, the idea here is when a certain station you're watching for is heard at your station, you get a text message about it. So you can kind of watch for that DX station to occur at your station to be heard, and don't necessarily have to sit at the radio. So as soon as you get that text message, you rush to the radio and try and work them. So that's one of the fun things that we envision. You could also set this up to monitor D-Star, but that's probably not as interesting for most people. And so I think I've raced through that. One final thing, I've got this running here. This is using simulated data. It's data collected some time ago, but it's decoding FT8 spots. And here it shows the number of spots at each frequency band we're monitoring. I would probably do this graphically. I just got this working the other day, just output it by text. So We see we got in the last minute 50 spots on 7 megahertz, 34 spots on 10, 71 on 20, etc. So you can observe which bands are open and how much they have been in the last minute. I anticipate we can also, look at the last 15 minutes, the last hour, various things like that, kind of analytics. So because we are short on time, I'm not going to go into a whole lot more detail on that. But all right, so this kind of covers the objectives that I had. And Nathaniel, you wanted me to leave some time open for questions.
Yeah, I think we're actually out of time, so we are over time. So I'll have to go right to the next presentation. Again, people, please put your questions in the Google Doc, and then the presenters, please answer the questions. So next up, we have 3 people: Hyomin Kim from NJIT, David Witten from Tapper, and Frankie Bonte. She's a high school student from DeSales High School in Ohio. So I think Hyomin's going to start off the presentation. Is that right?
Hi, good morning. This is Hyomin Kim, assistant professor of NJIT. So we're going to talk about development of magnetometer, which mainly led by David Witten, who is online. So I'll be talking briefly about what the goal of our magnetometer project is, and then Dave will run the rest of the session, and Frankie will show some of her work that she did. So if you, Dave, can you share your presentation slide, because you will be the driver for the most of the presentation. So. Or
yes. Hello, can you see this?
Yes. Okay.
All right. Well, this is just a short, oh, no, this is the wrong one. Pardon me. What we've been working on is magnetometer support for the personal space weather station and other related projects. We have myself, Frankie Bonte at DeSales, and Dr. Kim is acting as the overall advisor. We have specific goals to establish a densely spaced magnetic field sensor network to observe Earth's magnetic field variations in 3 vector components. The target performance level is set at around 10 nanotesla field resolution at 1 second sample rate. And by way of example, the Earth's magnetic field ranges from 25,000 to 65,000 nanotesla. So you can see that we're going for quite a level of sensitivity. The time varying field measurement is sufficient. Absolute measurement is not necessary. As far as the physical magnetometer support board and extender that I've been working on, the specific purpose is to support the personal space weather station. There is a smaller version of this that doesn't have the extender component, that's less expensive and simpler to work with, and it's also prototypes exist of that as well, and it's easy to attach to a Raspberry Pi or Arduino or something for other kinds of projects, perhaps school projects. The sensors used in either case is the PNI RM3100 module. We're using it as the module at this point. At some point, we may switch to having it manufactured with those module components directly on the PC board. It includes a microchip MCP 9808 temperature sensor for calibration and characterization purposes. The interfaces that we're using for this purpose, we're not using the SPI interface, we're using the I2C communications available from these components and polling them at about 1 second intervals. The remote extension is quite clever. This is credit goes to Tom McDermott and 0AX for this. We're able to use I2C over a shielded Cat6 cable to extend this away from any other interfering documents, seemingly at up to 100 feet, 30 meters, whatever, or more. We have not totally tested this, but it appears to work well. And for the full personal space weather station, 2 boards are used with 1 magnetometer module and a shielded cable to make the extension. So we've designed this in such a way that 1 board connects directly to the data engine or whatever other device you wish to hook it to by I2C, and 2 boards, and the other board actually has the magnetometer module and set in a remote mode and placed physically away from the other equipment. These are early 3D mock-ups of the boards. They don't show some of the headers that support the magnetometer, but they give you a general sense of what the current state is on this bit. There's several connectors on here. There's a PMOD connector for directly attaching to the data engine. There's there are 2 of they're JST SH connectors that are, they're not populated in this view, but they are similar to the SparkFun Quick or the Adafruit, they've got some name for it, Stemma QT, I think. And there's a Grove type connector on here too. So it's easily attached to other types of projects besides the full-blown personal space weather station. We're doing this in hope that people will find other uses for this beyond the direct, our obvious intention. The magnetometer module itself, as we're using it, is a 3-axis magneto-inductive measurement module. It's very low cost. Even fully built up modules are about 20 or less than $20. And so that should allow us widespread deployment. They're physically very small. They're essentially 1 inch square by 8 millimeters high, and much smaller than most other sensor types that we have access to. They're high sensitivity. The manufacturer claims 13 nanotesla with the default settings. We hope to tune that perhaps even better. I'm sure that is dependent on the setting, but it gets us into this right ballpark, and nothing else does at this cost. The board itself supports native I2C or SPI interfaces, but in this case, we're only using I2C. This is actually a setup that I've been using for electrical testing, or making sure that the basic functionality is working, not for evaluation of function. But and this shows an Odroid N2 with a SparkFun P hat to expose the quick interfaces. This has also been tried with a Raspberry Pi and an NVIDIA Xavier, and probably a Nano as well. I haven't really worked on the Nano much, but so it works with a variety of boards, single board computers. The extender function, this is probably the most interesting bit, at least creative bit. The I2C bus was created to provide a very short range, less than a half meter serial communication between boards in a chassis, and was not designed for high speeds or long lengths or high degree of noise immunity. The PSWS and similar projects need to be able to separate these things. NXP makes a PCA 9615 chip that converts I2C, the standard single-ended I2C signals, into differential signaling, and allows the use of an independent voltage for the link. So it makes a differential link, and we're using the differential link at 5 volts across two wires in the cable to give enough headroom to power the remote board without having to have a power supply out in the weather. And then NXP calls this an I2C to D-I2C converter, and we convert to differential for the extension, convert back to standard I2C at the remote. There is potential within the limits of the headroom, which haven't been determined, to attach other very low power draw components at either the local or the remote end of this bus, but always within the limits of the available power. This shows specifically the I2C extender chip. This thing's a pain to solder. It's about the limit of what you can do by hand. And I throw away a couple chips for every one I get right. But so ultimately this will go to automated manufacturing, and hopefully this will be better. The temperature sensor is a simple but fairly high accuracy sensor that will give us information about the operating environment. The one on the local end will tell us the operating environment of the data engine and other components. The one at the remote end will tell us about the operating environment of the magnetometer itself. It appears on the same I2C bus and requires no additional circuitry, so this was very simple to implement. And here's the location.
5 minutes.
Okay. There's more needs to be done with software driver development and more evaluation under realistic conditions. Had some references to the pages. And that's the extent of my presentation. See, how do I unshare? Then I wanted to give some time, if she's available, to Frankie Bonte. She and also her father have been working on some characterization of this, and I'd like, if they're available, perhaps they can give us some information on what they've been up to.
Yes, thank you so much, Dave. As he introduced me, I'm Frankie Bonte, KE8 HPA. Can everybody hear me? Can you hear me all right?
Yep, you sound great.
All right, perfect. Thank you. Okay, so I kind of wanted to talk a little bit about the data that we've been able to collect. So first of all, we wanted to start out making sure that we were able to get data before, even correctly orienting the setup. So I'd like to show the setup that we have. If you can see this. So over here, we have our the kind of setup that we have in the beginning. So as you can see, there's the real-time clock and then the SD card. And over here we have the magnetometer support board that was provided by Dave. So thank you so much for that. And so first of all, so in order to get data to the computer, we would have to take the SD card out to put it into the computer or use a serial connection. But so I'd like to show you some of the data that we've been able to collect. So on the computer here, here's each line of data, and each line of data has the real time and date. Oh, the computer turned off. I apologize for that. Okay, so here we have the real time and date, and then we have temperature in degrees Celsius that we got from the temperature sensor, and then XYZ readings in microteslas. And this is all in the CSV format, so it can easily be put into a spreadsheet later on. So that's just the data that we were able to collect before actually putting it out into like a test field. But we were able to make this box that we hope that the magnetometer would go in the future. So it has, so it's waterproof, the connection, there's a cable for it to go out, and we placed it on a concrete block so that whenever we set it outside, we will be able to face it north and level and plummet to get the best data from the magnetometer, and it'll be in a fixed position outside. However, because the data that we're getting, it has to have a serial connection directly to the magnetometer, our kind of next steps in the future will be to get the magnetometer placed in the box in a set position, and then also to be able to have the system communicate directly to the internet so that we can share our data with other people without having to have the serial connection or use the SD card to take it out and put that information in the computer. And also that will be super helpful to show that this is the data from our position, and then we'll be able to share it with other people around the world over the internet. So that's kind of the setup that we have over here, and hopefully in the future we will be able to get that connection and get the magnetometer set up outside. I'd just like to thank Dr. Kim and Dave for including my dad and I on this project. So thank you so much.
That's great. Yeah, thank you very much for the demo, and really great to see all your setups, including your HamSCI mug, which we're talking about right now. How exciting to see the HamSCI mug. So yeah, my concluding remarks, since we are running out of time, but my concluding remark from my side is that so magnetometer can vary in terms of price from say a couple of dollars to, easily like, hundreds of $1,000s. So instead of having a really fancy, high quality magnetometer at some point in one point, our proposal is to distribute very inexpensive, very easy to use magnetometer all the places to see how the magnetosphere ionosphere coupling system responds to the space weather system. So that's the goal. So that's why we want to go route to this type of like really inexpensive magnetometer. So it's great that high school students and other amateur ham radio scientists are involved to establish like really largely spaced, densely spaced magnetometer network. So that's the goal. So back to Nathaniel.
All right, thank you so much, Hyomin. Thank you to Hyomin. Thank you very much, Frankie, and thank you, David Witten. It's a great presentation. And I did get to see the magnetometer in person when I went to Orlando Hamcation this year. And so it's nice to see actual hardware coming out of the project. And it's nice to see it get into the hands of people like Frankie and her father to actually see them testing it and trying it out. So it's very good. Okay, we are now on to our first break. So we'll be back here at noon. During the breaks, I am going to leave the webinar open, and we have moderators. So now David Larson and Gareth Perry are going to be the moderators for this break and for the next session. And so you are free to ask questions and talk on the chat if you like, or go get coffee and do what you need to do. So we will be back with the formal part of the workshop in about 20 minutes.
Any virtual cookie or something?
Let's see, I have some European cookies right here. Yeah, we'll have to work on that. You'll have to go check your own kitchen. So I'll be back in a few minutes. And yeah, please feel free to talk, ask questions. We should point out that, don't forget, look at the Google document that's online. You can ask your questions there. Presenters can answer their questions there. Also, David Larson wanted me to point out that we do look for more helpers on this project. So if you want to volunteer and you're not already volunteering, if you want to help out on if you go to HamSCI.org and you go to the personal space weather station link, there's all information on getting involved. You want to join the Tangerine SDR project if you're interested in the engineering. So this is the Tapper side of the project. If you want to join HamSCI, you can click the Get Involved tab up here. And we have a Google group. We have science telecons every other week that last about an hour. So there's all sorts of information here. All right, have a great break, everybody. Thank you.
So I have a question for Frankie. The box that I think you must have 3D printed that box, right?
No, we just bought a box, and then we were able to screw it into a concrete block that we also bought for not that expensively. And then we kind of saw how the magnetometer was going to fit inside of the box, and then we're able to drill a hole just to see where the cable would come out of. But in the future, we were kind of hoping that we could try 3D printing a box. And even like putting like a sticker on it or something that would show you where north was, and something like that, so that it could be more like if you ever needed to move oriented.
Okay, I was just curious as to whether the box was big enough for the carrier board that Dave has made, because those two boards, one can be strapped as a remote, so you could actually strap the one as a remote if it's inside your box and put it like out in the yard, and then the other end would connect to either a Raspberry Pi or to the data engine. And assuming that the box was big enough, because I think Dave's board is kind of, I mean, it's about 2 inches by 4 inches, and it was hard to say how big your box was there in that picture.
No, we have the smaller magnetometer support board, but I do believe that the box is a 4x4 box. But we also have like a smaller magnetometer support board, so that would be the only thing that would go inside the box.
Okay, so Dave's larger board then doesn't fit inside that box?
I don't think so. I'm not sure.
Okay.
Scotty, yeah, if you can hear me, I believe it would fit in that box. That's a standard electrical box. I'm pretty sure it would fit in there. But
she says it's 4x4. How wide is the magnetometer? Before the carrier board.
It's the full blown board is about, I think it's 2.3 inches long or so thereabout, and it's a little 1 point something wide. It's smaller than the ones you've seen.
Okay, and that has the remote the I2C extender chips on it too.
Yes, it does. Although not the one that Frankie has at the moment, but the ones that are similar to the ones that I gave you.
So you could actually send her one of those boards that would fit in her box brick combination, and then could be placed outside to gather real data from out in the yard somewhere.
Yeah, that was the hope. Yeah.
Dave, this
cool.
is KV0S.
Go ahead, Dave.
It would help, Dave, if you could show your 3-minute video.
Okay, yeah, I can do that if anybody would like.
Scotty would really appreciate it because it shows your working system.
Oh yeah, I haven't seen it before.
Okay.
It was
yes.
supposed to be at the end of the talk, but they ran out of time.
Dave helped me with this. I've got to give him credit. It's been a big help.
Progress and demonstration.
Wait a minute. Let's see.
Share the screen.
Yeah, I have to share. Just a second. Just a second. Things move around. Share again here. And let's see.
Now just play it.
Now play it.
Progress and demonstration. Dave Whitten, KD0EAG, and Holman Kim, KD2 MCR. This is the PMI magnetometer board, a commercial product. It reads and writes SPI and I²C. The magnetometer carrier board, which connects to this commercial product. You will note that there are two of these. One has a PMI board attached and one does not. That determines which is the ends. The system is one PMI board, two carrier boards, 100 foot of Cat5 shielded coax, and an N2 board. The local end is as shown in the next frame. It's an Odroid N2 with a P hat on top to allow I²C connections. Also, there's a 5-volt connector. And this goes to the local board, which has no PMI, but connected to the Cat5. The remote end is the same carrier board, but with a PMI board attached, and it will return a remote temperature and the magnetometer readings. Now we're going to run the commands for this actual project. Where first we do the I²C detect utility. Here we get 18, 19, and 20. 18 is a temperature sensor, 19 is a temperature sensor, and 20 is the magnetometer. And these are the raw, raw values.
So that showed what's running in Dave's house.
So, Dave, is it possible for you to build another one so that I can fiddle with it, or something that?
Just a moment. I'm trying to. Oh, there. No. Where is
You're
my?
You're showing your email email, Dave.
I always have trouble. Yes, I have trouble undoing, unsharing my sessions, but or getting back to where I want to be. But in any case, Hyomin, I already have a pair made for you, and I anticipate sending them to you in the next day or two. I assume that address that's in the footer of your emails is suitable for that. But I'll be sending those off to you. I have.
Please ask me when you are ready to ship, because right now the school is sort of, closed. So we're not supposed to be present on campus. So maybe you have to use my home address so I can.
That's fine. I'll email you before I do anything. Won't go out till Monday, I don't think.
Yeah. No rush.
But,
Dave, do you have a board for Frankie also?
Well, no, not quite yet. I'm working on another set. These are a pain to make work.
Just that she has an enclosure all ready to go, so it would be interesting to have it actually set up out in the yard somewhere and read data remotely.
For my purposes, I was planning to use a piece of, I think it's 1 1/4 inch PVC plumbing pipe that this board fits in quite nicely. I just have to make sure there's a way to level it and know exactly what the orientation in the Y and Z, or especially the Y dimension, because the pipe is round, so I have to be able to mark it and hold it still. But that works well too, and you can get nice caps to go on either end. The PVC pipes, and you can get good glue to seal them. You have a reasonable sense of knowing that it works because it's what you use in your plumbing. But
I like her idea of gluing it to a brick so that you can get some stability and actually orient it in all 3 axes.
A lot to be said for that. So all of that's, the one thing is we have this hardware in limited prototype right now, and it's physically doing what it's doing. So we're at the point where we can really measure what it will do for us. I'm pleased to be there at this point.
So when do you think you'd be ready to actually do a production version of it? Because we could get our layout guy on that and do a real board that we could make in quantity, and we'd get it assembled so you wouldn't have to kill yourself trying to solder those small pins.
Well, there's one minor modification I think you and I have discussed that would need to be added, but beyond that, I'm pretty much ready to do that. I want to get it to some assembly. I haven't established any relationship with any assembly.
Yeah. So I'm sure we could take care of that once you get to the point where you're ready and you have everything working and you're confident that you know exactly how it needs to be connected because you got one working. It sounds like you're there now.
Yeah. Can your guy work with my KiCad document? My KiCad.
Either that, or I can redraw it in ArcCAD, whichever. Can you generate a PADS net list from KiCad?
No, unfortunately, I don't think I can. I thought at one point I could, but I couldn't.
Well, then I can redraw the thing in probably a couple hours at the most because it's very straightforward. I mean, you laid it out pretty nice, so it should be easy to copy.
This is pretty trivial compared to the stuff you and Tom are doing. So,
hey, that's the trivial ones are the ones that get you though.
Well,
you don't watch it.
Scotty, this is Dave. I wanted to mention I've seen it. It's running 100 feet across the basement of Dave's house, and the only reason he hasn't put it outside is he doesn't have a container yet. But it's working. It's been running for a couple weeks.
Well, Frankie will 3D print you a box and glue it to a brick for you, right, Frankie?
Yeah. Well, and the other thing is this has not been calibrated, so we don't really know what the exact values of the numbers are.
Yeah. So the question then is if we think that the hardware might have to change because of that, then we really don't want to build 100 of them. But if we really think the hardware is the way it's going to be and it's only a software calibration, then I mean, once you get the electrical part so that it works, so that it reads the data, then you're done.
Yes. So also what we found is that it was able to work best on the Arduino, the magnetometer support board running on the Arduino, because some of the data was a little bit, when we looked at on the computer, it was a little bit giving us weird numbers. But when we used the Arduino, it was able to give us more like numbers that when we looked at it, we're like, okay, that seems like they're more accurate. Although we haven't correctly, really like exactly oriented the support board, we've been able to kind of like move when we move the magnetometer and see how it changes the readings. That was, yeah. So it was working best off of the Arduino.
But you're still reading the board from inside your house, right? So that may be where the variability is coming from.
Exactly. And even when we were in like the very first stages of like seeing it, even when the like when it was close to different things, like that was really affecting it because the cable was really close to like the computer and like the lights and stuff like that. So it was giving us.
Yeah. That's why I was kind of interested in getting it put in a box and outside in the yard somewhere away from fluorescent lights and computers and cables and things like that. Because that's really, I think, where it's going to have to be used.
Yeah. And well, the first thing that we were going to try to do before we thought that it would be good to put it in the yard is to be able to get that data sent remotely without having to have that serial connection. Because some of it just seemed like it was coming too fast for the like kind of the system to be able to like translate and like show the data.
So are you able to, when you connect it to the Arduino, are you able to send the data to the network?
It's just being read off of the program, I believe. It's not over the internet yet.
Right, but you read it from the I2C port of the magnetometer into the Arduino. But then what your goal is to have it accessible over the internet so that anybody can see your data.
Exactly. But we've been able to get it in the format where it will have a lot of the necessary pieces like the real time, the temperature, and the readings. And it's also in the format that would be really easy to put onto like a spreadsheet or something like that. So then it can be, so the goal is to get it over the internet.
Okay, so just a little bit of software is needed to go in between maybe run on the Arduino.
But
is that right, Dave?
The video that Dave and I put together, he's running a C program that gives equivalent output, and he found that you have to change the speeds of the I2C port, and so you basically, there's a set of commands that Dave figured out to change that on the Odroid, and that's what's probably the part that Frankie couldn't get to work right.
Okay, so
hey everybody, it's getting close to times here, so we're going to get ready for the next presentation, and that's going to be from Christina Collins and Case Western. Welcome back. I hope did you guys have a good break while I was gone?
Yeah, we did.
Yeah.
Great.
All the discussion continued while we were gone too.
I know. This is very good. Okay, I'm very glad to hear it. How are things going, Christine? Are you about ready?
Just about. I don't want to jinx anything by remarking on how well they're going, but it's going pretty well. Let me copy some links into the chat here that I think will be helpful for this presentation. And David and John are going to join me. I see that they are here, or at least David is. And Bella is here with David, Bella the cat. All right, all panelists and attendees should now be receiving these links. There we go. All right.
So next we have Christina Kasdan Christina Collins, who works with David Kasdan at Case Western Reserve University. And you also work with John Gibbons and a number of other people as well. So
yes,
we have
Andy Monteiro is also here for this session.
Okay, so now we're going to hear from Christina Kasdan and on the update to the
Christina-
low cost. I'm sorry, I have too many windows open and I'm looking at too many things.
We're going to tell you about the low cost version of the personal space weather station.
Take it away, Christina. You're welcome.
All right, so this was, I'm glad that somebody brought up earlier the prospect of using one's existing ham station to collect data, because that's going to be one of the things that we focus on here. We're going to talk a little bit about the approach that we've been taking. David's going to give you a little tour of the data collection that he has set up. I'm going to talk about our plans for the future, and then John's going to tell us a little bit about his recent software contribution to FL Digi. So here we have our little cartoon illustration of how we use WWV, which is the time standard station for the United States, has very precise carriers on 2.5 megahertz, 5, 10, I want to say 15 and 25. And we use the fact that as the virtual height of the ionosphere between it and our station changes, that frequency shifts to make a proxy measurement of what the ionosphere is doing at that point. So David, why don't you tell us a little bit about your station here?
The station that's doing the data collection now isn't anything special. This is a 30-year-old amateur radio transceiver, a Kenwood TS450. It is an old laptop repurposed as a Linux machine and not doing anything else. Old rig blaster. The antenna is similarly nothing special, just some wire going into the attic. Notice the frequency display on the dial, 4.999 megahertz. We're running this as a low IF system, so in that sense, it is an SDR radio. Slide. Yeah. The choice here, this is an old rig. They're available cheaply. It was among the first inexpensive rigs back in the day to use a direct digital synthesis chip. So it has frequency discipline from one point. As shipped, it was run with a quartz crystal. You don't need absolute accuracy for all of these measurements. You do need better than the quartz crystal, but it's easy to swap in a temperature compensated crystal. And actually, I put in a GPSDO, which has proved to have some interference on the signals that we want, but we will get that working. Slide. You'll see the computer, it's running FL Digi, which I will guess everyone here has seen. The graph that's being generated is 1 UTC day of Doppler shift. The Doppler shift here is the black line. It is filtered a bit. Christina will talk about that more. The red line is received signal strength. This is 1 UTC day, so sun up here in Ohio is about the middle of the screen. That's the sharp drop in received signal strength. But you notice the Doppler shift precedes that. I think the data are accurate. This is a 2.5 megahertz. This is the night before last UTC. And as you can see, the night was rather hectic, more so than most. There was quite a bit of Doppler shift overnight.
All right,
and
now
we need to talk about our collected data.
we will see if this video is able to play. If not, there is a link to the YouTube video. I recommend right-clicking it and looping it because it's only a couple of seconds, this animation. But if you can see what I see on my screen here, this is the collected stack of plots that David has taken since December of last year. You can see that that peak that happens just after sunrise in Cleveland, which is associated with the formation of the D layer, is sort of skating backwards as the day lengthens. This is the 5 megahertz data, which David, I believe, is being collected off of your wire in your attic. And the light blue line is unfiltered. The dark blue line is filtered. We have not tune the filter very carefully, but you can extract some lines from it that at least look like something. So it's a promising start for being able to use this as a data collection method. And then I'm going to show you one more for 2.5 megahertz. And you can see the same thing here. This one is collected with a proper antenna. This is only about a week's worth of data for about Case's spring break. Because it's with a better antenna, requires less filtering. David, anything to add on this one before we move to the next event?
There was a question what the lines represent. That's local sunrise, zenith, local sunset.
Yes.
The collection for 5 megahertz began at the winter solstice, so you can see the daylight separating. We're in Cleveland. Having daylight is really nice.
And something of a novelty. All right.
That is local to the receiver, correct?
Correct. That's local to the receiver. So everything is on the axis in UTC time. Once again, the left-hand side of the graph from our perspective here is the nighttime. And then during the daytime, you can see where there's all of that noise from the sun. All right, let us move on to talking about the software a bit. David?
The local software collects the data off FLDIGI's analysis module, which John has rewritten in some important ways. We have some Python code locally that does some statistics checking, does some error correction for file corruptions, which we have found to be important, and prepares the graphs. I'm sure most listeners here are familiar with Linux's timing daemon crontab. The Python code then is called at the beginning of each UTC day as the previous day's file has just been prepared by John's modifications. Slide.
All right. So that particular set of software is what's being used for our prototype right now. It will definitely be undergoing more modification as we standardize this more to try to get people to participate. So I want to talk to you a little bit about this this adventure that we had in October when radio station WWV celebrated its centennial. And we had a big party out there, a big special event station. That first link, WWV 100, has information about that whole event. And a whole bunch of us went out there, had a lovely time. One of the things that we did as part of that celebration, partly to showcase the utility that WWV would have as a tool for data collection, was we did this thing called the Festival of Frequency Measurement, where we had radio operators across the country during that UTC day that was the centennial take Doppler shift data more or less in the way that we're describing. Some had GPSDOs, some did not. Some people were able to post 24 hours of data and a little bit more. Some people missed an hour here or there. And there was some variety, but for the most part, the data that we got, we were able to get into a usable state, and we're working on analysis of that concurrently. Here's a photo of WWV. If you ever find yourself in Fort Collins, definitely go out there. It's a beautiful place. Here's all of the participants. So we had something like 50 people across the country. This was a very interesting exercise. One of the things that we learned from having everybody use FLDIGI was that there were some gaps in the way that FLDIGI recorded things, which will now be rectified by John's code and hopefully make it so that instead of this being something that we would do for a one-day event and then have to spend a bunch of time manually cleaning up that data, we'll be able to automate it. So what this showed us above all things was that a lot of people are very interested in contributing to a project like this and collecting data in this way. And although it's important to ham radio operators that whatever we ask them to do for the sake of science doesn't interfere with their operating, they're very happy to let us have some downtime on their transceivers. So what we'd like to do is we'd like to build a system, which we've been calling the Frequency Analysis Network, to facilitate that as something that people could do. If I could leave my Radio Shack after I've been operating and set my radio and my computer to automatically record Doppler shift data that would then go into this database. This falls into the work that we've been doing for the low-cost personal space weather station, where we have specific hardware. But the same process that we're using to get data from our hardware, we can also be using for hams to upload their own data, and thereby create a much larger general network at the same time. So this essentially, we've talked about a bit. And the data that I think we've seen from David's station, some of the other prototypes that we've been working on have been very promising, and we're looking forward to exploring that more. So I'd like to spend just a minute talking about fair data principles. For those people who have been going to the AGU meetings, I'm sure you've heard about this a lot, but since we've got a broad audience here and everybody's interested in citizen science, I think this is worth going over a little bit. So I think often when we think of scientific data collection, we think of this very linear process where you have something that you want to explore, and perhaps you have a volunteer effort, or you have some sensor system that you create, and you collect all of your data more or less all at once. Hopefully you collect all of the data that you need. Then you perform analysis on that data. Hopefully you perform the analysis correctly, and then you gain results which are hopefully interesting and which you then publish. And the fair data philosophy, which is about making sure that the data that you're collecting is maximally useful for future scientific work, adds in the notion of having a data repository. When we started collecting data for the Festival of Frequency Measurement, Dr. Frisell had everybody upload things to this repository called Zenodo. And at first I was like, that seems like overkill to give every data set its own DOI number and so forth for just a little one-day project like this. But then I realized DOI numbers are awesome. And having it so that every data set has one identifier that you can point back to is a very convenient thing. So when you switch over to putting data in this repository, rather than having it be sent directly to you in order to analyze, it changes the way that your data collection process works. Your data collection now becomes this asynchronous thing. It may occur with you involved, it may occur without you there. And you as the researcher are then mainly retrieving your data from the repository in order to perform your analysis on it. And then after you've analyzed it, you can publish your results back to the repository. And everything has persistent indicators, so that if you collect a bunch of data and there's some indicator pointing to that data, some persistent identifier, you can then use the same identifier to see all of that data plus all the data that's been collected by the same person in the same way since. So you can think of this as there's sort of two buttons, one for collect data and one for analyze data. And ideally, you'd like to be able to push the collect data button, then push the analyze data button, gain some interesting results, go and get a cup of coffee for 5 years, come back and repeat the process and see what else you might be able to learn from the new information. So in that time, your data collection systems may change. You may get more volunteers. You may change some of your methodologies. And obviously, you're probably going to change elements of what you want to do in your analysis. But keeping that uniform is a really helpful thing in order to save yourself hassle and be able to access these things again. And I really like the tenets of the FAIR principles because they provide a really good rubric for ensuring that you'll be able to do that. So that's sort of the philosophy that all of this is meant to be based around. So if you yourself are interested in collecting Doppler shift data in this way,
5 minutes.
Yeah, okay. A good way to start is to take a look at the instructions that Aidan prepared and that others here prepared for the Festival of Frequency Measurement, which tells you where to go in FL Digi, how to set your radio up. And again, kudos to John on his addition. For those who are interested in joining the network, or more pressingly, for those who are interested in helping us implement automated data upload to Zenodo, there's a link here for the interest survey. I also put that in the chat at the beginning of this presentation. So please get in touch with us and let us know if that's something that you'd be interested in taking on, because we could use a little software help. So, all right, with that, I'm going to hand it over to John for talking a little bit about his additions to FLDigi.
Okay, I'm going to try and share the screen here. No, that didn't work. Let's try this again. Where are you? There. Are you seeing my screen yet?
Yes, we are.
Okay. Do I need to do that?
We're at 4 minutes.
Okay. Does that help expand the screen? Okay. When we started working with FLDigi analysis program, we found some basic flaws that were really causing us to have some serious problems. And the biggest one is when you restart the analysis problem, you lose all of your data. And for what we were doing, this was not acceptable. Also, our platform is going to be a Raspberry Pi, and the analysis directory is in a hidden folder, which for most common people who don't understand hidden folders in Linux is non-intuitive, so I had to fix that. The other problem is it sticks it into one big file and it doesn't separate it day by day, and using a cron tab job that we tried to utilize to create and do this process for us did not work out well. Also, there was no date stamp in the data, and there was no method for putting metadata in the header of the file. So in my modifications, the first thing I did is if the program stops, when it restarts, it picks up where it left off and keeps adding to the data that was already there. I have the ability now to include a date in the CSV file name of the collected data. It also includes the date in the first line of the code, and that's enabled as an option, which I'll get into in a minute for the version I released for FLDigi. It also allowed us to include metadata on the first line of this data in the file for each file that's created every day. I use absolute time only, and the relative time was moved, and on the change of date, it starts a new file with the new date. So now when you invoke the FLDigi package when it's released, there will be a status line at the bottom showing what's going on, and the frequency accuracy of the written data is to 3 decimal places now instead of 2. And the first thing I do under the Pi is I create a directory in your root user directory called capital FLD analysis, and that's where all the data is stored. And if you do nothing there, it acts just like the way the FLDigi's analysis package works now. And this is a screenshot of when you run the program. You can see where'd it go? There it is, the FLDigi analysis. This gets created in your username root directory. So when you run the program, it creates this analysis file, but it tags the date on the end of each day's data into the CS file, into the header, in the name of the file. So this is what's included in the file now. The first line is the standard header file that's there. Then you have the requisite information going on in there. Now, the cute thing that I added is if you go into the FLDigi analysis directory and you type in touchinfo.txt, which creates a info.txt file of 0 length, the program looks for that, and what happens is it adds, when it starts up every day, it adds the date as a metadata line before the header that normally appears for the data analysis. And if you go in and stick something in that info.txt file, like for example, I have my QTH, the frequency standard, and my latitude, longitude, altitude, if I put that in info.txt, when you run the program now, it sticks that whole line in the beginning of each day's data, so you can now have metadata associated with that. And I have submitted these to W1HKL, who's the author of FLDigi. He has accepted the changes, and they're already in beta testing even as we speak. But for HamSCI, I created something a little bit different. I do not create an FLD analysis directory. I created WWV data directory, and I look for 3 files in there: the org name, frequency standard, and lat, log, altitude text files. In each of these files, I contain information about the organization name, which for me was, as you can see here, it's pretty self-explanatory. Frequency standard, this shows what kind of frequency standard you're using in your radio. And then latitude, longitude, altitude is pretty self-explanatory. So when you run the program on the version that we're using for HamSCI, it sticks it in the root directory and under the directory name www data. And you can see that the metadata file includes the date and then the 3 included files, and then the standard header file and the rest of the information. Now, if you do not include those 3 files, so I renamed so they weren't there and reran it again, it puts blank information into the metadata spots so we can spot that and know what's going on for the database down the road. And also, if it stopped and restarted, you can see here, I ran this for this morning till 4:20, and then I'm sorry?
Time.
Okay, this is my last slide. If you restart it, you see it restarts here, and then I restarted it again down here. So it just picks up where it left off and you don't lose your data. And in summary, it's coming to you when the next release of FLDigi comes out. Thank you very much.
Okay, thank you so much, John. Thank you, Christina, and thank you, David. Very good. Those are all excellent updates. The data is looking very nice. I really like how you can see the dusk or the terminator move with the Doppler shift data, and it's great that we got those updates put into the FLDigi tree. Okay, we need to move along. So next is going to be Skip Crilly, K7ETI from the Green Bank Observatory on Synchronized Multiple Radio Telescope Microwave SETI. Take it away, Skip.
Okay, can everybody hear me?
Yes.
Great.
And I can see your screen too.
Okay, great. From beginning. Okay, thanks everybody. Yeah, I'm Skip Curley. I work as a volunteer at the Green Bank Observatory for about 5 years, and I work on maintaining the 40-foot telescope there. So we've been doing a very fun project since 2017 in the search for extraterrestrial intelligence. The idea is that individual radio telescopes are very sensitive to radio frequency interference. And so we've decided to put together this system of multiple telescopes where we put separate receivers at each location and run them independently. We don't communicate with each other. And we look over a band of frequencies from 1395 to 1455 megahertz approximately, with 3.7 hertz channels. And the idea is to look for signals that are arriving on multiple telescopes, 2 or more at the same time on the same frequency. The telescopes are a 60-foot dish in Haswell, Colorado, southeastern Colorado. It's an excellent low RFI site. And that's run by Steve Plock, KL7IZW. I drive to Green Bank, where I work, on the 40-foot telescope, and I install my computer, receiver, and digitizer on that telescope and run that for a week. Now, I keep the New Hampshire telescope running while I'm down there for a week, start it up before I leave, and then I come back. And then I post-process the files. So the idea is these files are independent, and they store signals that are above a signal-to-noise ratio threshold. And communication signals could potentially be sought out in post-processing, given that there might be signals that are on a very close frequency to each telescope. So this is what it looks like. Yes.
You have a little bit of popping on your microphone, so maybe you could just remove it. Move it from your.
It's a little bit too close to the mouth.
Yeah, maybe move it a little closer though. That's a little too far.
Is that a little bit better?
I think that's better. Try that.
Try that's better. Okay. So the idea is to generate an RFI filter that can reject out to a long distance with beam overlap. There's also a helpful situation because the Doppler shift is slightly different across the pattern of the antenna of each antenna. So if you take into account the overlap of the beams together with the Doppler shift, which is greater than 1 bin, 3.73 hertz, about 15 hertz for the Doppler shift across the beam, This is an RFI filter that can reject to about 720,000 miles before RFI starts to essentially be in the beam. So of course, there's always the issue of side lobes and other things that could occur. So we've been running this system since late 2017. We ran 135 hours until February of 2019. Each of these lines is approximately 2 days of observation. And we started not running all around the clock. And then as we ended up, we started running it continuously. And then we we finished up accumulated 180 hours in April of 2019. And then in December of 2019, we were able to run 3 telescopes together for about 4.6 days of combined pairs and about 1.8 days where Green Bank, Haswell, and New Hampshire were all pointing together. So it's a total of about 290 hours of accumulated time total. So I'm going to talk about observations. And before I say anything more, I'd like to say that I'm a huge fan of multiple hypotheses and analysis of hypotheses relative to each other with Bayesian inference. So I'm not going to hopefully say anything that will make you think that some of these observations might be an extraterrestrial signal. So this is what we saw after 135 hours. There were 7 pulses that were within plus or minus 1 hertz. This is right ascension around the circle. And those 7 pulses were as a result of the post-processing of all those first 135 hours of data. Now, the first thing that I noticed, which really got my attention there, is that 2 of the pulses within 1 hertz were on consecutive days in August 15th and August 16th of 2018. And the other thing I noticed is that many of the pulses have high signal-to-noise ratio, well above the 12 dB threshold. So those are anomalies that can be analyzed statistically to say, is there something there? So more than just, do we have signals on the same frequency? We want to know, what is the spectra of the signal when these simultaneous events occurred? So I'll just maybe clarify that these represent pulses that were within plus or minus 1 hertz, exceeding the threshold in the same quarter second at each of the Haswell and Green Bank receive systems. So if we were interested in looking for a communication signal, we would say, okay, well, what do we have? Well, the data stores everything that exceeds the threshold across the frequency, 1400 roughly to 1450 megahertz. And because the SNR threshold is quite high, there aren't that many events. There's about 10 to 20 events that exceed the threshold in a quarter second. And if there is a communication signal present, there is going to be probably some indications of something that diverts from the Poisson statistics that we would expect with this kind of a process. In addition, there might be high SNR. So the combination of SNR and small frequency differences can be used as sort of like a squelch in a radio to say, okay, there might be something interesting here to look at. So this is what happened in the Green Bank data at the same time as the -1 hertz in that direction that I mentioned, where the 2 right ascensions were overlapping. There was okay, so let me explain this graph. This likelihood with an offset is a plot of all the data points that occurred. The cluster is the quarter second of pulses that occurred during that quarter second. The axis, so horizontal axis, is the frequency offset between 2 adjacent tones that occurred in that set of captures. And so there are normally offsets that are on the order of about 2 megahertz or so. Now the graph dips in the middle because we have to, if we're calculating likelihood, we have to multiply by the number of trials. And the number of trials increases as we move away from the offset. So the 0 seconds, I'm sorry, I might have misspoken. The horizontal axis is the time offset from the time that the simultaneous pulse occurred, the -1 hertz simultaneous pulse occurred is a time offset. So there are these outliers that occurred slightly before the simultaneous pulse. So the 0 represents the time of the simultaneous pulse. This represents about 3 or 4 seconds, and there's a table down here that shows the time below that. So there are these outliers here that together we can calculate are extremely rare in noise, and this gets my attention. The other raw data saved for the Haswell telescope and the Green Bank telescope for the other pulse also had some unusual things, but this particular record had the most unusual set of close frequency tones, 607 hertz, 339 hertz, within 10 seconds. This is about a 10 to 20 year noise event that we would tend to see these close frequency spacings within this time interval. Okay, so then April 2019 came along, and then we have so here we have a pulse that was 5.8 hertz off in April 2019 between the two sites. And this had a very interesting spectrum at the two sites. So the Green Bank spectrum is above, the Haswell spectrum is below, and the 5.8 hertz is over here on the left. It turns out that the 5.8 hertz pulse that was present on both antennas had another pulse next to it that was very, very close and much lower than the 2 megahertz we would expect. There were also at each of these red pointers additional close tones that occurred, and there was a set of close tones up here that were close to another set of close tones at Haswell, 1.9 and 3.7, 3.8 kilohertz separation, which is also statistically very significant. This is a zoom on one of this Haswell pulse, and it has an offset of 1.66 kilohertz. So as an engineer who has spent a lot of time building test equipment, I need to figure out what is causing this. So December 2019, we ran all 3 telescopes together, and this is a plot of the offset and frequency between pulses versus right ascension for all of the transits that we did during that period of time of about 5 days while I was in Green Bank and Steve was operating Haswell, and I had the New Hampshire telescope running. If we zoom in on this region we're interested in, this 5 hours of right ascension, there's a collection of pulses down here in the 0 to minus 12 hertz that it appears to be statistically significant, although there are other examples. But the interesting thing about them is the right ascension is very similar on all of them. So if we take the full 24 hours and then calculate the difference in right ascension for these pulses, and then look at how many are accumulated in a window or in a bin, let's say. So if we choose a small right ascension bin, there's a big spike of pulses at this right ascension in this bin. In other words, a group of pulses were very close together in this 0 to minus 14 hertz range, so which seems kind of unusual. We can do some statistics, and depending on assumptions, you get some pretty small numbers because this is obviously a high deviation from the mean we would expect at other right ascensions. So the idea is, another idea is, can we find any pulses on one telescope operating independently? So after I came home in December,
5 minutes.
I ran an experiment to do the post-processing on the 2 orthogonal circular polarized receive signals on the antenna here in New Hampshire. And just as a starting point, and this is a 20 transits, and I had some various RFI filters that I experiment with, which of course can complicate results and is potentially a problem. But the interesting thing is that there does appear to be some anomalous set of pulses. The larger dots are higher signal to noise ratio. In this region around 5.1 to 5.4 right ascension and 0 to 14 hertz. And so the point is to continue looking at this, and I'm improving the system to do that. So what are the conclusions? Well, based on this data, the noise hypothesis appears unlikely to explain data. Of course, there could be many other hypotheses, and maybe I'm making a mistake on my noise hypothesis. But the observed anomalies, I think, compel continuation and looking at this and finding out what else could be going on. So I'm building 2 more telescopes on my farm that are going to be hopefully around 28 feet diameter. One of them I'm going to make transportable so I can move it some distance away from the farm and perform simultaneous nearby 24/7 measurements. And I'd really like to encourage others to try this. It doesn't take a very large telescope to do this test. So I'd like to thank Steve and Deep Space Exploration Society team. They operate the Blishner's telescope, and Green Bank Observatory as well, and family and friends. And thank you all for listening.
Thank you so much, Skip. Gareth, do we have any questions?
Just check out. It doesn't look like we do have too many questions. I didn't catch any. Anybody want to correct me on that?
Dave Larson, did you see any questions?
I just sent one.
You just sent one. Phil, why don't you ask that?
My question was, how do you know that the pulses are not coming in through side lobes and not the main lobe?
Oh, absolutely. So that's one of the RFI models, which is side lobe detection, and that is very possible that could be the case. What I normally see with side lobes is you get a lot of SNR fluctuations, and it's in a normal situation with Ricean statistics with carrier plus noise. They tend to see some pretty high signals with RFI. They jump way up above the SNR threshold, which these don't seem to be doing. But on the other hand, it's an absolutely perfect model. I mean, that's a model that should be fully vetted and tested and compared to others.
Thanks.
Okay, one more question. Any panelists? No? Well, thank you so much.
Oh,
go ahead.
I do have a question.
Yes.
Let's see. Do you have any resources for people who might be interested in getting started or encouraging perhaps their local astronomy department to get on this kind of thing?
Yeah, sure. In fact, my paper should be posted, I think. In addition, contact me. Yeah, I'll be glad to help with what you're trying to do. There are a couple of groups around the country that are working on their own systems, and I'm really anxious to help everybody I can.
Awesome, thank you.
Thank you so much. Thank you, Skip. Wonderful presentation. Okay, again, a reminder to all of the attendees and the panelists, there's a Google document that you can ask questions of. You can type questions in there. The link was just sent out to the chat. It's also posted to the top of the HamSCI workshop agenda page, and you can type questions in there, and then the presenters can answer those questions later. Also, you can use you can access PDFs of the presentations from the Google Drive which is listed on the top of the HamSCI agenda page as well. Okay, next we have Steve Serwin, Whiskey Alpha 5 Foxtrot Radio Foxtrot WA5 FRF. He's from the HamSCI community. He's going to be talking about WWV time to arrival time study to investigate multiple modes during daily dawn and dusk transitions. So I know some people were asking earlier for a better explanation of what we meant by Doppler shift. I think Steve's presentation will be able to answer that and show some of the nice results that we're getting from this. So whenever you're ready, Steve, take it away.
Okay, well, good afternoon, everyone, or still morning here. I'm Steve Serwin. I'm going to talk to you about some experiments I did in looking at the timing of WWV pulses to attempt to shed more light on some of the Doppler shifts that you see. So let's see, we'll do that. I want to make sure that I did the audio transfer and then go to full screen. Okay. The data I'm going to give to you is taken on a path that was from Fort Collins, Colorado to my location in, well, it's near San Antonio. It's about 30 miles west of the city. Okay, the motivation, the reason I wanted to do this is when I was doing the ARRL frequency measurement tests, I noticed that especially at dawn, the Doppler shifts kind of go crazy. During the evening, there was lots of frequency variance. It's at 5 megahertz. During the day, it's fairly quiet, but boy, when dawn comes, the tracks just run amok. And this amok time corresponds to the opening of higher angle modes. In particular, this is a graph of critical frequency, which is a very good metric to find out if higher angle modes can propagate or not. So my thoughts at the time were perhaps these multiple modes, which sure look like they appear in some sort of geometric progression or overtone order, might be multiple modes, in particular multiple hops coming from the ionosphere. There's a number of other hints that suggest this. One is, for example, this mode doesn't manifest till you're halfway through that dawn transition, because that's how long it took for that angle corresponding to that mode to become viable. This is 2.5 megahertz. They exhibit the same thing. 5 megahertz is the one we're talking about in particular. Here's a straight line mode, one overtone, another, and yet another. None of that goes on at 10 megahertz, but the critical frequency never got that high. So Doppler always infers a change in path length with time. Doppler is in fact the ratio of velocity to the speed of light times the center frequency. So for 5 megahertz, it's velocity divided by 60. We'll give you what the Doppler is if you know the speed in meters per second. So here's the setup. Here's a fixed station, fixed receiver. That doesn't change. What does change is the path that the radio wave takes to get from transmit to receive. And that is changed by the height of the ionization layer. If the ionization layer is fixed, there's no change in relative path, there's no Doppler. Multiple hop modes have a longer path as opposed to a single hop mode. So as this ionization descends, those longer paths have to get shorter faster. They have more velocity, so they have more Doppler shifts. That was the thing I was trying to look at. And of course, as the sun comes up, propagation at higher and higher angles become possible. So how do you know if what you're hearing is coming on what kind of mode? We looked at measurement of the angle of arrival. That's possible, but hard, certainly not within most hams' reach. But timing is something a lot easier to measure. This path, this double hop path is longer than this one, so the time of flight is longer. Now, other things happen at dawn that complicate things. Pedersen waves appear, which are these modes that are high angle but spend a lot of time up in the ionization region. The D and E layers wake up at dawn. F layer splits. Wave speeds are accelerating and decelerating, and an accelerating wave speed does the same thing to frequency that a closing path does. Wave fronts bunch up and you get a frequency increase. Not only that, but sometimes, very often in fact, at 5 megahertz here in South Texas, I can hear both WWV in Fort Collins and WWVH in Hawaii. They're both there. They have their own Doppler shift schedules. And so separating these things can be a problem. Timing can help sort this out. So here's published data on WWV over here on the left. These timing ticks are 5 cycles of 1 kilohertz for WWV. WWVH from Hawaii sends 6 cycles of 1200 hertz. In addition, they send these tones with quiet periods in between. And these 500 and 600 hertz tones swap. 1 minute it's WWV on 500, the next minute it's WWVH on 500, so they interchange. Synchronization for time can be obtained from the 1 pulse per second output from a GPS-DO. So here is some actual on-the-air pulses. Here's one of those times when both WWV come in and WWVH. They're separated in time by like 17 milliseconds because of why so much farther away. Here was below this, the screen trace is a particular time when I heard WWVH, but not WWV. For those of you who haven't heard these time ticks, I'm going to play a little audio. You'll hear this tone on the left coming and going. Then you'll hear voice announcements, female voice for Hawaii, male voice for Fort Collins. You'll hear both of them, and then you'll hear the tones start again. And all through this, you'll hear these annoyingly loud time ticks.
At the tone, 12 hours, 2 minutes, coordinated universal time.
And so that's WWV, and those ticks are what we're talking about. So how do you measure those? It's not real hard. You could get by with just a good receiver and a digital scope I use because it makes good records and it enables on-screen measurements. This was a Agilent scope. To synchronize it, this little purple trace right here is a sync pulse. It's the 1 pulse per second output from the GPS-DO. I also look at the spectra. For example, here's one morning's spectra of the amok time of WWV during the dawn transition. And I use an R8600, which has been stabilized with the 10 megahertz reference output. So I wanted to find out what kind of time delays to expect. So I put together this simplistic idealized geometry, flat Earth, constant reflection height. Here's the path distance. Here's the reflection height. So now simple geometry can let you calculate this path for 1 hop, 2 hops, 3 hops. And then you can convert path length to time of flight through the speed of light. And so here is a graph of these equations corrected to speed of light for reflection heights from like 100 to 400 kilometers. So here is the primary 1 hop mode. Here's the time of flight for 2 hops. And here's the time of flight for 3 hops. Now, the thing to notice is, let's pick a mid-range here. The time difference between 1 hop and 2 is a millisecond or so. For the next mode, it may be 2 milliseconds. Point is that the pulse length is 5 milliseconds. So these delayed copies come down on top of the primary. They superimpose. So you're looking at superposition. So here's 2 lines of data. This one is simulated on a SPICE program, just summing 2 5-cycle sine waves together. And down here is measured instances of what we're seeing. In this first graph is 1 millisecond of time difference, turns this 5-cycle pulse into a 6-cycle pulse. So this pulse out here in front is this one by itself. These are the sum of the ones in the middle. The one on the end is the delayed pulse all by itself. Can you see those on the air? Yep, here it is. That same picture with the first and last pulses smaller, 6 pulses from WWV instead of 5. If you have 2 milliseconds of delay, you have 2 cycles at the beginning and from the first pulse and 2 cycles from the end from the last to make a 7-cycle pulse. Here is one of those. And similarly for 3 milliseconds delay, you get an 8-cycle long pulse. And here is one of those. So you got to calibrate the receiver. That IC7610 that I used is a software-defined radio. And software-defined radios have a relatively long processing time to get from the input to the output, and you have to know what that is. So I cobbled together this little AM burst waveform with lab signal generators, fed it to the input of the 7610, and here's what came out, the audio. 2 things, it's delayed by 4 milliseconds. Secondly, the 7610 has an inverting path. In other words, when the amplitude gets bigger, the output goes negative. I took all my measurements to the middle of this first positive cycle. Here's my sync reference from the GPSDO. Here's where I measured to. This is where I want to measure to. So I measure from here to here. I've got to subtract out the 4 milliseconds delay through the 7610, and I got to subtract out this 3/4 of a wave. So it's that measurement minus 4.75 gives me arrival time with the primary pulse. So I measured a bunch of these things, sit in front of your radio for 5 hours, capturing screen captures, and then spend another 2 days inputting it to a spreadsheet, make a cluster plot, and they clustered. They clustered in layers, which suspiciously looked like multiple hops to me. Here's the timing data for the 1-hop data from 1200 Zulu to 1530, and here's the delayed copies. So this first hop was done by referencing to the beginning of the pulse, and then these were delays. How much did the pulse extend in length, which is the delayed arrival of the multiple hops. For reference, here's sunrise at my QTH, here's sunrise at WWV. When the sunrise was over the mean path, I started picking up these higher angle modes. I took that graph I showed you earlier about predicted times of flight, turned it around so that I have a descending reflection layer here. And then I cropped it, picked the part of that graph that matched the data that I measured. Now, this data was not continuous because I took these sequentially, and out of the 14,000 1-second pulses I got, I only collected about 250. So there's big gaps in here. I interpolated linear interpolation so that I could get a continuous function that Excel could draw a trend line through. And that they lined up pretty good. I got some good reference data from both Nathaniel and Carl. Nathaniel sent me this Farlap ray trace predictions at a specific time on that day. Here's 1200 Zulu. I happen to have a data point at 1201. Here's his prediction of the time of flight, and this blue bubble here is my measurement. So I didn't think that was too far off. That's within tens of microseconds, maybe 50 or so. Here's the same data for 2 hops, Farlap data for 2 hops. Now you can get both pieces of data from this pulse, because timing to the beginning of it is just the 1-hop mode, and then looking at the pulse extension at the end is the delayed copy. So you get the 2nd hop delay here. So here was the timing to the first reception, and then here's the delayed copy, and those fit nicely to the points where his graph diverges into the 2 modes. Thank you, Nathaniel W2NAF, for that data. Carl, K9LA, sent me PropLab Pro simulations for a 3-hop mode. Here's a 3-hop data trace. You can see the extra 2 cycles here in the end. The PropLab Pro predicted 6.46 milliseconds. I'm sorry, yes, he estimated 646 with the ray trace simulation. The measurement was 6.38. A little bit about making these measurements. I did these by looking at the extension on the end, but there's a better way. And the reason there's a better way is that all these pulses in the middle are distorted by superposition. That's the time when both pulses are present. This first pulse is all by itself. It's the 1-hop mode. These last pulses, these last cycles, I should say, are from the delayed copy only. So they are not distorted by superposition. So the best way to measure this is to reference off the leading edge and the trailing edge. So you do the same kind of subtractions, but in addition, pull off these 4 interim cycles. That's a better way of measuring it.
5 minutes.
Okay, and we're just about done. That's good. Here is the reality of the morning dawn transition. This is PropLab simulations from 2.5 hours before sunrise to 2.5 hours after sunrise. So you can see that while it's still pitch dark, pretty much one hop propagation is all there is. And by the way, this is a function of angle. And you can see that a lot of these angles don't get refracted. About the time sunrise makes it to my QTH, now we're starting getting these 2-hop modes. Sort of jives with that one mode manifesting at just the right time. Mean sunrise between the path, it gets sunrise here a little before it does in Fort Collins, which is farther west. Here's 3 hops starting to happen. And then as the sun continues to come up, more modes happen. You can see some Pedersen rays coming in here. You can see the overall lowering of the ionization region. If you could plot all of that and then take the time rate of change, you could infer Doppler from that. You can also see that there's refraction from multiple heights in here. So the point is that it's a complicated, as a common vernacular, it's complicated. And the timing analysis can help sort this out. Okay, we can take questions.
Thank you so much, Steve. Very nice analysis. Questions? See, moderators, do you have any questions?
Yeah, I had one. This is Gareth Perry. Steve, I might have missed it, but how do you know you're not seeing just mode decoupling? So you're not seeing a decoupling of the O and the X mode as that delayed pulse or that delayed, you talked about the arrival of a pulse and then, you know, a bit of a delay with a copy. Did you discuss mode separation between O and X mode there?
How much time difference is there between those two?
Oh, I wouldn't know off the top of my head. Microseconds, perhaps?
Well,
somebody else want to shout at me for that answer?
If it's microseconds, then that's not going on because the time differences that we're seeing are milliseconds, which really do jive with the geometry.
Okay, good. Thank you.
You bet.
Certainly doing that O and X mode timing prediction, that's something that Barlap could give us. It could tell us what the expected differences would be. So then we could basically rule that out.
Or at least know how to account for it.
That's right, yes.
Yeah, it's a complicated process, and I certainly don't know all what goes on here. This is a work in progress. But it looks like this data does point to, anyway, suggest that those multiple frequency tracks, divergence of the Doppler into 3 or 4 different modes is from different modes. Whether one's 3 hops or 4 hops versus a Pedersen wave, I don't know. Got to figure out some more ways to separate those things.
One more question? Any more questions? Okay, thank you very much, Steve. I really appreciate it.
Thank you, Nathaniel.
We'll keep working on this. Okay, so next up we have David McGaw, who is also going to talk about Doppler shift type of observations, but using a slightly different band. So David McGaw, N1HAC, is a research engineer at Dartmouth College, and he's going to talk about traveling ionospheric disturbances observed using Doppler measurements of clear channel AM broadcast transceivers. So I'm going to stop Steve sharing. So go ahead, David, you can take control.
Can you hear me now?
I can hear you.
Oh, okay. Very good. And you have the slides up?
And I see the slides, yes.
Okay, very good. I got a panel on the side here. Anyway, I'm David McGaw, N1HAC, research engineer at Dartmouth College, also vice president of our local club, the Twin State Radio Club. And we've done a, is there a way to hide the panels? It's covering my presentation here.
You can slide them off to the side, but we don't see them on your screen share, so they're not interfering with what we
Right.
see.
Okay, good. How am I going to? There we go. We started out with this research with an original proof of concept done in 2012, and a paper that was written by Mike Chilcott and others, published in AGU Radio Science, and a number of undergraduates were also involved. This was done using the MIT HamSCI ISIS receivers that are distributed around the Northeast. And we had help from Juha Viernen. This is the antenna that we used, had them at a number of sites. It's a smaller version of what we use for our HF research in the polar regions. It's about 7 feet on a side, loop antenna into a low noise preamp. And we had systems at Dartmouth, at HamSCI, and over at Siena College in upstate New York, picking up, in this case, WGY from Siena, from Schenectady West, and WBZ from Boston. And this is the data that we got from there. You know, as you see that it's shifting a few hertz, a few tenths of a hertz, plus or minus, due to Doppler shifts from the ionosphere. You'll also notice that the carrier frequencies can be slightly offset. This is a normal thing for AM radio stations. And this is an analysis that was done in the paper, lining up our Doppler shifts with the HamSCI Digisond, GPS total electron content measurements, and Wallop's SuperDarn, showing that the effects that we're seeing correlate with other ways of studying this. We changed for further study to a newer antenna, much smaller, essentially same preamp, but the large loop is much higher sensitivity than we need. So this works out well. It's two turns instead of the single turn, works out to the same effective inductance, but is better suited for what we're doing, and have deployed those to give them a try. The next, this next stage in our development was to deploy them in the same locations. No, actually, we added Jenny Jump in New Jersey, and then picked up several radio stations, Boston, Schenectady, and New York City. This time we were using the USRP software-defined radios, and we've gotten new results from that, as shown here, shifting you know, a few tenths of hertz, and showing that they we do indeed get good Doppler shifts off of these signals. So then we started development of our own system. I was showing it at the HamSCI conference a couple years ago. This is at Hamvention 2019. And we have now deployed the system out in a number of places. This is the receiver. It uses a 12-volt power supply. If we needed to put it on like solar panel or whatever, we could. It has an input for the preamp. We use a solid state hard drive. And this is showing it with a MiFi cellular radio interface. As one of our sites, we do not have access to wired internet. That's the front panel. It uses a Raspberry Pi, so you see that over on the left. We have a GPS internally, and we bring that out so that we can monitor it. GPS antenna going in. We have a attenuator on there because we're varying different distances from local radio stations, so we can pop in an attenuation as needed to prevent overload. This is the inside of the receiver, and made up of a number of components, and this is what's in there. We'll start on the lower right. We have the power input and a bias T for the preamplifier out to the antenna, remotely powered. Then it runs into the attenuator. Then it's fed to the Nolec Hammond up converter, because we're doing the AM broadcast band, and the SDR that we're using in this doesn't cover that directly. Goes into the RTL SDR. That's 24 megahertz and up, so that's why we run the up converter. There's the GPS disciplined oscillator that is our frequency reference. Because we're measuring things on the order of tenths of hertz on a megahertz, that's 10 to the minus 7th. We clearly need a reference frequency much tighter than that. That goes into the frequency synthesizer, which is a TI chip that develops 28.8 megahertz to the RTL SDR, which is its primary clock frequency. And then we create a 129.6 megahertz local oscillator for the up converter. The up converter, as it comes, is 125 megahertz internally, but 129.6 is harmonically related to 28.8, and it does fall within the pass band of the up converter local oscillator chain. We have a 12 to 5 volt DC-DC converter internally, and a couple of regulators that are used to develop voltages that the frequency synthesizer uses. And finally, we have the Raspberry Pi, which is the processing heart to the system. And the Raspberry Pi does yeoman service for us. What we're doing, we're running the RTL SDR at a 1 megahertz sample rate, and pulling in 600 kilohertz to 1.6 megahertz. And then the Raspberry Pi decimates that a couple of times. First, breaking it into individual AM station channels, and then it filters it further so that we're only looking at those 1.5 hertz channels, so that we can actually discriminate the Doppler shifts. So we have receiver sites. These are the designations of our receivers. AMD1 was a prototype that went to South Africa and was used there. But number 2 is the one that we keep at Dartmouth College. AMD3 is at Schenectady, New York, courtesy of MIT Haystack, Phil Erickson for citing that. AMD4 is at Jenny Jump, New Jersey, courtesy of NJIT and a number of individuals that have helped with that. AMD5 is at UMass Dartmouth, which is down on the coast near Cape Cod, and courtesy of Dave. No, that's I forget who we have that there, but they're with the maritime department there. AMD6 is at Cornell, courtesy of David Heisel there. And then AMD7 is pending, will be sited up in Messina, New York, to develop a ring of receivers around Schenectady and its clear channel station there. So these are the radio channels that are monitored from our system. WGY Schenectady is sort of our primary at the moment that we're looking at. But we have a number of them from Montreal, New York City, Toronto, Boston, and the one I used to listen to the Red Sox on, Hartford, Connecticut. This is our data as we receive it now. We're kind of on the early stages of plotting and analyzing. So this is a couple of panels of our that are coming out that's got a few hours of data. I've plotted this to show starting at during daytime on the left, and you can see the signals coming in as sunset sets in, and then further on into the evening and nighttime. You're seeing Doppler shifts coming in. And then this is a series of 3 panels of those 4, the ones to the right. I wasn't quite sure how to show this, so hopefully I can flip between them quickly. But this is the Dartmouth, Schenectady, and UMass Dartmouth on a night recently when things were moving around. And I think you can see how the Doppler shifts correspond, but are occurring at different times. And that is actually the end of my presentation. Are there any questions?
Questions. Thank you, David.
Yeah, I have a question on behalf of Jay Swartz. So the question is, are there any plans to make the AM Doppler receiver available for purchase as a kit or fully assembled?
We hadn't planned on that. We can certainly document it so it could be built by others.
Okay, and Anton has a question, Dr. Anton Kashcheyev. Go ahead. Anton, go ahead with your question. Anton, are you there?
Nathan, he just muted his mic.
Oh, okay. How about now? He's unmuted. Okay, maybe we'll come back to you. Are there any other questions?
This is Phil. David, you had to modify the up converter, I think, from the way it came when you just ordered it, correct? Was that something that was supported by the manufacturer, or was that something that you had to sort of reverse engineer?
No, and then yes. Well, what it is, the original ones that we got, I had to pull the oscillator out and tie in direct. But it turns out that the newer ones have a micro RF coaxial jack on them. And I was just able to drill a hole and buy a interface cable from DigiKey and pop it in. I just had to change disable the onboard oscillator and put the external local oscillator in. They did think of that on a second further revision.
That's really great.
Now the RTL SDR, I did have to hand patch that one, but again, pull the oscillator, and there are some holes there that it's easy enough to put a coaxial cable into it and run a jack out to the outside.
Another question?
Yeah, Anton got his through the chat here. Let me reiterate it. So his question is whether David has plans to reconstruct TID properties, e.g. velocities, it's moving to here, e.g. velocities, period, wavelength, etc., as he has multiple sites and can do it using interferometry.
Yes, absolutely. That's the intention of this system. And this is under my boss, Dr. Jim LaBelle at Dartmouth, and he will be giving a talk tomorrow. And maybe he will address some of that, as well as the other research that we're doing.
Okay, I have another question, actually, if we have time. Question from K60IK. How do you distinguish between Doppler and apparent Doppler due to interference from other co-channel signals at night?
Well, that's a very good question. We haven't quite worked that out. In fact, I think we're seeing multiple stations coming in. So that would be an exercise for the student.
David, it occurs to me, like WGY, I know in particular, is a clear channel station, which in theory means they're supposed to keep that lane clear, but I don't know out to what distance they keep it clear.
Yeah. Well, that's an interesting point, that these stations used to be truly clear channel, but I've noticed that a number of them have other stations on the same frequency within distance that we would probably see them at night. So it may be distinguishable by amplitude, but also each one of those stations has a set frequency offset from the center channel. Now, actually, some of them have a very odd oscillation on them that we saw. Maybe I can reshare here for a moment. And in fact, the one that let's see, which one of these is, yeah. If you see the bottom, next to the bottom station, it's got this oscillation on it. It's also very much offset. And it's the only station we've seen that particular oscillation on. But it's not, we have to wonder what is going on there with the station's frequency. They're not as controlled as they once were by the FCC. And we haven't found specific documentation of offsets, though there are SWLs, or should I say MWLs, out there that do document such things.
Well, thank you very much, David. And yes, let's all thank David. I guess we need some way of having virtual applause on these things. We haven't quite figured that out. It's a little weird going between presentations without having some applause, but thank you very much. And thank you to all the people who asked questions. Okay, and now we will move on to the last talk of this session, and that will be from Dr. Phil Erickson, W1PJE of the MIT Haystack Observatory. And he's going to be talking to us about amateur digital mode based on remote sensing, FT8 use as a radar signal of opportunity for ionospheric characterization. Okay, Phil, go ahead.
Thank you very much. Let me see if I can share my screen correctly here. All right. Can you guys see my screen?
Yes, we can.
Okay, great. So it's very nice to virtually be here, and I probably get minus points for having too long of a title. This is a work that has essentially been in progress for a little while now. And I want to point out my co-authors, who are Bill Lyles, NQ6Z, and Ethan Miller, K8GU. It's been a real collaborative effort, so I'm really honestly just reporting most of the hard work that the other folks have done. I'll go over why an overview of FT8 itself and why we might be looking at it in terms of an ionospheric remote sensor. I will talk about these things called radar ambiguity functions, which may be familiar to some if you've ever taken a course on radar or had some design experience with radar, but may not be familiar to everyone. And then what we're going to try to do here is see, hey, there's a lot of FT8 signals out there. Can we use some of them as a forward scatter remote sensor of ionospheric properties? I want to emphasize this is the beginning of our study, and there's lots more to do, but I'll give you sort of the highlights of where we ended up initially. So these are digital modes from our friends Joe Taylor, K1JT, and Steve Frank, K9AN, which have certainly swept the amateur community in the last 3 or 4 years as being really transformative, especially when we're talking about weak signal propagation or very low signal detection in the current solar minimum conditions that we're living in. These have really been a game changer for small stations to be able to make contacts. The interesting thing, by the way, there is a bit of a connection here in that Steve Frank was actually on Ethan Miller's PhD committee, so he even has a direct connection to this, professor at the University of Illinois. These were designed by Joe and Steve and company to be weak signal codes, and they're one of a suite of codes that sort of labeled WSJT, weak signal Joe Taylor. And they are things that are designed to be used in SSB audio bandwidths, which a conventional transceiver can be used. And they basically use some of the best coding theory that are out there for doing really robust error correction built-in communications. And the key design parameter in these kinds of things is EB over N0, which is the energy in a bit of communication divided by the noise floor in that bandwidth that you're transmitting the bit. And these are down to a few decibels above the noise floor. So they are really pretty close to state of the art in these sorts of things, especially at HF. If you look down here on the left-hand side on the bottom, you'll see a typical WSJTX set of people transmitting and people receiving. And then figure 1 shows you sort of a block diagram of how you would send your message. There's an encoder, you transmit it through the radio, someone on the other end receives it, and they demodulate it. They typically use a combination of, some of them use low density parity codes, and that's what we're going to be concentrating on today. Some of them use Reed-Solomon codes, and some of them use convolutional codes. And they have a very, very sophisticated deep decoder that uses a lot of interesting math to really pull out the last morsel of signal from a signal in the form of noise. So if you'd like to read, there's that Joe and Steve had put up a nice set of really meaty papers on the soft decision coder, which is really interesting. Just for reference, the best human CW operator has been quoted to can tick out a signal in about a 50 hertz bandwidth if it's really, really weak. FT8 is essentially only using as much bandwidth as that best set of ears, but has a much better detection floor than conventional CW. This table on the bottom shows you the various kinds of codes. We're going to be focusing on FT8 here, which is a LDPC, which is low density parity code. I'll explain more about what those numbers mean in a minute. And but it's obviously part of a suite of codes. So the question that our little group had was, can we use these things as a remote sensing ionospheric radar, really? And I like this table from one of Joe's articles because it shows you the various waterfall graphs of the various coding that is available in this suite. If we just focus on two things, we have the carrier over here. This is just basically a tone. You hold the key down, you don't do any modulation of it. And a carrier is a great thing for velocity. We just heard Steve Serwin talk about very accurate Doppler measurements or velocity measurements. That's really great. It has almost no range information in it at all. In fact, a CW tone has none. That's like a police radar, okay? It concentrates on frequency measurement at the expense of range measurement. If we look at FT8 over here, you'll notice that it's considerably spread in bandwidth compared to the carrier example. And so there's some range and velocity information that you might be able to pull out of that, because any signal that is spread some in bandwidth, there's something called the Rayleigh criterion that translates bandwidth into range information if you can process it quickly. So we thought, oh, well, there are some potentials for radar, okay, in here. And this is actually a slide that Christina made up that I've been using for a little bit. What do you do with measuring frequency and what do you do with measuring range in our case? If you remote sensing the frequency shift, you're going to be measuring the Doppler shift, which is essentially can be related to the ionospheric velocity. We've heard from Steve Serwin. We're going to hear from other people later in this conference about, again, measuring and interpreting Doppler. I will point out that I also gave a talk at the Tapper DCC meeting in 2019, which is available online, called Challenges in Understanding WWV Doppler, just to show you that, as in many things, it's a little complicated to analyze this thing, but you can make some interpretations about what the Doppler means on your path. So that's measuring frequency, which we're interested in. If you measure range, a very classic signal that measures range is an ionosonde. You send a pulse, a limited thing in time at a particular frequency. You time how long the return takes. And from that, you can then extract ionospheric information. In this case, you can recover some information about the bottom side electron density profile in the ionosphere. So in one case, measuring range is interesting. In another case, measuring velocity is interesting. So how do you figure out whether a particular transmission, especially one you do not control, like FT8, is useful for radar? Well, in the radar literature, there's this thing called the radar ambiguity function, and you can look up a number of textbooks and other references that talk about this. The idea is to evaluate how good your pattern is in figuring out how far away an object is, that's range, and what its frequency is, for example, Doppler shift, when the target may not be stationary, like it's moving in Doppler, which means it has a Doppler shift, as well as it may have a range extent. This thing called the radar ambiguity function, this is one of the mathematical definitions of it, but look at the picture down here. You make these little plots, which are two-dimensional, and the color indicates the amplitude of your ambiguity function. The range is on the x-axis, and the Doppler is on the y-axis. And this is an idea of how poorly you're doing in your range and Doppler. The thing in the middle is what you want to measure. You want to measure the object at the precise range it's at and at the precise Doppler shift it's actually at. No code is perfect. All these other colors you see here are side lobes. Those are unwanted responses, so that anything, for example, in this little diagram, that's at a little higher Doppler and a little bit closer to you in range has a little contribution that kind of gets mixed up with the thing that you want in range and Doppler. And so the mathematics of picking a radar transmission signal is to attempt to determine how can I make that code look more like a dot in the center, which is called a thumbtack function. Kind of looks like a thumbtack sticking up, or a delta function. And I'll just point out that, yes, this one happens to be not an ideal code. It was used as an example.
Phil, we are seeing your presenter's desktop.
Oh, no, really? Okay. Has that been going on the whole time? Probably. Well, how about this? I will pause for one moment and I will just share my desktop. How about that? And now, can you see my desktop? Can
There
you
you
see
go.
there? Thank you very much. So I've been explaining here that we have a, we'd like a thumbtack function. Okay, that's what we'd really like to head for. There's a very nice analogy that I want to point out. It's kind of like a blurring kernel in image processing. The original picture at the top is the actual object that you'd like to take a picture of, but maybe you have a lens, for example, that's dirty or that isn't the best lens, and you can mathematically deal with that by applying what we call a blurring function, which takes the original and makes the thing at the bottom. It makes a blurry example of that. So we'd like the thing on the top, the thing we measure is on the bottom. You can think of this in a radar sense is that this in here is mixing up the two-dimensional X and Y in the image. Here you can think of X as being the range and Y being Doppler or frequency. We would like as little blurring as we can. So it turns out that there are many coding examples of how you get toward not too much blurring. One of the simplest one is a pseudo-random phase code. You basically make a random sequence. In this case, I've basically created a 1024 long random code, which is a phase code. So it just goes between +1 and -1. You either shift the sign or you don't. And as you make that thing longer, on the left-hand side is my Doppler and range. And I've zoomed in on the middle at the right-hand side to show you that there is, in fact, a very nice, pretty close to thumbtack in the middle, and all that other stuff is little bits of confusion because it's a fairly long random sequence. And this is easy to explain in an intuitive way because a random sequence only perfectly correlates with itself. So it tends not to mix up range and Doppler. As you make the code longer and more random, it gets better. So this is a place that we might want to head for. So now let's look at FT8. There's a bunch of facts about FT8 at the top there, but the important things are that it uses 8 frequency tones. So that's 8 frequency shift keying spaced out by 6.25 hertz. So it occupies a total bandwidth of about 50 hertz. And if you dig into the details, okay, and there's plenty of details in the bottom, this is one of these low density parity codes. It takes 87 information bits out and then makes 174 coded bits. And then you've got essentially 8 tones. So each time period, you can put 3 bits of information in there. And then the final thing that happens is that Joe allows for the fact that the receiver may have an offset. The clock on the computer may be offset in time, and the receiver may have drifted a little in Doppler. So he puts these things called Costas arrays at the beginning, middle, and end of the sequence. And those are in orange right there. And they are designed to let him search for the time and frequency offset of his receiver with respect to the transmitter. And so he assembles that whole thing into a payload that you see represented by that numbers. So what we wanted to do was take the blue part, never mind the Costas part for the moment. We wanted to see how random does that blue part, which is the actual coded message poured through this very sophisticated low density parity code, which has lots of error checking in it, how random did that make the message? Remembering back here that we'd like to head for that. So Ethan made this particular plot. On the top is what we call a message stencil, which means everywhere there's a yellow block, we're using that frequency and time is on the x-axis. So for example, at the beginning, you're transmitting on frequency 4, then to frequency 2, and then to frequency 5 and such and on. And you take that and you calculate the radar ambiguity function by using that mathematical formula I said before, and you get the bottom part, which is essentially your estimate of how good this code is. Remember, we're looking for something that only has a dot in the middle and not much else everywhere. That's pretty good. This, by the way, is for the sequence that you see on the right-hand side, K1ABC from W9XYZ at grid square EN37. So one message on its own looks pretty good. It looks pretty random in that 15-second interval. But there are some side lobes visible. If I plotted that in a log scale rather than a linear scale, you would see that in fact there are some not responses not in the center that are mixing a little bit of information. And did we happen to pick a message that coded into a quasi-random sequence by total luck? We wanted to check that. The way to do that is something called Levenshtein distance. This is Vladimir or Volodya Levenshtein, who received the IEEE Hamming Medal in 2006. This is a general metric for measuring the difference between two sequences. There's two examples on the left and the right-hand side. You can use this for strings, like I want to take the word kittens and transform it to sitting. Takes me 3 steps. So the Levenshtein distance between kittens and sitting is 3. Or on the right-hand side, I've got some numerical sequences, and the distance between A and B, for example, is 1, because I only changed one number to get from A to B. So this we're going to use as a tool. Let's see how random a range of FT8 messages is, rather than just one. The more random, the better we can make this by piling together multiple sequences. So pretty much the last thing I will tell you is this is how it comes out. That antenna that you can sort of see in the lower left-hand corner is my little extremely modest fan dipole in my backyard, not even that high. I have an FT8 receiver running on a red Pitaya pretty much continuously. And on the January 2nd of this year, it collected 38,567 spots from 8,000 plus unique calls. We took that database. And on the right, what you see is we compared every message to every other message and assessed its randomness using the Levenshtein criterion, which is almost 1 billion different message pairs. There's an example there on the left. And we did the histogram. How far were these apart? And if you look at the histogram, it turns out that they were on average apart by about 41 or 42 changes in the message. Remember, the message length is 58 symbols. If they were perfectly random from message to message, they would be at 58. So that sequence sense is reasonably random. And in fact, that's even a little bit better because all of the messages, we started out with W1PJE because that's where I was receiving them. So that's inherently a non-random element. And still, that message sequence was pretty random. This is good. That means that we could take 7 or 8 of these codes over say, a 2-minute sequence and stack them as long as those receivers were in about the right direction for better performance. So just as a summary, this is kind of where we've gotten to right at the moment, is that the coding that is built into FT8 means that even though you're sending a coherent message, my call sign, your call sign, location, the coding randomizes it really well, makes it a pretty good radar signal. And now I've shown you also that I can take multiple of these sequences, string them together, and improve the randomness. However, it's a work in progress because what kind of Doppler and range resolution did we get out of this? Well, the Doppler resolution is about 1 over the sequence length, which is actually a little bit less than 1/10 of a hertz, which is pretty good. Ionospherically, that's about 10 to 15 meters a second velocities. That's all right. The range resolution isn't so hot. FT8 occupies a bandwidth of 50 hertz. If you flip that over, that's, oh, I can tell you where we are to a half an Earth radius. That's not so hot. But there are more exotic super resolution processing techniques where essentially you oversample the signal and then you go ahead and try to synthesize more range out of it. They may help. That's a future study. But I think this kind of has, if you can imagine a bunch of personal space weather stations out there collecting FT8 signals in this manner, I think there's some real possibilities here for doing basically what we call passive radar, which is just a radar where you don't control the transmitter, with all of these huge numbers of FT8 signals flying around out of there. So stay tuned, work in progress, but hopefully this will be a nice application for the space weather station. And I'll stop there.
Thank you so much, Phil. That was great. It's really nice to see this because it really shows something that we can possibly use to make good measurements with an actual amateur radio mode. So people can operate their ham radios like they do right now. We can provide a good way of collecting that observations back for the ham radio community. And we can also collect some good ionospheric data from this as well. So we are right up against another break, so it's just about lunchtime now, but we'll take a couple questions before we put it into open webinar mode.
Yeah, Phil, Gareth here. I got a question from Anton. It's about that figure you have up on your slide right now in the top left, about the color code. I think he's wondering what.
Oh, like let me back up that one right there, huh?
That's correct. Yeah.
Oh, the color code is literally just to show you that wherever there's yellow, that means I'm using that frequency bin, and whether there's blue, it means I'm not. And if you look, I'm only using one frequency tone at a time. So if you look across, you'll notice that there's never vertically more than one yellow block. So that's what we call it a stencil. It's sort of like an old punch card in that we punch one column at a time, and then as a function of time, so if you ever turn on an FT8 signal and put it in your headphones and listen to it, you hear this warbling frequency, but there's never more than one tone at any particular time.
Thank you very
Bill,
much.
I had a question.
Yes.
For Phil. When you were doing the talk about the Levenstein analysis, I think you made the statement that you thought that the call W1PJE appears in all the messages, but that's only true if the station is calling you. I mean, if you're saying using like a red pitaya to collect FT8, there's not going to be a whole lot of messages in 38,000 messages that have your call sign in the W1PJE.
I completely agree, Bill. And what we just did was, for this particular thing, we just started with, I was always one of the stations, okay? You are right. In a general station that is receiving call A to call B, the only caveat I will put on this is that I think our analysis only extended to messages that had the receiver and the transmitter and the grid square. Because we figured, we want to be using this for remote sensing, so you want to know where would this one of the stations is coming from. If you look at FT8 traffic, there's a bunch of things that say RR73 and other kinds of things. We didn't analyze those. So this is, again, it's just the beginning.
Yeah, okay.
One more question? All right. Well, thank you very much, everybody. We will convene again. Thank you again, Phil.
Sure.
Okay. And we'll do the virtual applause. So everyone's clapping at home. All right. So we are going to meet back here again for the formal part of the workshop in about an hour. So that would be 2:50 p.m. Eastern or 1850 Zulu. So if you are following the agenda, again, that agenda is posted on hamsci.org. The webinar, we will leave it open again, so panelists can certainly discuss things. Attendees, feel free to chat in the window. The moderators here are going to be Carl, Carl Letchelswab, K9LA, and Dr. Declan Mulhall, and they will be glad to oversee things. And since we have a little bit more time for lunch, they can let some of the attendees talk as well if they would like to chat using their voice, since we have a good hour or so for lunch. So thank you very much. Take it away, Carl and Dec.
Oh, okay, I'm here, I think now. Hi, Dec, how you doing?
Not too bad, Carl. Can you hear me okay?
Oh, I can see you okay too.
Well, that's good. That's
yes.
I don't know if that's better, but it's good.
Yeah.
Looking at this morning's, can I ask a naive question? And even though it's on the World Wide Web, no, there's not much privacy. It's a little bit embarrassing. But I had a question regarding one of the slides on. Let me see. I had it all in here. Yeah, it was on Christina Collins and David Kasdan's talk. There was solar noise they were looking at, and in the solar noise there was the nighttime turning into the daytime, and there was a graph of the noise. All of a sudden, you could see the sun rising, and then there's a big spike, but then there was nothing, and then there was loads of noise. If the spike was because the radio could see the sun, in some sense, why was there nothing after sunrise? and then a load of noise. Why couldn't you, if you can see the sun, you can see the sun. Where did the 5 megahertz noise go? Do you understand my question?
Can I take a shot at that, maybe?
Yeah.
Declan, this is Phil. If you look at the comments for the questions that have been accumulating on the Google Doc for this, I'm pretty sure that one of the plots, I don't remember which one, also had the amplitude of the carrier that was received as a function of time. After sunrise, that carrier was getting reasonably low enough that I'm pretty sure that I would have to check out whether the algorithm was still locking on the carrier or whether it was being fuzzed by things that were not the carrier. The ionosphere should be reasonably blocking most of the solar emission at that point on that frequency, mainly because the ionosphere basically got the density went up, and so things don't really go trans-ionospheric at that point. So there, and that's in the questions too. There may be a little bit of confusion between, are we really measuring what the Doppler is doing, and if we're not, I don't think that that's solar HF emissions, but that's just my initial guess. Probably would have to be looked at more.
Thanks very much, Phil.
Can I throw in a couple of cents worth?
Oh yeah,
Sure.
I hope you do.
Please do.
That may be all it's worth too. I've noticed, especially at 5 megahertz, that at night the frequency is very turbulent. Lots of wanderings around.
Mm-hmm.
It's not all Doppler. I built some AM and FM demodulators, and a lot of that, especially the symmetrical frequency excursions, is really AM sidebands coming from all the selective fadings. The ionosphere is a great AM modulator. The amplitudes fluctuate wildly, and every time the amplitude changes, that makes sideband, just like an AM transmitter. So some of that is sideband noise, and I've taken some data by sending it through hard limiters, which absolutely strips off the amplitude fluctuations, and a lot of that noise just goes away. Another thing I've noticed is during the day, the frequency track is very, very stable, almost a straight line. No turbulence, no Doppler, no nothing. And that could be that because during the day, the D layer is blocking access to the higher regions of the ionosphere. So maybe all that turbulence is happening up in the F layer, and you can't see that at 5 megahertz during the day.
Yeah, I fully agree with what Steve is doing. There are competing things you're trying to sort out here, right? What path are you looking at? If Steve's conjecture was right and the D layer was really sort of meaning that path was quite stable through most of the day, we know that if we use a ionospheric radar, of megawatt class 1 that I happen to be involved with, and look at the natural ionospheric variability up in the F region, okay, anytime during the day when you turn it on, you're going to get a couple of 2 to 3% just fluctuations, and these are internal gravity waves and other kinds of things floating around. But if the D layer is blocking you from that, I agree with Steve, that path could be extremely stable. And so it's a very interesting thing to track further. With some modeling, as Steve has been doing, you could kind of see if that makes some more logical sense. So definitely a thing to investigate further. But by the way, Steve, I've been noticing that as well here. I'm using my own GPS locked oscillator, and I just leave it running all the time on 5. And I can tell you, I see exactly the same thing. When the sun comes up a little bit after the sunrise, bam, everything just goes to being almost no fluctuations. And if you just look at that curve, it's extremely easy to tell when the sun goes down.
Well, you sure can. I agree with you. It seems that the activity is more violent at dawn. Similar things happen at night. The Dopplers all go the other way. They're negative instead of positive. And you don't see anywhere near as much of the frequency tracks breaking into more modes. I've seen it only once or twice, but most of the time it's just one swing, negative, and that's it. And then it goes into nighttime jitters.
Yeah, and that makes perfect sense from ionospheric physics, as Carl here well knows. When you turn off the extreme ultraviolet that's actually making the ionosphere relaxes in the evening at a much more gradual pace because it's just chemical recombination. You know, the neutral atmosphere is beginning to suck up the electrons, and that takes a while. Whereas in the morning, at sunrise, you've had a low electron density because chemistry has been eating away at it all night. And all of a sudden, you turn the sun on, the temperature goes way up. And it's like there's a ringing and an overshoot. Even at the professional level, people tend to steer away from sunrise because there's so many things happening all at the same time that it gets almost impossible to understand. And Steve's results are showing that beautifully, where you just see all of these dynamics at sunrise that last for an hour or two. After that, there's been enough ionization produced that the heating is beginning to stabilize. And if you were still able to see the F region, you would see that a lot of that would begin to quiet down, although there's some residual activity. So all of this makes sense even from just a basic ionospheric physics point of view too. It's fascinating.
And there was a good comment from Dr. David about you know, the nighttime valley above the E region peak starts to go away as sunrise occurs too.
That's right too. Yep.
And there's also one that I don't think we understand very much is, you know, during the long nighttime, electrons can attach to heavy neutral molecules. So that takes them out of the absorption process because the heavy molecule doesn't, you know, move as the wave goes by. But then when sunrise hits, and maybe even it could be that just visible light can detach these electrons because they're not they're not attached very well. Yeah, there's a lot of stuff going on.
Yeah, and especially in the D region too, and part of the E region, the chemistry pathways are really ferociously complex because you're so far down in the atmosphere at that point that the ratio of the ionized part to the non-ionized part is getting so small that you're basically buffeted by the neutrals. Collision frequencies are everything. It starts to make not too much of a difference where the magnetic field is pointing. The poor charges don't get a chance to do too much before they're hit in the head by another neutral. And remember, those neutrals are beginning to rise in temperature as well because the atmosphere is beginning to expand. It's really complicated and really fascinating. And the professional models are just beginning to get the resolution necessary to actually start poking into all of this. So, you know, the stuff that Steve is doing has, for example, has a really large role to play in getting us observational data that we can try to pin some of this down with.
Yeah, I think in the past, I think we've believed that sunrise and sunset were the same thing, but
yeah,
it's pretty clear now that there's a big difference, and we can even probably relate that to a lot of observations on the radio too.
You know, another thing you might want to consider with that is that at the 2.5 and 5 megahertz frequencies, if you're looking at ground paths more than 1,000 kilometers from WWV, you're probably reflecting by the E layer, not the F layer.
Right.
Yep.
Oh yeah, and also one of the earlier
Carl's
questions.
prediction showed that.
Yeah, one of the earlier questions was about you know, the ordinary and the extraordinary wave decoupling, and you know, those plots that I provided to Steve were the ordinary wave. And as you get lower in frequency, the ordinary and the extraordinary take different paths because the index of refraction is different because of the magnetic field. So, boy, that can get, there can be lots of modes in there. And
yeah, but those time differences are a few hundred microseconds at most.
True. That's true. But Terry, it's also probably important to get people thinking about that the ionosphere is birefringent in that it's not symmetric, right? Because of the angle of the magnetic field, if I shoot a ray from me to you, and you turn around and then shoot a ray from you to me, the angle is somewhat different. So, the thing might not take exactly the same path coming back. I agree with you quantitatively. If you look at the delays between the O and the X, they may not necessarily match some of the other multipath that would change, like, okay, now I'm reflecting off the E layer instead of the F layer or something like that.
There's a comment on the chat from Dr. David Timmons that says there's also a decent EF valley in the morning for about 1 to 2 hours. So,
right.
David Kasdan, I unmuted you. Did you have a question, David?
Yeah, I do. We've got quite a collection now of 5 megahertz data, smaller one of 2.5. About a night in 10 at 5 megahertz is quite frequency unstable. What should we be trying to correlate that against?
Nighttime sporadic E.
That's what first comes to my mind too. Yeah, which is tough, right? Because sporadic E is patchy, very localized. So unless you're lucky and have one of Terry's Viper systems like in the right place, it might be a little hard to see it and correlate it with the kinds of stuff you're looking at. Terry, I don't know what other comments you have about that, but that's kind of what comes at the top of my mind.
Yeah, the sporadic E has time constants on the order of 10 minutes and spatial variations on the order of 100 kilometers. So you need a fairly large number of receivers to map out a sporadic E cloud using this methodology. But that's what HamSCI could potentially provide.
And that's of huge interest to the research community. People have been hacking at sporadic E for a long time. And honestly, to me, there's just not observationally constrained enough to figure out, people have flown rockets through it to estimate the spatial scale size where you get one cut going up and coming down, but you don't have this distributed view of it, a continuous distributed view that would, I think, help a lot.
No, we don't. We still can't even hit it with a sounding rocket reliably because
by
the time you say go, you're at T-10 with something with a 10-minute life cycle. It's moved or it's disappeared by the time the thing leaves the rail.
Yeah, roll the dice and maybe you'll hit it and maybe it will have moved a little bit or you're only going to hit the edge of it. Yeah. Whew. It's hard.
Yeah, with the Whisper and other modes that are available on 10 meters and 6 meters, maybe we can map the sporadic E.
Yeah.
Yeah, it's very...
Well, there's an interesting corollary there too, in that I know people talk about sporadic E season, especially on 6 meters being, shows up in the summer. There's another sort of peak, in December and what have you. But with the lower noise floor of these other detection modes where you're picking up 10, 12 dB, a little bit more, I know the statistics are beginning to show that people are finding paths open when you wouldn't necessarily have expected them from the conventional sort of climate wisdom about when they should be there.
Mm-hmm.
I would not be at all surprised if, as Terry said, we know this is highly patchy stuff. One last thing to mention, one of the ways that sporadic E layers form is thought to be a wind shear, okay? You get neutral winds that are going in one direction at one level and then in another direction at another level, and because the ionization is sliding along the field lines, it sort of piles them into layers. But those neutral winds themselves are very highly localized, so the patches can create and go, and you've got a very, very sharp gradient there, and nature really hates gradients. It wants to diffuse that part away as fast as it can. That's another reason why this stuff is there and gone, and then it's only here, and then it moves over here, and people like Carl for years have been saying, okay, yeah, this is cool. Why did that work for 10 minutes? Oh, yeah. Let's close.
If you're in the right frequency at the right time, man, it's great.
Yeah.
Actually, Phil, I would say the other way, nature loves gradients. It creates all manner of phenomena.
Depends on how you look at it, I guess. Yeah.
Creates uncertainty.
Yeah.
Hey, Phil.
Yes.
This is John.
What is involved with some of these weak nodes?
You're talking about sporadic E, and that kind of leads to 6 meters and sometimes 10. There's very little organized research, it seems, that's gone on 6 meters. I've listened for whisper there. I don't think anybody's regularly beaconing. I'm told that 6 meters isn't a good band for whisper. I don't know quite why, maybe just the transmission length. But is there more that we could or should be doing to think about setting up monitoring on 6? That'd be something I'd be really interested in.
I think the problem is people aren't patient enough. They want to hear
Mhm.
their signal.
Yep.
Well, but we can put receivers up, monitoring 7 by 24.
Yeah.
And one of the things I tried doing a couple of years ago was extending the reverse beacon network up into VHF. So we have at least a few places that are listening to the CW beacons and feeding those back into RBN on 6 and 2.
Right.
And I mean, I think the capabilities are there to build a monitoring network, but I don't think there's maybe ever been a reason stated why we should.
Yeah, well,
Well,
also in light of the topic of this conference, you get auroral skip off of up in those frequencies.
That's right.
Well, regarding the whisper and trying to use beacons on, say, 10 meters in VHF, what I've noticed is whisper has, I think, a 2-minute window, and my experience has been, especially on 6 meters, that the fading, QS Bravo and whatnot is such, it is really hard to get a window of 2 minutes with a very stable signal on 6 meters. I noticed this when I started doing analytics and comparing the amount of spots noticed on 6 meters from whisper to anything else. It was very generally, it was a few percent of the total was whisper.
Mm-hmm. That does make sense that the 2-minute cycle is just too long, because on 6, and some of it's meteor scatter, but stuff comes and goes extremely quickly.
Yeah. I'm going to go back to the presentation that I just made, where you have this code that's been designed, and Whisper has been designed with a certain tolerance in range and Doppler frequency on the transmissions, right? I mean, so it's a huge, vast code space. And so Joe Taylor made some decisions on what could he tolerate for spreading and what could he not tolerate. And I'm supposing it's possible that some of those paths may just be outside of the bounds where the code is going to lock up, and you just get fewer decodes.
Yeah, well, we got plenty of bandwidth up there. I would say maybe use code similar to Whisper, but much higher bandwidth.
The nice thing about Joe and Steve is that they do introduce new modes now and again. Look at FT4, so that might be a good suggestion to make to the groups that's designing these kinds of codes, is say, can you consider something? I mean, he's got meteor scatter modes, he's got MSK 144, he's got EME friendly modes, all of which have different set points and are tailored for different things. Maybe somebody needs to just say, hey, what about a sporadic E mode? That's kind of intriguing. I hadn't even thought of that before, but
that is an excellent idea. But by the way, FT8 and FT4 do work pretty well on 6 meters.
Oh,
much
yeah,
better
they do.
than Whisper.
Sure.
Yeah, FT8 is a killer on 6. That's one of the big problems. People are talking in the contest lists that FT8 has almost destroyed 6-meter SSB and CW.
Well, to me, there was a fascinating you ran into the human problem when you hit FT4, because the FT4 cycle is essentially half as long as the FT8. Now you're getting into 6-second cycles, and it's starting to bump against the human limits of being able to decide what to respond to. And so, you can't, you can't go too much shorter than that, of course, because then it's going to have to be all computers. There's just no way you're going to be able to pick that out. And I don't want to get into that topic, because there are pages filled with people complaining about computers talking to computers. But FT8 it seems like a pretty good set point for balancing a lot of different things. FT4 for contests, I guess, right? Is that right? I think that was why.
At least on 6 meters, we've not seen FT4 used really yet. Of course, it's brand new, but the rates aren't high enough. I think that that cycle time is a really big deal
Yeah.
on 6, whereas on HF it's a bit of a different world.
But the challenge to this group, if you want to talk to Joe and say, hey, would it be interesting to design another mode for sporadic E, is that you have to have the science people on this call, for example, have to pull out their knowledge of, mean, okay, how stable is this thing going to be in range and Doppler, and at least give him some boundaries so that he could figure out how to design a code that would kind of target that. If we could do that, I'm sure he'd be interested. I mean, he's generating new stuff all the time. I don't even know what he has in the pipeline right now.
Now, the other thing is that if you want to be bouncing it off of Aurora, the Doppler shifts are so tremendous. You got to be very robust to frequency shift.
Yep. And Nathaniel's example at the beginning of this was really nice. You could hear the tone at the end of that come down to a carrier, but after that, geez, there was 3 or 4 frequencies to my ear in there going fluttering all over the place. Quite interesting.
Yeah, especially at frequencies 6 meters and higher, what you're going to get is you get a lot of scattering off of these sporadic E layers, because you're not scattering off of a smooth plasma. You're scattering off a very perturbed plasma. You're doing Bragg scattering.
Yep.
And the signal fading pattern is very sharp fading patterns.
Yeah, I completely agree.
Yeah, you should, Phil, maybe you're aware that, VOACAP has an above the MUF mode. In other words,
yeah,
if the operating frequency is a little bit above the classical MUF, it's kind of, some kind of scatter that introduces more loss, but still the FT8 can really take advantage of that. And
yeah, Carl and I had a discussion about that offline a little while ago, and there's more than one theory about how you calculate the attenuation. When you're, as he says, when you're in some buffer, you're maybe a couple of megahertz above the maximum usable frequency on a path. It's not like it can't get through, but what's going to happen, of course, is it is going to get attenuated and reduced in amplitude. And until now, you haven't necessarily had a detection mode that could actually detect those paths. And I'm pretty sure that some of the reason why some of these FT8 modes work in ways that people didn't expect is that you can still detect it, even if you've hacked 20 or 30 dB off of it. And so that's another place where, frankly, you could do propagation research.
Right. Yep. Lots of interesting stuff.
Yeah, and I think we're seeing a lot of examples on 6 meter FT8 where, I'll leave my station running even through the winter and see almost nothing, but all of a sudden there'll be one decode from somebody, in a place you wouldn't expect. And I think there are these very short-term modes, as Phil said, probably with other modes, you never even would see them. But with FT8, you're able to detect those. So I just think there's an awful lot of opportunity at 6 meters to learn stuff if we can figure out the best way to do it.
Well, John, I'll bet you'd detect a whole lot more stuff if there was more people actually trying to transmit stuff on 6 meters.
Oh,
there's sporadic E out there, but nobody notices because nobody's sending anything. What we need is some 6 meter FT8 beacons or something like that.
Mm-hmm.
John, I believe you gave a presentation in a prior HamSCI conference where you were trying to encourage people to do it on 6 meters, 2 meters, 70 centimeters, and on up, right?
Yeah, this is what we call the reverse beacon VHF plus, where we really were just, and the hardware was RTL dongles that were feeding into a Raspberry Pi that emulated an HPSDR, and that could feed into the CW skimmer. So we were able to monitor the entire 432 bands for CW beacons and feed those in, but there aren't very many of those CW beacons, so that's part of the problem. And CWs may not be the best mode for this, but I mean, to the point that I think was Bill just made, there have been openings when I've had S9 plus 20 signals or 30 dB almost FT8 decodes between Ohio and Florida, and there are only 3 stations on in Florida. If there were more stations, I could have worked dozens. And it is that lack of activity that's the problem, and some kind of a digital beacon mode that we could transmit continuously and monitor continuously might turn up an awful lot that we don't know about it, particularly if we could get a density of stations.
Do we have to get some kind of special dispensation from the FCC to run some kind of special unattended beacon that's different than the current ones?
Well, why not? Why don't we just see if the IARU NCDXF beacon system can also put something on 6 meters? I don't know legally what the issues are, but
I think that the legality is, I think that the requirement for the CWID, and there are some stations, some beacons, I think mainly in Europe, that are putting out a combination of CW and FT8 or PSK31 or some sort of digital mode. So I'm not sure that the legalities are necessarily what would hold us up. It's really just defining the best format. And you may have to throw a CWID in every so often, but that's not hard to do.
Well, John, you said you used an RTL dongle so you can receive all the bands at once. What do you use for transmit?
Well, the VHF plus RBN was receive only. We were listening to the CW beacons that were already on 6.2 and 432.
But it seems like part of the problem is you're saying there's not enough stations.
We need beacon transmitters with an optimized coding, and we need receivers. So you got to have both sides of the equation to make it work.
David Kazan had his hand up a couple of times.
Thanks, I appreciate it. We've been trying for a while to get a network of collegiate amateur radio clubs on Whisper. We got some traction with it during the fall semester. Case and University of Michigan were doing whispering on 10 meters and on 6. It seems like a very good project to me for the college stations that are trying to get back on their feet, don't have much money, don't have much antenna space. And we did get some interesting results. There were some remarkable 10-meter openings at times, the usual statements don't predict it. And we had actually kind of a hard time getting just across Lake Erie between our two stations. So for what it's worth, 10 meters and 6 meters for a collegiate network does seem like a good bet to me.
There's a interesting comment from George. How can you tell even that a band is open just by listening to the noise on the band? I think we have a good example of claims that can happen by a fellow up in VE7, but I'm not sure, noise, just noise tells you if a band is open or not. What are your thoughts on all that, guys?
Directionality?
Is that really the question? Let me go read it again. Oh, by the way, there's another question at some point, Carl, about FT8, but let's finish this. He's saying how an experienced operator can identify signals as being distant and not local based on how the signal sounds.
No, the one before that at 2:06 p.m.
Oh, sorry. Yeah, he's just written another thing.
Okay.
He just says, as a human, the band sounds different when it is open.
Yeah. On the other hand, if you're on, what is it, 15 meters, you might be hearing Jupiter.
Yeah, that's inconvenient.
Well, I have seen algorithms that
this blanket statement that if you hear noise, the band's open.
Yeah.
Well, I have seen things where people measure the total amount of energy in the band, and then that can be correlated with the band being open because you're seeing a bunch of signals in there.
Sure. No, that's very true. Yeah, but as somebody said, there's more than one noise source at 20 to 25 megahertz, which can be really pretty screamingly loud, depending.
But when the conversation was about sporadic E affecting 5 megahertz WWV monitoring, I would have thought that was too low a frequency for sporadic E. Am I not correct?
Not necessarily. It's going to depend on the density of the patch. And, frankly, David, I don't know that we know as much as we should about the density of those patches. If a sporadic E layer is in the process of breaking up, where it's actually diffusing away, it very well could get to the point where for a defined period of time, 5 megahertz works.
Yeah, if the density is high enough, could 5 megahertz be a specular refraction or reflection?
You know,
it could be specular because there's almost always sporadic E there, and sometimes the E layer is higher, but at those heights, the M factors are on the order of 5 or 6. So it doesn't take much ionization to complete a 1,000-kilometer long path.
Yeah.
Right, because a 1 megahertz equivalent, you know, FOF2 is not very much density. That's 10 to the 10th per cubic centimeter, if I remember correctly, Terry, as a cubic meter, as opposed to, you know, 10 to the 11th or 10 to the 12th. It's pretty small. It's
Aren't
pretty
you going
small.
to get a lot of D-layer absorption at 5 megahertz?
Always.
So
whenever the sun's up.
So,
but that doesn't mean that doesn't mean that it's always so much as to crush your ability to see it, though. That's the interesting thing.
Yeah, because you know, even on 160 at local noon here in Fort Wayne with a kilowatt and a good vertical, I can talk to stations on the East Coast on CW with a good station. So one hop is lossy, but during the day, but it's possible.
And Carl's written.
WWB has no power.
Yeah. Carl's, by the way, written several articles about this on his website, which I recommend you take a look at, because I know you've had a bunch of, you know, either anecdotal or otherwise direct reports. Hey, this happened for me. Why did it happen? And if you go do the analysis and you make some assumptions about attenuation, sometimes it is doable. The D-leader doesn't always kill everything.
Yeah.
Hey, gentlemen, this is Tamitha. I've been listening, kind of lurking, and I apologize, I don't have my camera on at the moment. But I just want to let you know, hopefully most of you guys know me as the space weather woman. So my angle is a little bit different than yours. But what I am doing right now is I'm working with meteorologists, training them in broadcast space weather. And one of the things that came up that I've been talking about with Nathaniel quite intensely is the idea that with these local television stations in all these different communities, let's just say in the United States for the moment, these meteorologists are getting TV gigs, and a lot of these stations have rooftop, you know, capability. And if we get something like personal weather stations for these television stations, they have their own, you know, terrestrial weather stations sitting on their roofs typically, or they have a specific location for those things. If we are able to plant or get them to plant a personal weather station, space weather station, right alongside their normal terrestrial weather station, that kind of thing doesn't seem like it's all that far-fetched. What becomes the question, however, is from listening to all of this discussion, is if you guys had a wish list that is obviously not so big, not a shopping list, but a wish list of the best frequencies, whether it be a beacon, you know, transmitter or receiver, what kind of frequencies and what kind of transmission would you like to have, would you like to see on these weather stations if they were, you know, let's say television stations? So you had them dotted pretty much all over the map. And what would be the most beneficial? Is there a way to put something like that together, or is that something that you guys would be just hashing out and arguing over incessantly because there's just so many choices to make?
Tamitha, this is Phil. You know, there's certainly a lot of different possibilities, and I mean, what you've been hearing already is that we tend, because we're limited resource, we'll tend to get focused on one particular direction because it's either low-hanging fruit or somebody has this really strong interest, even from a hobby point of view, that says, hey, if you gave me X, I really could use that right away. So we should talk more in this group collective about that, because it's a balance between what the science folks want and what the operational community would like. And there's lots of settings in the knob, I guess is what I'm trying to say.
That's what I wanted to just kind of bend your ear a little bit about, because I'm hearing that and I'm looking at you guys and I'm seeing all this, you know, back and forth about what would be best and how do you use it and what is it good for. And yes, I mean, obviously I'm looking at it from an operational point of view because, you know, I care about the first responders and I care about being able to do a now, even just a now sounding of the ionosphere in local regimes. And that can be done. But it is a slightly different angle compared to the typical research that HamSCI is really, the academic side that you guys are kind of bent towards. So
Yeah.
please keep that in mind, and just think of that as an also, because I am training broadcast meteorologists right now to start doing space weather broadcasting, and a huge aspect of that is this community, the interests of this community. So please keep that in mind. I need that information from you guys. So, I know that's a tall order, but the more information you can feed me, the better I can serve you.
By the way, Tamitha, so Jerry Krieger just wrote a note while you were saying that says, let's think about tagging onto the Citizen Weather Observing Project, which obviously Jerry is quite heavily involved with, in the meteorology community. So there's probably, there's got to be some way to fuse a little bit of the legwork they're doing there, rather than just kind of reinventing wheels.
Absolutely.
And who knows?
Hi, I'm back. Yeah, I think that sounds good, Tamitha and Phil. I think for these sorts of questions, the more involvement we have from you, Tamitha, and from Jerry, we certainly have a lot of people involved right now doing the engineering side of things with Tapper. We do have, like you said, we have a very heavy branch of people working on the science side of things, especially from Phil and myself and a number of other people. I see Terry on the screen right now. But yeah, if we get more people showing up and from the space weather community saying, yeah, like you said, what do we need? What's the best thing? If we get some people kind of working on that problem and representing that community here at the table, then we will be able to work those questions out sooner, I think.
That may be something that you want to schedule a specific meeting for and have people ponder that question, prepare their ideas, and then we all have a discussion and put something together.
I think a lot of it too, it's not just scheduling a meeting, it's really having a person, kind of fight for their interest. So like my interest has always been like HF. So that's one of the reasons the personal space weather station is so HF focused, because that's where my personal interest is. It doesn't mean that sporadic E is less important or more important, but at higher frequencies, but that's where my interest is. So if we get, some people like Tamitha or like Jerry, or if they had a student that they wanted to come kind of represent them and participate in these discussions, then that particular area will naturally get more attention paid to it.
Yeah, thank you, Nathaniel. That's a good point. I will tell you flat out right now, the best angle for me to be able to help the ham radio community as a whole is to go where the meteorologists believe that space weather is relevant to the ham radio community, which means first responders, FEMA, Red Cross, anything that is using emergency frequencies. So, during hurricanes, during natural disasters like earthquakes, things like that, going into the academic range or going into frequencies or sounding, checking out the beat, seeing whether or not 6 meters is going to give us something different during sunrise compared to sunset with Doppler and everything else. The meteorology community is not going to care.
Yeah.
So, I'm going to have to. Unfortunately, my pipeline will be very, very constrained, simply because what I have to do is get a foot in the door with them.
Yeah.
And that specific needs being met.
Well, maybe one thing we can do is, as I said, we had to pick a theme. We have to pick a theme each year for the HamSCI workshop. So this year's been the Auroral Connection, working with Aurorasaurus and trying to branch up into high latitudes. So maybe our theme for next year or the year after, next year would be great, since we are doing personal space weather station, to try and theme the meeting more along the lines of what you're saying.
That'd be interesting, Nathaniel. Maybe we should talk about that some more. Of course, obviously, I don't want to have your whole HamSCI workshop be hijacked by a space weather person.
Well, it's not a matter of it being hijacked. Like, we try to blend these themes. So like with the Auroral Connection, you can see that, we have a substantial part of tomorrow, Saturday, featuring both aurora and auroral physics and auroral posters. But we still have today a lot of being the personal space weather station and personal space weather station meeting. So there's a lot of things that, I think it's good to have kind of a theme that's kind of new and novel that, brings spotlights something. And then we still have our core purpose of these more general science discussions and the science, personal space weather engineering portion as well. So I actually think doing, talking about a theme of addressing this space weather would be a good theme for a future HamSCI workshop.
Fantastic. I'm all
And Tamitha, this is Phil, and we, that would have to be from the start very closely coordinated with what you're seeing is not only the thing you just saw that is important, but where your medium to future track is on how you figure you're going to continue to get engagement and traction in that particular community. Because I agree with you, that's where the boots are.
Yeah. And it's also something that's very much of interest to the amateur radio community, I think, too, because many people in amateur radio are involved from an emergency operations perspective. That's often how we justify the existence of amateur radio. And a lot of hams are just very interested in operations in general. So I think it could be a really good focus for a meeting one year.
Excellent. Yeah, and a lot of people know probably that I am now teaching, officially a professor at Millersville University, teaching broadcast meteorology, even a graduate curriculum that's going to be a certification, and hopefully it will be adopted by the AMS. That's the long game. I'm actually on an ad hoc committee for the AMS, for the American Meteorological Society, to get a space weather certification built so that meteorologists, working meteorologists, can get a certificate in broadcast space weather called a CCBM. And the Millersville program is the baseline point of departure for that endeavor. So the neat thing is that I'm now really entrenched in the meteorological student community. And it is amazing when I talk about space weather for the modern meteorologist, how many of these young students get their minds blown realizing that they can add space weather skill set to their terrestrial meteorology skill set and be that much more of a specialist and that much more needed by just television stations and being station scientists and that type of thing. So it's being adopted very, very vigorously, and it's being encouraged. I mean, the students are being very encouraged by what I'm saying. So I don't think we are going to have to hunt very hard to train these students. I think they're going to start looking more for space weather and for reasons to have space weather skill set. So this is coming fast and furious. And this is why I really appreciate, Nathaniel, that you might want to think about this as being a theme, at least a partial theme for next year.
This is Jim Secan. I've been what is being called a space weather person since 1972. So I've seen this business grow from nothing into what it is now. My one concern with all of this about engaging a bunch of students, this is a niche market. It's an interesting area. I will throw in a couple data points. I had been receiving ionospheric data from the Space Weather Prediction Center in Boulder since 1997. Mm-hmm. Last month, they decided just out of the blue, oh, we're not providing that data anymore, because the ionosphere is really on the outside as far as a lot of space weather people are concerned. The ionosphere is this thing that's down here, but it's not as sexy as the aurora and up into space and the magnetosphere, and especially the sun, this big thing that does flashy things. The ionosphere is, that's the thing that those ham guys like. DOD, as somebody pointed out in the chats, they're interested in the ionosphere because of OTH. There are a lot of unsolved issues in the ionosphere as far as OTH is concerned. TIDs are a big thing. Mid-latitude structures such as sporadic E, which is still not well understood, as is mid-latitude spread F. These are very interesting topics for a very small number of people. So yes, it's interesting. If I had students, I would suggest they might want to broaden outside of space weather, because I don't really see it as an area that there is a lot of room for new people. There is some room. It's an aging group, as you can see by the beard, but I would hesitate to drag a bunch of new students into it. Or at least if I brought them in, I would want to make sure they understand what the real world market looks like.
I appreciate that. You might not know that I work for the Aerospace Corporation, so I'm very intimately familiar with AFWA, with the 557, and what the Air Force needs and requires of NOAA, and how NOAA is hamstrung to provide certain data. I'm very familiar with all of the scientists at the Space Weather Prediction Center. I'm close friends with many of them. Most of them are my colleagues. So I am very, very acutely aware of the issues that they face and of their knowledge base and the knowledge that they have and that they don't. Most of them do not understand ionospheric propagation at all because it's not their bailiwick. Their bailiwick is solar and space physics. So they worry more about NWO. They worry more about taking the models from the academic community and translating them into operations. And they have such a thin budget, and they're so hamstrung. It's not even worth talking about. So yes, I am very aware of those things. What I am trying to do, however, is create a civil, basically a civil version of the Space Weather Prediction Center. I don't have any interest in serving the needs of government partners and agencies. I don't want to be the NWS. What I want to be is something more like what I guess AccuWeather, from that point of view. There are a lot of civilian uses of space of signal data, for example, GPS, GNSS, the drone industry, the pilots, ADS-B is being adopted far more rapidly than I'd like. And people have come out of the woodwork towards me and with me in a complete grassroots movement. The need for civilian knowledge and awareness of space weather is unbelievably large. And I have been inundated. As a matter of fact, over the past 5 years, I can hardly keep my head on straight because I have so many people that are tugging on me this way and that way to learn more about it and figure out how to create better data products that SWTC basically can't make. So I am not interested in creating more scientists. I am interested in creating a field of broadcast space weather that is basically about communications. And it's about getting the public aware. And it's going to happen in meteorology because it's not, the scientific community is not interested and there is no room. So it's going to be coming from a totally different angle. And frankly, it's growing very quickly, but it's also very haphazard because no one's ever done this before.
And Tamitha, Tamitha, you're also not saying that you are trying to drive people to have their entire careers necessarily in space weather broadcasting, but you're also trying to just say for the regular meteorologist or broadcast meteorologist that everyone should have some sort of literacy in this. Isn't that right?
Yes, and it's a skill set. It's a skill set that they add onto their terrestrial meteorology. It's just
Tamitha, this is Phil. I had a question for that. In any field where you're trying to adopt something new, you want to get over the critical mass so that very, very crassly speaking, you want the arms race happening where a department says, I gotta have a space weather meteorology program because University X that's bigger than I am in US News and World Reports does, and I can't be seen to be left behind. If you can get that seated and happening, then pretty much you get bang, you get, departments in most places. Where do you see us on that track?
That's hard because how do I calibrate myself? Well, several years ago, the late Matt Parker, who was the president of the American Meteorological Society, reached out to me on Twitter and actually pulled me into the AMS, and I became a member. He introduced me at that time to quite a few different meteorologists and opened my world to how similar space weather what space weather is compared to meteorology or to broadcast meteorology in terms of what I was doing. And unfortunately, he passed on before we were able to really get very far. But he did introduce to Professor Rich Clark at Millersville. And right now we are, we started this curriculum literally not even 6 months ago, and the class is already completely full. We did a study, and I guess I could share that with the HamSCI community. We did a study for the AMS, pinging just a small group of people, about 100 people inside the AMS who are meteorologists, who had an interest in space weather or had some understanding of it. And we asked them various questions like, where do you see the market? What is the need? Is there an unfilled need for space weather in your place of employment? We had about 10 different questions that we asked. And we came back with about a third of them saying that yes, there is absolutely an unfilled need. And we came back with about 80% of them saying we want to learn more. And the only people who basically said they didn't want to learn more were people who had masters and PhDs already. They already had the skill set. So we were very surprised. And that's why the AMS actually asked me to create, to lead an ad hoc committee to determine whether or not a certification in broadcast space weather is something that the AMS needs to look into. So there is a push here, and it was not all initiated by me. I was pulled into it simply because of the work that I do on social media. And that's pretty much the way things have continued. So it's very difficult for me to gauge. I would say we're early on in that track, but I guarantee you it's going to be something that's going to change by 2024 when the sun starts working again.
Terrific. Sounds great.
Yeah, Nathaniel, we can discuss more of this stuff. Maybe I can give a talk at the next HamSCI or something to kind of bring everybody up to speed as to where we are in developing this field, because it sounds like that is going to be of great interest to this community.
That would be great. Yeah, we'll talk about that some more.
Returning for just a second to Tamitha's initial point, I don't know if Skip is still on the line, but as kind of an instrumentation person, I find myself thinking of the construction of the big telescope at Green Bank, which basically came out of a meeting where a bunch of radio astronomers sat down and said, okay, hypothetically, if we had infinite money, what would we build? And they wrote up this description. And then when they had the catastrophic failure of the old telescope and happened to have a very supportive senator, they were able to just pull those plans out and use that as the starting point for the execution. It seems to me that we've got a lot of really interesting ideas for instrumentation networks that people would like to see that fall under this umbrella of personal space weather station and related notions. And I'd really like to see HamSCI start putting together a page or a repository or a single spot where we can look at it and scientists can say, hey, I'd really like to see analysis of this phenomenon, and I think that this would be a good technique for exploring it. And we can start to have HamSCI be an arbiter of sort of that pathway from the point of scientific interest to the technical approach to the citizens and the volunteers who are implementing it and recording that data. Yeah, so
Well,
I think it'd be interesting if HamSCI started organizing that.
Once you get the network built, wouldn't it? It's just a matter of trying to decide what you want, what information you want to collect, right? So how do we sense it? And we already have the mechanism to collect it and put it into tag it and put it into a repository where everybody can get access to it. So what is it we want to collect? That's the question in my mind. And that might be a good subject for next year, because we'll be pretty much done with the HF portion, and we'll be maybe looking for additional hardware to collect data that we don't know we need yet.
Yeah, but I think Christina brings up a good point, and it's something I've been trying to do in organizing these workshops too. Like if you look at the structure of the workshop, the beginning talks this morning, they were all engineering talks, all the technical, how do we design this thing? How does this thing work? What is the number that we need to have the precision time measurement, all of that stuff. And then after we got through those team reports, you started seeing some examples of how we might analyze this data. Over the past couple of years, I've shown examples of how you can analyze WhisperNet and RBN data to see solar flares, and we're going to see an example of some TID work I've been doing with that this afternoon, and that my student has been doing. And then, we now see the Doppler shift work that you, Christina, and the other Case Western people have been doing, and that let's see, and that Steve Serwin is doing, and Phil Erickson has been showing examples of how we can use the FT8 signals. So we're starting to get a collection of different ideas on how to use this. I think the path, so I mean, maybe what you're asking for is to have a better way of curating that, and I think it would be nice to have that over time. What I'm hoping is that as we can attract a few more of these discussions and flesh out some more of these ideas, and then we really need to pick a few concrete ideas and really implement those. And I think some of the ones that we have already, I think the Doppler shift is a real winner. It's a simple measurement. You can do it with the low cost system. It's very convincing. Not a lot of other people are doing it. Just the way in your plot, when you showed that video of the Terminator just moving in time, when you made that movie stacking one day after another over a period of months, you could now see, you could start to see a pattern in those waves that we remember. If I remember your presentation from last year, we couldn't see that sort of pattern, but now we're starting to see something. You'd say, oh, this looks like it's geophysical, that's leading on to something. So I think we just need to keep moving along those lines. And I do want to say, to help out with this, I did just hire a postdoc who's been listening this morning, and his name is Dev. I mentioned him earlier. So his specific job is going to be thinking about what are the best analysis techniques for us to do with these software-defined radios. And his job is supposed to help you at Case Western, figure out that analysis technique. That's one of his jobs. Another job is going to be using the Tangerine SDR. What is the best, or what is a really good approach to doing a data analysis? So we're starting to get some people who have more advanced research degrees thinking about that problem. And then it's just, hopefully it'll just snowball from there. We do a few concrete things and give some good examples. And then like Scotty said, once, in addition to the concrete things, we just save the data, tag it properly, show the rest of the community, not only do we have these concrete things, we also have this data repository, and we can get other people's ideas. What do you think about that, Christina?
Yeah, that's pretty much exactly what I'm looking to do. Should Dev be our point of contact for getting some of this stuff into a recorded public form?
Well, Dev's not going to officially start until May. We have some more paperwork that we need to get cleared before we have all that, before he starts officially. And once he does start officially, we can start talking about exactly what his role is and things in that form.
All right, awesome. Looking forward to it.
Yeah, I would say for you that the best thing to do is just, I think you're doing a really good job with the low cost system. I think the plots you showed this morning, I thought they were very nice with the showing those TIDs. Yeah, no, they look great. So I think you're on the right track, and I think we're starting to come into focus. And one of the real key things that, as I said, I don't know if you remember when I came to Cleveland last year, and you were starting to show me some of those things, and I said, well, this is one day. Okay, great. What does another day look like? Do you remember me asking that?
Oh yeah.
And I'm like, and we didn't quite understand, how to sense everything. But but now you're finally able to show a plot where you can start seeing a systematic change, and you can see how one day relates to another. And then you can start relating that to like, okay, that makes a clue as to, okay, this really is due to a day-night variation and not just, we're starting to be able to tease that out. So the next question might be like, okay, you have your receiver in Cleveland doing this, if you send me a receiver and I put it up here in Scranton, do I see the same patterns? And then, and if I do I see the same, like, I think if there's an uptick in the noise at night, right? You know, do I see that same thing here? And is that something that's locally generated by like man-made stuff just because people, you know, go to bed at night and some sort of equipment turns on or something that causes that noise? Or is it really geophysical? Do we see that at every single location? You know, you take these observations. And if you do see it at every single location, you take these observations around the world, and you can start to say, well, how does it vary a little bit? And you can start to pull apart and finally answer, okay, what's actually causing that particular signature?
Yeah, that's the idea.
Yeah.
And what I'll add to that, I think we are about ready to start that line along the Great Circle Path from Fort Collins through Cleveland, extending to the East Coast, so that we have a whole bunch of simultaneously recorded data that are rarefied in some way, this time in the path, to compare and correlate. We have some people identified, and I think we need to find more.
And this is the that notion that we're getting at with this idea of the frequency analysis network, is that the best way to do this is definitely going to be to set up the data collection right and to do it once. And to start picking out some stations so that we can do that.
Yeah.
So yeah, at the moment, I'm really interested in getting stuff standardized early. And I think the part of it that I feel the most trepidation about is being able to extract useful information from the data. But I think that the first of several answers to that problem is to get more data.
Yeah, I think there's a couple answers. One is more data for sure. And two is to keep, you know, where you can refine things a little bit, keep refining the process. Like you said, that standardization is very important. And to think about different ways to organize the data.
Yeah.
You know, that becomes really, really critical because with my solar eclipse QSO party paper that I wrote a few years ago now.
I remember you showing me the first your first pass of the data for that. And it didn't show up at all.
It's actually really, you know, it's really interesting. If you go back to the HamSCI Facebook page right now, let me see if I can bring that up. You still see a movie, I think, of when I first, you know, some of the first views of the data. So here's the HamSCI Facebook page. Let's see if this movie is here. Yeah, there it is. Okay, right. So this is one of my very first views of the solar eclipse data.
Wow, look at that.
Right, and all of that nice eclipse that you see in the background, that's just calculated based on the shadow of the sun. That's not actual data.
I don't think I'd seen that one. That's really amazing.
But okay, so that's the solar eclipse QSO party, the logs. That's WhisperNet. That's PSK Reporter, and that's Reverse Beacon Network. And it's color coded by frequency here. And how well do you see, you know, the eclipse signature in that?
Wow. You know, we have an interesting found experiment to do. We have collegiate ham radio operators all sitting at home bored all over the United States.
Very, very bored.
Yeah.
We really, the next month is our time to distribute this stuff and get some data collection in place.
Yeah. Well, I'm afraid we're gonna have to start. This has been an excellent lunch discussion. I have to say, I'm really enjoying these break discussions. I think they're a lot of fun, and I think they're actually some of the best part of the conference, the workshop.
I'm pleased that we're not totally losing out on them by being online.
I know.
But there is a question, I think, directed to you from Asti Bhat.
Oh yeah, Asti. Hi, Asti. Some science opportunities, combining HamSCI data with other instrumentation. For example, we run a network of F-region airglow imagers across the US called MANGO, which I'm familiar with. We routinely observe these types of ionospheric structures waves for night side TID, combined MANGO HamSCI investigation would be very valuable. Yes, Asti, we would love to do that. And later this afternoon, Diego is going to be, he's one of my students. He's going to be showing some TID ham radio data that I've worked on with him and Gareth and Carl Letchel-Swab. You know, we've all been working together on that. And that's potentially a good thing to combine with Mango. So we should definitely talk about this more. I would very much like to do that.
Nathaniel, is this HF type of data?
Yes, it is. It's the same data I showed at the Tapper DCC. I gave a presentation on LS, large scale traveling ionospheric disturbances, using reverse speaking network and WhisperNet. So I would love to continue this conversation, but we are actually coming up against the end of our break. So Gareth, are you about ready?
I am about ready.
All right, so just hold on one second. We're going to start our next presentation. We have two new moderators now. So it's going to be Laura Lukes and Dr. Laura Lukes, KK4 FYT. She's from the Eclipse Mob project. She'll be one of the Zoom moderators, and Dr. MD Maktoumi, he is a professor here at the University of Scranton who specializes in RF microwave work, and they will be our moderators. So I'll let Gareth, you can take it away, and I will give them moderation power while you're talking.
Awesome. So, okay, well, welcome back from lunch, everybody, wherever you are. Let me share my screen. My audio is okay? Everybody can hear me clearly?
Yes, I can hear you just fine. Thank you.
Good. I'm going to go ahead and share my screen. Okay, everybody sees that all right?
Looks great.
And how about that?
Also looks great.
Awesome. Well, hello, everybody. My name is Dr. Gareth Perry. I'm an assistant professor at the New Jersey Institute of Technology, and I'm going to be updating everybody on the Golden Ears project. Don't worry, in this talk, I also just talk about what the actual Golden Ears project is and then update you on it. I'd just like to acknowledge my co-authors here. So there's me, KD2SAK, there's Phil Erickson, Bruce Blaine, K1BG, and Bob Reif, W1XP. Those two individuals are citizen scientists featured in this talk and some of their work. They're from the Neshoba Valley Amateur Radio Club that's up in Massachusetts there. And then, of course, Nathaniel is the last co-author, last but not least, of course. And yeah, it's unfortunate we couldn't all be together in Scranton. So I guess, you know, I'm broadcasting from Montclair, New Jersey, northern New Jersey, just west of Newark here. Good to be with all of you, but let's get started. So I'm going to be showing a bit of data from a Canadian satellite that I worked on as a postdoc, and I still work on now as an assistant professor at NJIT. It's the Cassiope satellite. It's got a couple of names. Some people call it EPOP. Some people call it Cassiope. Some people call it Swarm E. But essentially, Cascade stands for Cascade Smallsat, and Cassiope stands for Cascade Smallsat and Ionospheric Polar Explorer. It was launched in 2013 by Elon Musk into a nice polar orbit there. And EPOP is the suite of instruments, which is the science payload. Originally, there were 8 instruments. Now, still about 5.5 work fairly well. And really, the science objectives are to look at wave-particle interactions in this energization process at really micro scales, or really very small scales. So really, the EPOP package on Cassiope is designed to study space physics, or the ionosphere, in these very concerted burst modes, these very short campaigns, because it's going to be collecting a lot of data at a high sampling rate. So there's you know, the acronyms on the left here, if you can see my mouse cursor, of all the 8 instruments. And I'm going to advance a slide here. The one instrument I'm going to be featuring that I've worked with exclusively really is the radio receiver instrument, the RRI instrument. This is a digital radio on board Cassiope, and it is consisting, you can see on the front of the spacecraft there, the 4 3-meter monopole antennas. And really, we're looking at radio emissions that are natural and artificial with this. We sample at 62.5 kilohertz, which is IQ sampling, and then that's passed through a 31 kilohertz, anomaly about a 31 kilohertz passband. And again, we're targeting natural and artificial emissions. Natural meaning Whistler waves, or aurora, auroral hiss, auroral roar. And then artificial is we're looking at our radars, over the horizon radars. HARP is another target we look at. And what I'll be showing you is the CW band at 40 meters. And so one thing I didn't mention here was that we're able to actually tune this digital radio receiver from as low as 10 hertz all the way up to 18 megahertz. Okay, so we can tune that 31 kilohertz passband over. It may have a lot of nice agile things we could do to sample different bands at different times. And we can also tune these 4 monopole antennas into a cross dipole configuration to get other nice information such as polarization, or we can tune the dipoles to different bands if you wanted to. One, say VLF down at 30 kilohertz, and another one at HF if we wanted to monitor 2 things simultaneously. So there's all sorts of stuff we can do and we have done with RRI. So here's just a basic kind of schematic of the cartoonish thing of what we do with RRI. We have our spacecraft in orbit, and we have all this ground instrumentation below it. We have all sky imagers, ionosons, our rheometers, magnetometers, so on and so forth. Of course, we have the atmosphere and the ionosphere, or the bulk of the ionosphere below it, and we move the satellite through, or orbits through, and we can transmit from HF sources, or we can tune into VLF sources here. So right in the bottom left corner of that schematic, imagine that HF VHF radar being a ham radio enthusiast, right? A ham in his shack or in their shack, tapping away at a CW key. That's the kind of picture you should have in mind for the bulk of this project, or bulk of this talk, I should say. So we've done some work in the past with RRI, with EPOP, listening into amateur radio, listening into field day. And so for those that aren't aware, the ARRL has a field day exercise. All the hams in the US and the bulk of the world, I think, actually, kind of join in. And it's a large scale emergency preparedness exercise. Everybody kind of gets off the grid, kind of partakes in contests to make sure that they know how to run their hardware, and they can operate off the grid as in an emergency where you may not have power, so on and so forth. But there's a lot of contests, meaning there's a lot of people on the air, and the CW is one of the modes, right? The CW, or a Morse coded signal, is one of the modes that are very popular. And then they run contests, so a bunch of people get on the air and do their thing. We had an opportunity in 2015 with EPOP to actually activate the radio receiver instrument for just a couple of minutes over the United States, over Chicago, essentially, to listen into the CW band, and we could actually start doing some radio science and some space physics work with the signals that we were seeing. And so we actually published that. So we have a long history here now. It's been 5 years almost, between the formal science community and the citizen science community through EPOP RRI. And here's just a sample of what we picked up during the 2015 data. Here's just a snippet of RRI's sampled signal. And this is just a Morse coded, this is the CW in Morse code of K9 ESV. And then FD stands for field day. I remember when I decoded this, I had a Morse code translator on Google, I think I pulled up, and I pulled out K9 ESV, and I'm like, oh, I can actually see the dits and the dots in the Morse code. Then I looked at Nathaniel, or I phoned up Nathaniel. I'm like, what's this FD mean? I'm, an ignoramus when it comes to the CW. And he goes, oh, that stands for field day. And I was so relieved because I was so scared that I had done something, or worried that I had, done something really stupid somewhere. But, it just shows that we can actually really drill down to the dits and dots of each pulse, and actually, it's a bit of a blurry picture, but you can see that there's actually even more and more detail on top of each one of those dits and dots. And we can actually go in, and what we did in the paper was analyze those little oscillations on top of the dits and dots to pull out that we were observing. We could measure multipath propagation with RRI from K9 ESV. So that was a nice result. So we can actually do, hopefully to convince you that we can do some really cutting edge ionospheric physics and some plasma physics, really, and radio science with RRI and with amateur radios and hams. So we did it again a couple years afterwards, and then we did it again, I think, in 2017 and 2018. And then we did the same kind of experiments, but we scaled up in 2019. So whereas in 2015, when we did this field day exercise, where we eavesdropped in on field day with RI for just 2 minutes, and we got a lot of data and a paper out of it. In 2019, we listened for, I think it was closer to, yeah, it was over an hour. So we had consecutive passes over days, and here you can see just the ground tracks of all the days for 2 consecutive nights. So we had some daytime and some nighttime passes, nicely kind of bracketing the continental US. You got the West Coast covered there, and then you got the East Coast covered there. So we did, we kind of scaled the experiments up, and we got lots and lots of coverage. And we started looking at the data, and here's a bit of the first look of one of these passes. So this is the June 22nd pass at 21:35, 14 UT. That's when it started. So I just want to scroll back and show you. It's this. I don't know if you can see. It's the track that starts just in the center of the continent there, and it kind of goes into to the southeast. And this is listening in on the 40-meter CW band in Ham. And our RRI, this is one of the dipoles tuned to 7.025 megahertz, which is in the 40-meter band. And we're looking at just over 7, maybe close to 8 minutes of data. And this is a spectrogram, right? So it's like a waterfall plot on its side. And what you see is all these going left from right. You can see all these little dits and dots, and that is the CW band as sampled by RRI. So you can see it's incredibly packed in. There's lots of information there to kind of unpack. There's lots of conversation and QSOs going and everything. So it's a very, very busy band. You also see a lot of these streaks going through that look like noise. That's what I call them now, just noise. They could be an actual important signal to somebody, but for now, they're not important to me. So they're the definition of noise. And you can see lots of nice variations here. Going from left to right, we're going from high latitude to low latitude geographically, and you can see how we enter into this kind of this loud cacophony of conversations on the CW band as we kind of proceed over the continental US, and actually more than likely kind of go equatorward of the aurora oval, which may just kind of disrupt a lot of these comms. And at the very equatorward edge on the very right side, you see this kind of washout, and this was actually a signature that's very common along all these passes. It kind of varied in latitude, but we haven't looked too much further into it, but we think we may be seeing some sort of a geophysical auroral boundary or a geospace boundary kind of imprinted or showing up in this HF signature. And we haven't really dug too much further into it, but we got lots of signal. So we're really excited about that. But how do we actually go ahead and attack that signal? So what we did in 2015, I'm just a tech. I only have my tech license. I don't really know CW too well. So what we had to do was take the RRI data, throw it over to an audio file, and Nathaniel and Ethan Miller and a few others kind of orally by ear decoded some of the call signs that we heard. And then we went back and tracked down all those individuals to confirm their location and did all that analysis. But if you remember that plot I showed previously, that would be a lot harder to decode of a couple of people to go through all that band and slowly decode. There's 10 minutes of data there, slowly decode all that data. And so, the 2015 technique worked for if we had, 5, 10, 20 people on CW, hams on CW. Now, if we have hundreds like you saw previously. So we needed a better way. We tried to use skimmers, which is this software technology. It's really sophisticated. It's incredible. It's what they use for, the RBN and stuff to actually decode the call signs in almost real time, in real time from receivers that you could, use to kind of eat up that band and then spit out what the call signs were. However, the difficult part is the skimmers we tried to run in 2015 failed. They didn't work too well. And the reason is because the flutter on the signal is too noisy. We believe it's just because the signal that has passed through the entire ionosphere instead of just more or less reflecting off the bottom side is far more scintillated, and therefore the software can't really account for that. So we do have to kind of stick to this cumbersome, this manual oral decoding technique. So how do we, go from there and scale up to start attacking using this oral decoding technique to all these other, these hundreds of these jam-packed signals with all these data. And so we got the idea, I think this was really Phil's idea, Phil Erickson's, so I'll give him credit for it, but he said, you know what, we should just try and do this in a more automated way, find some golden ears, which are individuals who have really good hearing ability to really good experience at decoding CW, and try and almost work them against one another, try and see who can decode the most in the short amount of time, or trying to make it into a contest. And then we'll get them just to fill out what they hear on some spreadsheets, and then we could start from there and maybe try and scale this up. And so that's what became the start of the Golden Ears Project, which is what we're calling it. It's a project where we're going to give, and we've just started the initial parts of it, we're giving some golden ears, some volunteers, select for now, some data and some spreadsheets, and we're asking them to slowly go through it and tell us who was there, almost like what we did in 2015, but with the hope that we can scale this up to have many individuals listening to the similar bits of data, so they can, cross confirm and everything. Another thing that's nice about the Golden Ears name is I completely blanked on this until recently. I'm from British Columbia, near Vancouver, the suburbs, and there's the Golden Ears Provincial Park, and right in the Fraser Valley where I grew up, and that's Golden Ears Mountain, so that's a shot. So if there's ever going to be a logo probably for this project, that's going to be it right there. You see the Fraser River, which is, I grew up on the banks of the Fraser River, is kind of in the foreground there. So there we go. It all kind of comes together nice. It's a perfect name for a project, in my opinion. Let's just make sure the project is worthy of the name. So here's how we do, here's what the methodology has been so far for this Golden Ears project. I showed you that large spectrogram of all that CW signal. What we decided to do is we would channelize that whole band. So it's about a 31 kilohertz passband.
5 minutes.
Maybe a little bit wider. We channelize it, meaning we're just going to filter little 500 hertz chunks of it, and we're going to step through in about 450 hertz increments. And we take that channelized data and we put it into a wave file, like a wave audio file. And we have that audio file be 2 channels. One would be the one dipole, and the second channel be the second dipole, because remember, RRI is a cross dipole configuration. And then we send this data, or we leave it in a kind of a shared directory, so that our Golden Ears, which are Bruce and Bob in this case, to at their leisure, listen to it, comb through each one of these little audio files of the 500 hertz channels that are 10 minutes long each, and listen and decode these signals and give us some indication of who they heard, when they heard them, the quality of the signal, any interesting features to kind of pull out. So there's lots of listening, and the hope is that if we can get this down with a few volunteers, we can then start ramping up and maybe taking this to the masses in a much more concerted effort to get more information out of it. So these are some of the first results from Bob, who's W1XP in the top, and Bruce in the bottom here. And yeah, I just what we're asking for, you can see the file, it's a spreadsheet, you can see the file name, you can see the seconds into when they heard a call sign, the seconds that they heard the call sign, and what the call sign was. And then there's some more codes just to identify the strength of the signal and the tone, and the quality, and anything that they may have heard that may be of interest. And so this is just a snippet of what they've sent, and it's really excellent. It's really excellent. I've just been busy just digging through the first bits of it. What I want to highlight is something that Bruce showed, which is really exciting. I've kind of highlighted on the bottom there, and you can see the call signs, and you see this K0DIT, VE3NGY, and then NG77A, and then the VE3NGY keeps showing up. And over in the notes, you can't see it, but what Bruce is saying is VE3NGY is calling CQ the whole time. He's just calling CQ, and you can just hear people, and he does it for several minutes, and you can hear people calling back and replying to him. So you're just kind of watching this conversation happen. And it's a really kind of excellent thing, because when you think about it from a receiver perspective, you're seeing 2 signal sources come up to your spacecraft from 2 different locations, and you can probably separate those 2 signals and really do some analysis that way. This is what it looks like. I've taken a spectrogram, I've zoomed in a bit further, and this is really showing the 500 hertz channelization, and you can see what I suspect, what I've identified, I have to confirm this, as VE3NGY, and it's there for several minutes, this nice descending tone. You get a Doppler shift descending as that spacecraft goes southward. And I'm going to play a snippet of this code. It's about 5 minutes into the whole thing, but I'll let everybody get a sound or sense of what the sounds sound like.
1 minute, Gareth.
Okay. So it's really good data. You can hear all the warbles and the flutter, which makes it difficult for the skimmers. So the ultimate goal is to use this data to do some science. I'm a scientist, so that's what, I mean, it's really fun to look at this stuff and really fun to go through this stuff, but we need to really attack some good science problems. And I think we can do that with CW, with the CW band and RRI. So the thing we can attack is probably what the origin of these scintillations are, and to really leverage that high sampling rate of RRI to go after some really fine spatial resolution studies of perhaps irregularity structures in the ionosphere. There's some other electrical engineering or signal analysis things to maybe we could design a better skimmer, maybe building an autocorrelation function, knowing that we can go through and find the call signs, knowing what call signs are already in the wave file or in the data, and pulling that out and building up an autocorrelation function. I think Phil Erickson's talk and my talk are kind of barking up a bit of a similar tree there in that regard. And just my last slide, probably what's in bold is what I keep, banging the desk about when I give talks like this, is we can do radio science from ham transmissions. Ham science is very valuable, and we can use these citizen scientists as scientists to do some good stuff. And hams, as I always say, are a great ally for solar terrestrial physics. Okay, and I just leave it at that so we can maybe get a quick question in. Thank you.
Nathaniel, there's just one really quick question from Scotty. How do other people get involved? Gareth, you and I have talked about, using these two guys as pilots and expanding them to more people.
Yeah.
We probably need to get some information out about that.
Yeah, the hope is to really scale it up a bit more, and I haven't gotten around to figuring out how we would do that, and I hope to pull your ear on about that. Is to how to get this to more people, because there's more than 2 golden ears out there for sure, and to really kind of smooth this out and get it more efficient and get it out to the masses.
Thank you very much. All right, we need to move on to Magda Moses now. So once again, a reminder, please put your questions into the Google Doc. The link is on the top of the agenda page, and we can also post that link out to the, Gareth can maybe put the link out on the webinar chat again. And next we're going to hear from Magda Moses, KM4EGE, and she's going to talk about observations and modeling studies of effects of the 2017 solar eclipse on SuperDARN HF propagation. This should be very interesting. SuperDARN is a very good system for making remote sensing measurements of the ionosphere and its connection to space. So take it away, Magda. We can't hear you, Magda.
Any better?
Much better. Go ahead. Start again.
Okay, you can hear me now and see the slide?
Yep, I can hear you and I can see the slides. It looks great. Go ahead.
So yeah, as Daniel mentioned, my talk is kind of departs from, like, called it focused talks, but it is a system because it looks at HF that could be compared, whose data could be used with ham data. So, and we've got some talks about the next eclipse coming up after mine, so it might be good to look back on what we've learned from the last one. So just a reminder, the 2017 eclipse, as you probably all remember, across the entire country and started in Oregon and exited in South Carolina. One thing I want to point out on this map is that even though the path was pretty narrow of totality, the eclipse was, most of the continental United States was in about at least 60% obscuration. So you can still see some good effects, some interesting ionospheric effects, even in partial region. So what we expected before the eclipse was that at low altitudes, where it's like the D layer, which are only really sustained by sunlight, the plasma would completely disappear. But at high altitudes, the plasma would be depleted but remain. And we expected also the plasma motion would play an important role in the evolution, especially because we're at mid-latitudes. And of course, any change in propagation and change in the ionosphere can usually be detected by changes in radio propagation through the eclipse region. So this talk focuses specifically on like SuperDawn radar's data. So SuperDawn, or Super Dual Aurora Radar Network, it was originally just a polar network in the name of in the Aurora region, but it was so useful that it was expanded to mid-latitudes, and we have several in the United States. All the radars in this talk have are located. Well, each radar site this talk has actually two radars, an eastward and a westward looking radar, and they operate independently of each other, as shown in the top left figure. And that's the top left figure is a aerial photograph of the Fort Hays radar in Kansas. And yeah, you can see the supports. You can't really see the antennas running between them, but but the antennas can be phased from phased array to form a beam in a given azimuth, or in the direction of a given azimuth, as shown. So in the right figure, you can see the beams comprising the field of view of each radar, and other site, Christmas Valley. So it's important to note that each radar can only make an observation along one beam at a given time. So you sort of have to choose your look directions and cycle around. But along each beam, not looking at the bottom plot, along each beam there's a wide elevation spread, and the radar operates at HF frequencies. Actually, it was at about 10.5 megahertz during the eclipse. And it can, well, sends out a pulse, and the pulse or signal can either be reflected from a large scale plasma irregularity along a field line directly back to the radar. This is referred to as ionospheric scatter, or it can be go up and be reflected or refracted in the ionosphere, reach the ground and be reflected back to the radar from the ground. That's known as ground scatter. And it's important, we can differentiate the radars measure not just the distance that the scatter traveled, or that the signal traveled, but also they can measure line of sight Doppler velocity, as well as, well, some of them can measure the elevation angle of received scatter. As you can see in the top, if you look at the top left figure, the two antenna arrays. And the velocity information particularly can be used to differentiate what is ground scatter and what's ionospheric scatter, which is useful to determine whether any irregularities were forming during the eclipse. Now, specifically, we used these 4 radars in the eclipse experiment, mainly because they had fields of view that intersected the path of totality. So as you can see, this path of totality passed so close to the radars that the radio signals were likely passing through a partial eclipse region when they actually were in the ionosphere. But it was good enough. So also I want to draw your attention to the highlighted beams. So as I mentioned before, the radar can only make measurements along one beam at a time, but with the eclipse being only a few minutes, well, at totality being only a few minutes, you kind of want to maximize the collection. So we only used about half of the beams at each radar, and those are highlighted. And then we also had a camping beam, which basically between any two measurements on any two beams, it would return to the camping beam. So the beams, and those are highlighted in blue, and they have the best resolution out of all of the beams data. And those are what I'm going to, the data from those is what I'm going to show next. All right, so it's a lot of information, but each of the figures is a different radar, and they're all from the data from the camping beams. You can do the annotation. Oops, no. No, I guess I can't figure that out now. Okay, well, the top. Okay, no, here it is. So this panel, I want to draw your attention to like this panel here. That just shows the distance of the center of the eclipse from the radar. And over time, oops, what? Sorry. Okay. Sorry, technical difficulties. Sorry. So this panel here, that's the one that shows the distance of the eclipse from the radar, the eclipse center from the radar as a function of time. So it's just a proxy for the magnitude of the eclipse at each site. And the bottom three panels have x-axis in UT, universal time, and the y-axis is range of the scatter, which the scatter is reflected back. And the colors differ between the three plots. The top one is just the received signal to noise ratio. And the middle one is the velocity, the Doppler velocity. And the bottom is spectral width, which, I mean, so the important thing about the bottom two panels for each of the sites is that the velocities and the spectral widths are low. Therefore, we categorize that as ground scatter. So no, we don't observe any irregularities forming in the ionosphere during the eclipse, any large scale plasma blobs or anything like that. So now just looking at the signal to noise ratios and comparing the different plots. Well, at Christmas Valley, the maximum eclipse occurred around this time. You can see that during the onset, partial phase of the eclipse, at the onset, the more scatter is, less scatter is returning, and also the range of scatter seems to be increasing slightly. And it's also, the recovery period is very symmetric around totality with the onset. But when we take a look at the eastward looking radar, we don't see as symmetric or as clear of a response. We same time of totality, but you don't see much of an increase in the range of the signal, though you do see a decrease in the amount of signal around totality, but also there's a much quicker recovery. Then going to Fort Hayes West, the eclipse occurred a bit later in the day. So around here, around 1800, so I don't know if you can see the pointer. And the here we can see a decrease around totality at the and a increase in slight range, at least of one of the scattering bands during the onset phase of the eclipse. But we don't see the symmetric recovery that we saw at Christmas Valley. There's something that looks like recovery several hours later, but that also appears in the Christmas Valley plots as well, so that might not be eclipse related. So, and then at Fort Hays East in the lower left, lower right, there's almost no discernible eclipse response, and also the noise, it's much noisier than westward looking radar in Kansas. So summary is that almost all the radars observed some decrease in the amount of the amount of signal returned near totality, and the signature of the eclipse is much clearer in the westward looking camping beams. However, the recovery period and even the onset period differs greatly between the two sites. Thank you for this annotation. Okay.
5 minutes, Magda.
Okay, well, went way too slow. Okay, well, the elevation angles, as you would expect, you could see that that only lower ones are returned. And this is, I only show this because elevation angle data is helpful in our analysis, which involves ray tracing through, well, generating models of the eclipse ionosphere with different assumptions, and then using far left to ray trace through them and ray trace through the output of the model and generate simulated radar data, which we can compare with the measured to determine the validity of the different hypotheses, and the elevations are very helpful to compare. So as you saw before, the eclipse path lengthened, the signal path lengthened during the eclipse, especially at Christmas Valley, but it could have been, just looking at that, it could be either due to a change in the height of the layer or ducting through the eclipsed region. Looking at the ray trace plots in profile view, you can see that, well, so the white lines of the paths and the background is kind of plasma frequency, which is proportional to the electron density. And top is the control case and bottom is the eclipse case. And you can see that the height of the peak density in both cases is about the same, but the signals in the eclipse case are ducted in the ionosphere through a greater distance, and also more of them escape. So this path lengthening was due to ducting and not changing in layer height according to our model. And I'm gonna get this quick because I only have a few minutes left, but this is just an example of how we can use this ray trace analysis to compare, to improve our models. So this shows the elevation angles at Christmas Valley West data at the top, and then one of eclipse masking functions model output in B, which has much higher elevation angles than data, and then an improved one in the bottom panel, which has elevation angles that for Transcata that actually much closer to those observed. And I don't think I have time to go into this, but my presentation is going to be online. But one of the reasons one among many reasons that we might see differences between the Christmas Valley and Fort Hays data is due to the differences in the magnetic field orientation at each site. And also, we did a study that involved changing the direction of the neutral wind in our model and seeing how that would impact the electron density and then the ray trace. And we can see that the components that are best aligned with magnetic field have the most impact on the radar data, the simulated data. So this is just a summary, but one thing got out of this is that these SAMI model and far left ray tracer can be used together to better understand eclipse dynamics. And well, we have another one coming up soon, so more data from the Superdome and the ham community and other sources could help us answer some of the remaining unanswered questions. And with that, it's open for questions with the next speaker.
Thank you so much, Magda. Do we have any questions?
Just one quick question. I missed something. What does the term camping beam mean? Why do you call it that?
We call it, it's kind of like the base. So it's Superdome's kind of scanning across. Superdome's kind of scanning across the field of view, going from one to the next, except in between motion, like in between successive beams, it returns to the camping beam. So it's kind of its base. It scans one beam, then goes and takes a measurement along camping beam. Scans a different beam, goes back to the camping beam, makes a measurement. So that's why it's camping. It's
Okay, okay, I got it. Thank you.
Great, thank you so much, Magda. I really appreciate that. Okay, next we're going to have Bill Lyles, who will be talking about Eclipse Mob initial planning for 2024. So Bill Lyles, NQ6Z, go ahead.
Okay. So, yeah, okay. So I'm going to be talking about the Eclipse Mob, and some of you already know about this group because we were around for the 2017 eclipse. And so I'm going to kind of talk about some historical collection, lessons we learned from the 2017 effort, what we're going to try to do for the 2024 one. We changed the receiver design and some conclusions on this. So you just heard from Magda, so you know why it's important for us to study during the solar eclipse. And you also heard during the lunch break about day-nighttime complications using the normal sunrise and sunset. Well, we don't have those same sort of complications during the eclipse. So historically, the first data collection was done in 1912 by Bill Eccles. Some of you may know him as the co-inventor of the flip-flop. And he didn't even have a transmitter back in 1912 to listen to, so he just listened to atmospheric noises. He did get it published in Nature magazine, however, for doing that. Then after him, as the eclipse moved eastward, some folks in some other countries listened all to the same transmitter at the Eiffel Tower. But since they didn't know they were going to be doing that, they didn't collect data in the same way. They couldn't compare the data. We didn't get any sort of general view of what was happening as it happened, went across. So they said, okay, we know what we're going to do now. We're going to make this so that we can really do an eclipse. 1914 is the year. We're going to collect it across Europe. Well, you all know what happened in 1914, so that one didn't happen. 1919, going to do this again. Had set up 2 transmitters, one in Panama Canal, one in Cairo. And again, people collected data very differently. And so some said, oh, the reception got worse. Some said it got better. They had no idea how to compare them. So again, didn't get the results they were looking for. 1925, Scientific American, for a whole year prior to the eclipse, ran an article about, hey, the eclipse is coming. Here's some data to report. Do this. Okay. They got 2,000 mailed in replies. AWL did the same thing. They got 150 reports in. Most of those reports were useless because people didn't report the date. They didn't even say if it was done on the day of the eclipse or not, where they were located, what the time was, which AM station they were listening to. So we got that location in terms of the Scientific American. The ham reports were just as lousy. So not good. So what do we learn about this? You got to have some sort of standards of how this data is collected if you're going to collect from multiple sites. So Appleton and Chapman said, hey, okay, we can do this. So in 1932, 33, and 34 eclipse, they collected all sorts of data, and the report written by the 2 of them in 1935 says, hey, we blew it again. We can't compare any of these reports. We need a standard way of doing that. Well, today, we got inexpensive hardware, GPS receivers that give me date, time, location, and all that stuff. So I shouldn't have this problem anymore. That's the goal. So what is Eclipse Mob? Well, Eclipse Mob in 2017 was, we're going to send out kits for people to receive WWVB down to 60 kilohertz. There's a picture of the kit that they made. We send them the proto board and chips and everything. And then, oops. And then they would hook that up to a phone. I'll go to that later and collect the data. That. Okay, so that was a 2017 thing. And here's what the receiver was. We had an instrumentation amplifier. And now we're at 60 kilohertz, remember?
Hey, Bill, your slides are not
changing. SDR.
Bill?
Bill?
And so the ADD converter and all the processing is being done in the cell phone, smartphone, which has the GPS and everything. So we have a multiplier chip to get it down to inside the audio bandwidth of the cell phone. Well, in order to do that, we had to mix it. Well, where did we get the local oscillator to mix it?
Bill, can you hear me?
We took the audio output of the cell phone, went into a multiplier, and we combine it with another multiplier to get it down into the audio bandwidth. Okay. That
Bill,
was the receiver.
Question.
We had 150 kits distributed across the United States. We were in 3 countries. Some people couldn't get a kit, so they just went online and bought parts from DigiKey, Mauser, whoever, and built the stuff themselves. It was wonderful. But you may notice that there's an awful lot of kits were distributed around the 2 yellow dots, which is George Mason University in Virginia and University of Massachusetts in Boston. And so we didn't get the best distribution we wanted. So that's one of the things we're going to be taking care of next time. But we had a lot of folks listening in, and we, for the 60 kilohertz and also 55.5 kilohertz from Dixon, California. That's right outside of Sacramento, California. So what did we learn? Folks are really helpful. A lot of people wanted to do this thing. We got calls, we got emails, we got people up on this social media. It was great. However, we started with less than a year before it was going to, event was going to happen. That was not good. For example, the software wasn't delivered until the day of the eclipse, and yet people were building receivers and couldn't test it with software. Not good on that. The outreach in social media, I did not understand that, and it's basically a full-time job just to handle that. Okay, so we're going to try to do this coming up as a train-the-trainer model, because a little team, my co-authors and myself, we were basically trying to handle everybody. And the receiver system had some flaws in it. One is what smartphones do kept changing. So for example, when I first tried this, guess what? I could actually put 60 kilohertz into the smartphone and there's no filter on the front end and it would take it just fine. But then they changed the methods used in smartphones and there was a filter. Also, I don't know if you know this, but just because you plug something into the microphone input jack of a smartphone doesn't mean that it's going to accept the external mic. It can still use the internal mic. And I have lots of recordings of people talking about oohs and ahs of seeing the eclipse without data because of that. And the way we debug these things, people came like to George Mason, we worked on them, and that doesn't scale because we want now thousands of receivers distributed around. So what are we going to do for 2024? We're going to scale this thing up so we can have thousands of receivers around. We're going to change the receiver. We're not going to use a smartphone anymore. We're going to use Raspberry Pi, GPS receivers connect to it and that, because then we control it. Okay. Yes, Raspberry Pi's changed, I know, but not as much as cell phones change. We're also going to try to pick up signals all beneath WWVB. And if we are good in our design and we're trying for this, we also want to pick up the 136 kilohertz ham band, because last time there was only a few experimental stations on there. Now there's quite a few, and if I can pick them up, so much the better. And like I said, we're going to go to train-the-trainer model. So here's our basic model. We got a leadership team. Going to do a lot of stuff on the web, because that's how people operate. We're going to distribute them for local leaders and event organizers, but yet so people can do it as part of teams, or they can still do it on their own. So what about the 2024 receiver? Told you, smartphones we're not using anymore because they don't have microphone and headphone jacks. Once they get rid of that and I got to use like Bluetooth or Wi-Fi to communicate with them, I might as well use something like a Raspberry Pi because I'm already spending some money there. GPS subsystems available at low cost. I can do that. I can put all the stuff out on SD cards because one of the things is that people tend to go outside, away from cities and away from Wi-Fi or cell hotspots to collect this. So putting on an SD card so they can then upload the data to our servers later. So that's where we're going with it. So again, the instrumentation amplifier up front, Raspberry Pi controls everything with a GPS and SD card and status display. So it's a very simple, self-contained thing. The antenna, however, we're not changing. That's what the antenna looked like for 2017. That is 2 loops. So it's a balanced non-resonant loop antenna. Each loop is 100 turns of wire. And I'll tell you, we had 5-year-old kids building those antennas. We had adults building those antennas. The plastic box that you see it wrapped around, that happens to be the box that we used to ship all the components and tools that were needed to build these kits. Yes, we included all the tools with them. So we used the box also for the antenna. So staying with that sort of antenna design. So what are we doing? We're starting much earlier. Like you're hearing this talk now, not less than a year before the eclipse, right? We should have the working receiver and software this year. We're pretty well along that way. We're planning to hire some professionals for this task instead of students. And we plan to leverage this network of folks and train the trainer sort of things. So given all that, you know what the next slide is going to say. Acknowledgement, that's John Walkway, who gave us the 55 kilohertz signal out of Dixon, California. That was great. George Lemaster, he helped in ways that can't even go on to explain. Whatever something needed to be done, he was already there doing it. He was just wonderful. And thanks so much for the National Science Foundation for supporting that effort. If you would like to help and on the upcoming effort, please let us know. We do want to talk to you, and we're starting to try to organize that as I speak. Okay, that's it.
Bill, we have one question.
So if I can get the control back to.
We have it, Bill. Go ahead.
Bill, we have one question from Dr. McDonald. What is the difference between this and PSWS? Will they be compatible?
Hello, Bill. Can you hear us?
Is anybody talking?
Yes.
I don't
yes,
hear
we're
anybody.
talking. Hello? I'll try to see if I can call Bill. Go ahead with your question though, Laura, from Liz, while he's while we're working that out, because someone else might be able to answer it.
Okay. So the,
Hello,
the
Bill,
question.
can you hear us?
Oh.
Go ahead.
So we had a couple questions actually, and one I already answered. So Bill is only discussing 2024. The question was, do you have the opportunity to use the 2020 Chile-Argentina eclipse as a smaller trial
I'm
run?
sorry, I still don't hear anybody.
And the answer to that is we talked about that. We plan to do that, and also the one that went in 2019, but we were still testing the system, and so we're not able to take advantage of those 2 eclipses.
Christina, do you want to talk at all about things you have planned and that we have planned?
Well, we're going to be very well positioned because Totality will be going right overhead here in Cleveland. And so we are planning on being the sort of the center point of some of these activities and setting up stations along and around the path of Totality for that purpose. David, anything in particular?
Well, yeah, that and the University of Southern Illinois at Carbondale Club was right at the center of totality for the 2017 eclipse. And that's where the two paths are going to cross. So we ought to work out something good to do with them. And Christina, you're planning on traveling to Chile, aren't you?
Not under the current circumstances, no. But I would like to try to collect data from some of the other eclipses that are happening worldwide in advance of the 2024 eclipse so that we have some things to look at to get ideas, in the same way that we used the Festival of Frequency Measurement as sort of a first pass at figuring out what we needed to know in order to do larger scale data collection, because we only get one shot at this.
And interestingly, there are several beacon stations in South America that may be suitable for monitoring.
And I wanted to add in the note of, so if you know anyone, sorry, was that Bill? Oh, okay. But if you know anyone who is interested in, happens to be near one of those beacon stations or is interested in eclipses across the world, put them in touch with us at Case Western. We'd be interested in working on that.
Bill, can you hear us now?
Perhaps he cannot.
Yeah, I think he's still having technical difficulties. We can
I see a
continue.
connecting to audio thing under his photo there.
Yeah. So why don't you just, you can keep with your eclipse discussion. We still have a couple more minutes before the next presentation.
Sure, yeah. The only note on that is that we're currently exploring the idea of looking at using the same sorts of Doppler techniques that we've been using with WWV for other time standard stations around the world, of which there are many excellent ones. And I've been mapping out eclipses and looking at where time standard stations are relative to them and what data we might be able to collect that could be useful.
Okay, so I have a comment on that. We're collecting the raw signal so that we can do Doppler and any other sort of measurements we want to do with it.
Mm-hmm.
We're just not, what most people care about is just, was the signal weaker or stronger during the time? We want to actually analyze the signal. So that includes the Doppler stuff.
And I'll add to that in phase and quadrature measurements. That's what we supplied in 2017.
Mm-hmm.
Will the eclipse mob for 2024 be doing in-phase and quadrature?
Okay, so the actual A to D converter doesn't, but given a real-time stream, you can convert it to INQ, and that's what we'll be processing as INQ.
Are you going to be able to make any use of the 2023 annular eclipse?
We would like to. That's one of the reasons we're starting earlier.
Right.
But,
So that gives
also,
you,
there's other eclipses around the world.
There are,
that aren't
yes.
just in the U.S.
Right.
And so, we actually are thinking about, okay, how about shipping some equipment over to another country and test there prior to the 2024 here?
Yeah. How much difference do you think there would be in the annular eclipse versus the total eclipse from an ionospheric standpoint?
Okay, so the path that you usually see of the eclipse across, the total eclipse across like the US?
Mm-hmm.
Well, first of all, you have to realize that's the path of visual complete obstruction. That's not the path of how the ionosphere is being treated.
Right.
Okay, and so when you look at some of the annular ones, actually you hit more of the ionosphere and it will come out very similar because it's higher up and you're at this other angle.
Mm-hmm.
You understand what I'm trying to say?
So you're saying they'd be rather similar from an ionospheric perspective.
Yeah. So the ionosphere path is actually, for each layer, it's a different amount south of the visual path.
Right. So really the 2023 annular eclipse is going to be a very good thing to have to be working toward as well.
Yes.
Yeah. Great. Thank you very much. Really appreciate that, Phil.
Yeah, sorry I had a problem.
That's okay. We worked through it. So good job. Okay. Next up, we have people from the University of New Brunswick up in Canada. So we have two people here, Aaron Farnham, VE9CG, and Dr. Anton Kashcheyev. They're going to talk about a new chain site in New Brunswick, low cost, high frequency, and global navigation satellite system instruments for the solar eclipse 2024.
Hello, can you hear me?
Yes, we can.
Yeah, we start with Aaron will start the presentation and I will join him at a later stage.
Thank you. Can everybody see my screen?
Yes. We can see and hear you.
Great. Okay, I'll start with just a quick overview of who we are for those that haven't heard of us. The CHAIN is an acronym, stands for the Canadian High Arctic Ionospheric Network. We're a collection of 28 sites at high latitudes. All of our sites have a GNSS receiver for scintillation and tech measurements. We've got 10 ionosondes at those sites. Our oldest site in Eureka has data from 1994. So we're quite busy. We're doing a lot. One of the things that we're continuously trying to do is expand our network, not just geographically, but also in our capabilities. So currently, all of our GNSS receivers are Septentrio or Novatel receivers. They're quite expensive, and that's can be prohibitive for expanding. All of our ionosondes are Canadian advanced digital ionosondes. It's an older design and also quite expensive. So something that we've been playing around with is testing low-cost instruments, and there's a plethora of stuff available. So Anton will talk a little bit more about that. Right now, some of the things that we're trying are USRP sounders and various GNSS modules. So why is this important to HamSCI? Well, for one, our data is freely available. We have lots of data dating back to 2007 for our GNSS observables. And as mentioned previously, some of our ionosondes have data back to 1994. We also, we're doing other work. So we're working on an assimilation model, which is being driven or is driving the need for densification. We also have an empirical Canadian high Arctic ionospheric model developed by Dr. David Demens. This is supposed to be an IRI substitute for high latitudes. But what I really want to drive home is that we're open for collaboration, and we think that we're uniquely positioned to collaborate with scientists all over the globe, particularly because of our footprint in the Arctic. So as I mentioned before, we have 28 locations. All of these locations have infrastructure available, and there's room for co-located equipment, and we're also open for working with others to try to add value to the network. So some of this could be augmenting our data with second sources, bringing your instruments into our network, or hosting instruments, or potentially scheduling campaigns that will provide you data that will hopefully help to augment your work or augment our work. The pictures below here, the one on the left is from Sax Harbor. That's in Northwest Territories. That's our westernmost Arctic site. And then on the right, you see site location is Kikik-Tarjuak, Nunavut, which is our easternmost Arctic site. So that's why you should care. And regarding Eclipse 2024, well, we have new news. So we have a new site that we just put up this year. This is just for testing, research and development for things that we would like to implement in our network up north. So this current site has a caddy, has a USRP-based ionosonde, septentrio GNSS. It's got a few more pieces of equipment there, and there's lots of room for more equipment. The reason this is important to some of you is because it is located in New Brunswick, Blissville actually, and it's very close to the totality of the 2024 eclipse. And we would like to take advantage of that to the largest extent possible, either by creating campaigns that will provide data for others, or hosting instruments, or any sort of collaboration that that anybody may be interested in that could advance the cause. So now that I'm done the marketing shtick, I'll let Anton take over.
Thank you, Aaron. I'll try to, yeah. If you stop sharing your screen, I can take over.
Yes.
Hello, everyone. Can you hear me?
Yes, you're good.
Yeah, okay, thanks. So I will continue from that point. You've heard about our network we are operating currently. I would like just to briefly mention that, of course, there are multiple other networks. In particular, I will be concentrating my talk about GNSS networks and try to explain why it is important for HF community as well. So other two examples, these are two biggest in terms of spatial and temporal coverage. GNSS networks is a course continuously operating reference station, and IGS, that is International GNSS Service Network, providing data back from 1999 and up to now from all the points over the globe you see. So what type of studies we can do using GNSS measurements? I just would like to mention a few examples of what might be important for an HF community. That's here I'm presenting different results of other researchers studying medium scale TIDs. That is, providing you have a good coverage, a dense GNSS network, you can reconstruct to a very details, in particular directions, spatial and temporal scales of TIDs. So the left plot is in Japan, and the middle plot is in the US, and right is over Europe. So you see here fluctuations of TAC, that is total electron content, that is integrated value along the ray path between a GNSS receiver and a GNSS satellite. That, of course, you know, now we have multiple GNSS systems like GPS, GLONASS, Galileo, and Beidou, at least 4. What's more important for space physicists is studying solar terrestrial connection and let's say response of the space weather in general to magnetic disturbances, to some solar events. And here I'm presenting results of large-scale TIDs. That's on the left plot. You can see a good representation of that in over the US, and on the right hand side you see that is a recent result from 2016 by our colleagues from UCAR, and that you see that network is they are pretty dense over Europe, northern part of the Northern America, and in South America as well. Now, yeah, here is a mistake in a title, but here I'm gonna talk about solar eclipse. So you heard Garrett was presenting his EPOP results, but now I would like to show his early results. Well, not so early, but recent actually results studying a solar eclipse using TAC data. So that's on the right side as well, showing how TAC, how ionosphere reacts to a solar eclipse. You may definitely ask why is it important for HF propagation, but to show just a brief example how TAD may affect HF ground HF propagation, I will play you a short video from taken from our new site in Blissville just a few days ago, showing an example of TIDs. If you look at these are a set of ionograms taken every 2 minutes sequentially. And if you look at the 4 megahertz range, you may see, roughly, I don't know if you see a video, but it is uploaded to a Google Drive, so everyone can download later and take a look. And in particular, yes, I will try to show you an area where to play. Where you can see a fluctuations in the reflection height of a certain frequency and how it fluctuates in time when a TID is present. Now I'm gonna talk a bit about our results. We are trying to see what can be done using low-cost equipment. As Aaron mentioned earlier, we have a number of scientific-grade GNSS, TAC, and scintillation monitors. But what we can do with essentially low-cost devices. We have a number of GNSS receivers under test. One is Septentrio, with what all of our sites are equipped with this receiver, and two more, that is Pixie and U-Blocks receiver. The orange one is a Pixie, and the U-Blocks is these are all dual frequency GNSS receivers. So you can see the differences of price. It's almost a 2 order of magnitude. So here I would like to show you some few really passes, satellite passes, and comparison of on the top left plot we have a blue line showing a TAC computed using Septentrio receiver, and the orange line using Pixie receiver, and the red line shows elevation angle of a satellite seen from the ground. And right bottom plot will show you a difference between these TAC. It is intentionally left a little bit spaced apart because we didn't apply any calibration for TAC measurements. I'm only interested in fluctuation part right now. And so what's important here is to see that the standard deviations, the difference between these two, these are, again, just to remind you that this is 2 order of magnitude difference in cost of these 2 receivers. That is 0.0 TAC units. That's really good. So other tests, we have more statistics in the left bottom plot. We have more statistics about the difference, maximum and minimum difference values that is not exceeding 1 TAC unit. That is pretty good. We have same results for U-Blocks that actually we got it in our lab just a few months ago, and we are happy to and probably be trying to expand our studies in terms of densifying, at least in New Brunswick area, our network. Another thing I would like to mention is that we are also playing with a low-cost HF equipment. In particular, we have, you've seen we have 10 CADI ionozones, but they're aging and quite expensive. But we have an idea to replace them sometime in the future. And an example of that, where we are using USRP devices and 200 software-defined radio to generate and transmit the signal, and then to receive it back and post-process in the PC. So we developed like a prototype of a low-cost atmospheric sounder. You see here kind of a block diagram of it consists of USRP. Then we use an ICOM 718 transceiver exclusively as a power amplifier. Not anything else is not used. It just as the cheapest option as it appeared. And a PC, just at Linux or Windows, no matter what. And, we have a network of these devices. At least three of them are, a couple of them have been working for almost 2 years. One is in mid-latitudes in Europe, another one is in Antarctica, in Antarctic Peninsula. And its recent installation was done in Blissville in New Brunswick, Canada. And a new site is planned in low latitudes in Africa later this year. Just a few examples of ionograms taken by, in Antarctica, we have two ionozones sitting next to each other. One is an old IPS-42 Australian ionozone, and transmitting at 4 kilowatts power, and the new system, USRP-based system, is using maximum 100 watts. So the blue ionogram on the left side is made using USRP, and the white one is from IPS ionozone. We have just a few more plots showing the comparison between, statistically speaking, between ionograms taken using an old system and a new system, just to understand how it performs and if we can substitute one with another. And it shows pretty decent results. Now, these are comparison plots of ionograms taken using CADI in our new Blissville site, just again a week ago, and a USRP. In USRP, we use a different way. We are trying to use different coding techniques like complementary, Barker, and some other new M codes as well. But like what we see here, in principle, USRP based is not at least worse than a CADI, and that's leaving us a good feeling of we can do something with that. In conclusion, I would like to repeat Aaron's words that we are open for collaboration and interested in opportunities for value-added expansion, in particular for coming solar eclipse 2024, and using our Blissville site that is close to total eclipse and totality, and as well as a whole chain network. And two more things in conclusion, that both low-cost dual frequency GNSS receivers are good alternative to scientific grade receivers or geodetic grade, let's say, receivers to estimate TEC, ionospheric fluctuations in terms of TEC. I'm not touching here the scintillation monitoring right now, but as well as low-cost HF sounders available on the shelf is a good alternative to existing ionozones as it appeared from our studies. What I would like to deliver as a message for ham community, especially for Tangerine people who are working on that having a dual frequency low cost GNSS module as a part of your design, we, like scientists like our group or many other groups are interested in using also TAC measurements. And we will definitely benefit from having a dense network of GNSS receiver as a part of space weather stations, personal space weather stations. On top of that, we will be happy to host space weather station in most of our sites. Yeah, I think that's it. If I have time, please, questions.
Thank you so much, Anton. Thank you, Aaron. That was very interesting. I can tell you, for me personally, I would also be very interested in collaborating with you, especially over the next year or so as we start trying to develop methods for the Tangerine SDR and the Personal Space Weather Station to look at signals of opportunity. So discussing some of these ideas of coordinated scheduling and knowing good algorithms for decoding the signals that you're transmitting from your systems. I think that would be very good, and we'd be more than happy to share the data with you. So after this workshop, over the next year or so, maybe we can start talking about some of those ideas and how we can collaborate.
Yeah, absolutely. We would be happy to collaborate, and we are pretty open in terms of campaign modes as well. When it comes to a Blissville site that is very close to your location, we will definitely can discuss the possible campaign modes for transmitting signals, whatever we would like to transmit.
Thank you. Thank you very much. Okay, again, I'll put the Google Doc link in the chat window again so people can ask questions. We do have to move along with the schedule for the moment, and then we'll have a break, another 20-minute break. So next we have a presenter from the Radio Jove community. This is Dr. Xing Feng, and he's a NASA scientist. And I was actually first introduced to Radio Jove when I was an undergraduate. So that was some of my very first experience with citizen science. And Xing has a very nice presentation that even though Radio Jove, their main mission is to look at radio emissions from Jupiter, he's looking at HF spectral signals and identified a very interesting feature that I think everyone in this group will appreciate. So go ahead, Xing.
Okay, thank you, Nathaniel, for the nice introduction. So I'm going to talk a little bit about the work that I've been working on with a group of citizen scientists associated with the Radio Jove program. You see a lot of co-authors on this slide here. Everybody can see my slides okay?
Yes.
Okay. So basically, everyone who is not associated with the university or Goddard are the citizen scientists participants in this group. Let me first say a little bit about the Radio Jove program, which started out more than 20 years ago as an educational and outreach project, started at Goddard with what is called the Directorate Discretionary Funds, sort of internal funds that support these educational efforts. So the project consists of participants building a radio receiver kit, which is fairly low cost still. So over the years, they have distributed over 2,400 kits, and I understand the latest count is pushing 2,450 now. So as Nathaniel mentioned, the object of the exercise is to observe Jupiter, the Sun, and the galaxy. So hopefully with the building of the radio receiver kit, so the participant will get hands-on experience with radio astronomy. So at the same time, and they can learn about observing the cosmos, and so to speak. With the group, there is a subgroup of people who are actually more sophisticated than the regular participants. They actually operate a spectrograph unit, which actually takes spectrogram instead of the single frequency the traditional Radio Jove receiver. So in the last few years, we have started with partnering with the NASA Space Science Education Consortium, which is an education consortium that does public outreach and try to promote the heliophysics to the community and try to use heliophysics as a medium to firm up STEM education. So we partner with them, and with the specific extension of Radio Jove scope to include citizen science research. So what we're going to talk about is how we're going to start doing that. I'm not advancing the slide for some reason. Oh, that works. Okay. As I mentioned, the subgroup, the spectrograph users group, operate a FSX swept frequency spectrograph. And currently we have about 9 stations distributed across the US, including Hawaii and Alaska. So this is a swept frequency spectrograph. And we're trying to develop a network of low-cost receiver to make a network, just like what HamSCI has tried to do, to develop a network of receiver to make observations and try to do some science with the data. So in developing our phase 1 network, what we have done is upgrading every different stations with calibrations and timing accuracy so that every station would be performing at the same level. So we actually now have an operational phase 1, if you will, but we're still doing testing and checking on comparing data and that sort of stuff. But we're also looking in the future to develop our phase 2. Our phase 2 development will be based on SDR units. Currently, there are a number of team members are working with the SDR plays and some other SDR units to identify what is the best unit for us to work with. So of course, the idea of going to the SDR is the low cost and perhaps more capable unit, and therefore we can build more stations that way. I understand that some of our team members has already talked to some of the Tangerine SDR developers, so potentially we can probably work together and come up with a workable unit, both for HamSCI's purposes and for Radio Jove observations purposes. Well, I don't have a picture for you, but I can show you the antenna configuration that's being used by the subgroup. The spectrograph worked off of a 7.3 meter square TFD arrays. So the arrays are connected to a quarter wave coupler, a hybrid, which then takes both the right-hand circularly polarized wave and the left-hand waves together, but at different times. So in a nutshell, this is the specification for the spectrum analyzer. The frequency range we're working with is 15 to 30 megahertz. The reason for this is that because for the most part, the group wanted to observe Jovian radio emission, and this is right in the middle of the Jovian decametric radiation. So the frequencies are put into different channels, and each band has 30 kilohertz bandwidth. And we're stepping in frequency by 50 kilohertz. And the unit would sweep at 2,000 channels per second. So that gives roughly the dwell time on integration time per channel is about half a millisecond. And typically we would run 300 channels between 15 to 30 megahertz. So that gives you, with the 2 polarization output, the time resolution would be 300 millisecond or 0.3 second per spectrum in both polarization. Okay, so I'm going to talk a little bit about the TP. So this is the characteristic feature of the TP, has a upper, oops, has the upper cutoff frequency increasing with time and decreasing with time afterwards. What we're showing here is a dynamic spectrum with frequency increasing from, here is a 16 all the way up to 30 or so megahertz. And the horizontal axis is time. So the time scale for one of these things is, a few hours, okay, at the bottom. So, and then it forms the triangular shape feature. So that's why we call it a TP. It looks like a TP10. In this example, it's actually two TPs observed simultaneously in Florida and in New Mexico. So, and that's very interesting because, well, we don't see these all the time, but sometimes we get lucky. So we're able to detect a TP simultaneously. I actually don't know, I can't tell you that these actually have the same source, but given the time signature, they have the same time for the apex frequencies. So if you assume that the same source produced the TPs for the very widely separated stations, and the simplest thing to do is maybe put a source in the middle. The two stations are separated by over 2,000 kilometers. So somewhere in the middle is 1,000 kilometers would be the source location. So that makes it a very interesting scenario. So what could produce this TP signature? TPs are observed not only in isolation, but they also seen in groups. In this case, we call it a nested TP, which is you see a TP here, and then at a higher frequency, you see another TP. So they look like a nested or tower distribution of TP signature. And another one over here, and you can see that, in fact, the one with lower apex frequency tends to be a little stronger than the ones with higher apex frequencies. The color scale are adjusted so that I can actually emphasize the TP feature, but if you bring up the color scale a little bit more, you can see that this is actually the galactic radio background, same as over here. Okay, so here's the nested TPs, but there's times you can also see TPs in a series. Over here is a 12-hour spectrogram, and you can see a series of TP that continues on, and then it ends toward the end of the day. So whatever mechanism can produce the TP signature, not only that it has to produce the isolated TP, but it has to also explain why we sometimes get the nested TP or sometimes TPs in the series. This enhanced feature up here is around 27 megahertz. Those are the CB bands interference. And some of the other discrete bands are also radio interference. Okay, so if we could put some of these things with a more geophysical context, we're going to start looking at some of these TP observations relative to, well, what is the rest of the magnetosphere is doing? So the simplest thing for me to have done is to look at the occurrence of these TP features during the times of, asking what is the geomagnetic condition during that time. So on the right is the top panel is what is called the KP index. The KP index is measured over 3-hour interval, and it measures the global geomagnetic disturbance over the Earth or of the magnetosphere. The second panel is the DST index. Some of you may be familiar with. It measures the strength of the ring current. In other words, it tells you how stormy the magnetosphere is during that time. And the index below is the AE index, and it measures the auroral activities. So in this particular event, it's actually pretty quiet. Okay, so KP has a scale from basically 0 to 9, and this is actually less than 2. The vertical scale here, I got this from Omni, their KP value is 10 times the KP value. So if you divide this by 10, you get the traditional KP value. So the spectrogram on the left is a 10-hour interval. So the same 10-hour interval is marked on the right. And you can see the KP is actually very, very quiet. And it only marches up to maybe just below 2 toward the end of the day. And DST is slightly positive. And it's certainly nothing to write home about. And the AE index, the aurora activity is exceedingly quiet for the most part of this interval that we're talking about. It only went up to maybe, well, below 300. It's still pretty quiet in terms of aurora activities. So this is actually a quiet time event. So the one more thing I want to do is to zoom in on this part of the spectrum to see what it looks like when you look close up. And I'm not able to advance. There, okay. So now the next panel here is 1 hour of this particular event. And you can start seeing some of the fine scale structure over the top, which is the cutoff frequencies. If you zoom in some more, this is a 20-minute interval. And at last, this is a 2-minute interval. So this is the same event, zooming in succession from 10 hours to 2 minutes. What you see is a series of discrete bursts. So the discrete bursts are seen occasionally during quiet time. So that if you just look at this slide, that's what it suggests. So during quiet times, you tend to see these things, discrete bursts. So the only natural source that I could think of that could produce these discrete bursts is probably lightning flashes. So that's how I'm going to start thinking about these things as lightning produced radiation. So next I'm going to show you another event, which is during moderate times, moderate activities. So here, this is an event that occurs when KP is up to about 4. So again, this is a 12-hour interval, the same 12-hour interval, and you can see that KP is now 4. DST went slightly negative, but it didn't quite go down to a storm type condition. So this is still above DST minus 20. The AE index here, because of this time in 2019, we actually do not yet have the definitive AE index. So I went and looked up the provisional AE index. That's what this is. And you can see that the AE index actually at times, even during this 12-hour interval, it at times went up to 1,000. So you would be expecting some aurora activities at this time. So this is a case when you have a moderately disturbed magnetosphere going on, and we still see this TP signature, and then this is the CB enhancement. Again, do the same thing with zooming on the same 2 minutes. Now the picture looks very different. It looks like hash, but in between the diffuse signature, you also still see these relatively still discrete, but not continuous bursting. So it would seem now that the diffuse appearance may imply significant ionospheric scattering, because during geomagnetic active time, the ionosphere is disturbed, and then you're more likely to produce irregularities in the ionosphere, causing scattering of the signal, producing this diffuse looking appearance in the TP signature. Okay. So next, we're going to look at a possible generation mechanism of the TP. This is a familiar picture for most of you. So all it says is that you have a transmitter or radiation source of some sort. You produced a high frequency wave, some of which would propagate upward toward the ionosphere. The dashed line is indicates the bottom side of the ionosphere. So above the bottom side ionosphere, you have a density gradient with electron density increasing upward up to a point to maybe the F, the critical layer. And then the upward propagating wave at whatever incident angle at the bottom side ionosphere is going to refract continuously up to a point and then refract backward and come back down to Earth. So this is the traditional picture back in the 20s, and this configuration has been well studied, certainly in terms of radio communications. So there's a theorem called the Bright-and-Tooth theorem, which says this continuous process of refraction can be replaced by a simple specular reflection at a virtual height. Okay. So from now on, I'm just going to replace this refraction process by this simple reflection at a virtual height. Okay. Well, all I'm trying to do here, let me go back. So with this configuration, what we can do is that we can calculate the range. Let's say if you're standing right here with your source, you can calculate for any upward propagating radio wave, what is the range for that wave as a function of frequency, and incident angle at the bottom side of the ionosphere. So that's the result in the next page. So all I'm trying to show is that you can calculate the range as a function of this angle theta sub 0 and the normalized frequencies. And all of this is a function of this y sub m, which is the density gradient above the bottom side ionosphere. Since we're talking about a potentially large range where D is very large, if D is large, you need to take into account the curvature of the surface and therefore also the curvature of the ionosphere. So the equation on the top gives you the range formula for a flat surface, stratified ionosphere, and the bottom equation gives you the same quantity, but taking into account of the curvature of the system. So with these two equations, I can now produce a set of curves. So this now is the range D in the vertical axis as a function of angle theta 0 for various frequencies. So X here is the frequency parameter normalized to the critical frequency of the reflection layer, okay? And the panel on the top gives you the flat Earth case. The panel on the bottom gives you the spherical Earth case. So in both cases, you can see that these frequency curves has this U-shaped structure. So I just call them U curves. And in fact, this actually shows the calculation of the maximum useful frequency at the bottom of the U. So here are the U curves. So each U curve is a frequency, the normalized frequency, and the U minimum gives you the MUF for that range. And so the rays that are above theta 0 are what is now called the low angle ray, and the rays below the critical angle, the minimum angle U, is the high angle rays, okay? Okay, so since this is a well-studied problem, in fact, back in the 60s, people have already done ray tracing calculation in this scenario. So what's being shown here is a figure I have adopted from Croft 67 in JGR. So what he had done is a 2D ray tracing calculation for a fixed transmitter location. So he would launch rays at different angle of elevation. So then he would compute the ground range for that ray. So using the Bright-and-Tooth theorem before, and you can see that this is the black dots indicates the apex or the virtual reflection point. So as a function of angle, the locus of the virtual reflection point traces out a U or a V, if you will. So this locus of the virtual reflection point is called the reflectrix. So you can draw a set of reflectrix at different frequencies. So each one of these curve has one frequencies. And turns out these reflectrices correspond exactly to the U curves that we had before, because every one of these U curves is a frequency, okay? So in fact, if you look at the U curves, they have exactly the same structure as the reflectrices. So, and now it makes very convenient to interpret the data. So this picture here is a static picture with a fixed transmitter. But if you're sitting at the receiver location, which is fixed to the ground, instead of you moving, but the source is actually moving. If the source is moving, that means that the angle of elevation or the angle of incidence at the bottom side of the ionosphere has to be changing with time. So in that case, that situation is represented by this blue line. So this blue line said, as I cut across this frequency structure, I would be going from low frequency to high frequency to a highest frequency, and then come back out to a low frequency to a low frequency, which is exactly what we would observe in the dynamic spectrogram. So that in a nutshell is what we think is what's going on in terms of explaining the creation of the TP signature. So that's what that is. Okay. So we can summarize. So what we think now is the TP signature that we observe in the dynamic spectrogram is a propagation effect from perhaps distant lightning storms. And as I mentioned, you have to explain, the same mechanism has to explain why you have groupings of the TPs. So for the nested TPs, nesting of the TPs is probably coming from a line of thunderstorms. It's propagating, it's being viewed by your antenna beam. So your antenna beam is actually getting radio signal from lightning storm at different distances with a line of thunderstorm. So for the case of a series, the TP series could be a line of thunderstorm just moving across your antenna beam. With modeling, we could potentially use these TP signature to remotely sense or understand or model the height of the bottom side ionosphere, the density layer, and the critical frequencies. And lastly, as I mentioned before, depending on the geomagnetic conditions, you have different amount of ionospheric irregularities. So by looking at the degree of diffuseness of the discrete bursts, if you will, we might be able to start learning something about how irregular or how disturbed the ionosphere is. Okay, so I think that's the end. Thank you.
Thank you very much, Shing. I really appreciate it. And again, a virtual applause to you on behalf of all of the panelists and attendees. Well, we are coming up against another break here, and we went over a little bit, so I will let everyone go for the break. We will come back here at 4:50 p.m., which is the same as 2050 Universal Time, so that's in about 13 minutes, so go take a break. The webinar will be left open, so you can ask Shing questions if he's willing to stick around or have a conversation. Christina Collins and Phil Erickson are the moderators for the break in the next session. Thank you very much. I see Tim Duffy got in there too.
Yes.
Shing, also, there's some questions that have been dumped into the Google document, which is, you can find a link to that in the comments field the
Okay.
chat field. So you can, there's a couple of questions in there. I think there was a little confusion maybe about whether the TPs were occurring only during eclipses. From what I heard in the end of your talk, it seems like they may just be occurring. Lightning occurs all the time, of course. So is this a regular feature, I guess?
Correct. They have nothing to do with eclipse.
Gotcha. There is a comment from Steve Shurey, G3GPS. It would be interesting to know if the formation of the TPs correlate with sprites and blue jets from energetic lightning strikes above thunderstorms. I don't know if you
That's
have
an
any thoughts.
interesting question. But well, sprites and stuff occurs above the lightning storm, so we don't have those observations to correlate with, because you have to know, where the lightning storms are occurring, because we're making the observation remotely from over 1,000 kilometers away.
Right.
Phil, real quick, my audio okay?
Yes, you're sounding fine, Tim.
Good, good, thank you.
Yeah, Dr. Shing, I had a question on one of your earlier slides. You showed a what looked like a scanning algorithm for the receiver, and you said you had frequencies list and how often you let's see, a frequency step and a frequency range.
Right.
And so I was wondering how that would apply to an SDR, where you would be basically receiving all the frequencies at once, and you'd be mathematically integrating. You could do all the integrations at the same time.
That's right. That's right. So this is actually a different paradigm, and we wouldn't have to sweep the frequency. So that actually is an advantage for the SDR.
Okay, and I think we could do. I think you had, was it 3,000 different frequencies that you were integrating over? I think we could do all of those in parallel.
Yeah, that's right.
Yeah.
This week is 300 channels.
300 channels. Okay. So I think the FPGA could manage to do 300 integrations at the same time.
Yeah, yeah. Yeah, we're looking forward to working with you guys to see if we can come up with a good working system for both of us.
Yeah, because I've been talking to Larry Dodd on email. So.
Right. I think Larry's online too.
Oh, okay. Yeah.
He's
Hello,
one of the
Larry.
attendees.
And Dr. McDonald points out that one of the regular Radio Jove participants is also an excellent sprite observer in New Mexico. So there are already people who are working on connections, I know, between sprites and lightning. Perhaps that link can be made here too.
Yep, absolutely.
Thank you. Very good presentation.
Thank you.
Christina, are you online?
Yes, I am.
Okay, can you, I need about 5 minutes and then I will be back to help you. So I'm leaving you with the control.
Okay.
Hi, everyone. I'm back too. Thank you so much, Shing.
Okay.
Yeah. Did you get some good questions at the end? I'm sorry, I had to step away for a minute.
I think so. I'm just going through the chat thread now.
Good.
Are these questions also captured in the Google Doc, or do I have to answer in the chat?
They're captured in the Google Doc.
Okay, so
So
I
actually,
just, all right, so I'll just put my answer in the
if you just put your answer in the Google Doc, that should be fine. In fact, I think I know Laura Luke started putting most of the questions over, and then MD is going through the rest of the chat and making sure all the important questions are in the Google Doc.
Excellent.
From this session.
Nathaniel, did you see the comment about the YouTube stream is currently muted?
No, I did not see that.
I saw someone type it into the Google Doc document.
Now that's interesting. How? Okay. The YouTube stream is currently muted. Okay, I will go take a look at that. So it'll take me a couple minutes to figure that out. I'll let Christina, the conversation is in your capable hands.
Thank you. Although I just opened the YouTube stream and found that it was not muted. The person who said that may just have not found the mute button, but it's probably just as well if somebody else checks.
Yes, no, it's always good to double check that.
Yeah, I just checked it. It's playing here fine.
Okay, good. So we're okay then. Yeah. All right. So I'll stick around. Yeah, it's kind of tricky keeping all these technologies in line and working.
You know, I was thinking about it. It's funny because it's sort of forcing a return to the way people used to document these conferences. How you would have somebody who was taking down notes on all of the conversations that were occurring, and then you'd be able to go and look those up as references.
I think it's going to be really nice. I'm very happy with how the Google Doc is shaping up there.
Yeah.
I think that's going to be a very nice way of really capturing some of the really important parts of the workshop in a single document. So.
And the nuances of the thing that you put in the presentation that you needed to like add something else to that somebody pointed out, stuff like that.
Yeah, it points out where the missing gaps are in the presentation.
Yep.
So yeah, that's really good.
And you only need 3 computers and 5 monitors to run everything.
There you go.
That's what I have here. I have one on the YouTube channel. I have 2 monitors on another computer, one on the agenda and one on the Google Doc, and then 2 monitors on the presentation computer. So never be said you can't throw more hardware at something.
Yeah, it's all it's like we all have our own little command stations.
That's right. It's like more horsepower than NASA had, you know.
Yeah. Let's see. That's right, more horsepower than NASA had.
I think your phone has more horsepower than NASA had for Apollo 13.
That's probably true. Let me let's see. I need to go check on something. I will be back in like a couple minutes. So back over to the group.
Yeah, so I always get the chance in a live presentation to ask people how many Raspberry Pis they have at home. And the answers usually will astound you because it's usually in the range of 20 to 30 is the most that you get. So it'd be interesting to put this question up on the Google Doc and see how many answers we get there.
Go for it. Go for it. Make it a little poll. See what you get.
Little poll, yeah. I ought to do that. Let's see.
Well, you know, one thing that I've been thinking, especially in light of these last couple of talks where people have been like, hey, we've got our stations here and here and here and come collaborate with us. We should just make a map of everybody. That's something that I want to start working on, partly because I've started finally learning how to use Leaflet. Partly because of some discussions at the Tapper conference.
So we could make it automatic to put up a map with a dot where every login is.
Oh, that's an interesting approach.
I wonder if you could do it automatically or not, because I don't know if you would get the locations or not.
I see Jerry Krieger says he can help with the map. That would be neat. I can generate something if we just get some points. I wasn't even thinking of mapping the attendees, although that's a really good idea. We could probably just get estimates from call signs or IP addresses as a starting point.
Well, call signs, that's a good idea because you could get that right off of QRZ.
And there's a way to do it where you pay like $60 a year for the service. There's also a way to do it where you kind of hack it because their webpage, if you ask it for like 10 addresses for 10 call signs, it will give you 9 of them. So you can just query it twice. Anyway, yeah. So, but they do have a really nice little API for querying that sort of thing. And you know, if they want to make money with it, I guess whatever. But for like that map that I showed in our presentation for everybody in the festival of frequency measurement, that was just from finding their addresses from their call signs.
You just did it manually? You just did it manually and placed it on the map?
If you look up QRZ like call sign lookup or something like that, there is a pretty nice feature where you can copy in a list of call signs. It will give you a CSV of addresses and latitude, longitude.
Okay.
So you can pull data for it, and I haven't figured out a favorite method to do it. Like I haven't yet gotten something where I can easily query QRZ. But if you want to find like 50 addresses for 50 call signs, you can probably do it in about 15 minutes.
Okay.
So
I'm logged in on.
I see we've got a grid square offer.
Yeah, how about putting that into a Google Earth KML file?
I don't know enough about it, but sure. I mean,
I mean,
anything with a list of locations would be cool.
That's just a required field in your login.
All right,
Yeah,
everyone.
actually.
I for one use Google Earth for a lot of my experiment planting.
Well, I've been switching over to doing stuff with Leaflet because Google Earth is all bound up with Google Maps, and Google Maps no longer does free support, which means that everything broke. Like Reverse Beacon Network used to use Google Maps, and you could get wonderful illustrative charts of where your radio signals were going, and now you can't get that on there.
Yeah.
And Leaflet will do the same things for free. You just have to learn how to talk to it. So I'm in that process, and one of the things that I'm working on next is, we were talking about eclipses. I want to do a map of all of the eclipses coming up in the next few years, basically copying some that already exist on timeanddate.com. But then I want to start peppering in all of the stations from HamSCI participants, because at this point, we're probably talking about like 10 different citizen science networks. I think it'd be really helpful to be able to say, okay, where are all these people?
All right, that sounds great, but it's time for our next presentation.
Oh my gosh, already?
I know already, but I agree, and I saw the work that you were doing with the, I guess the OpenStreetMaps, and that was Leaflet that you were doing on the festival pages. Yeah, so it's looking good. So I agree with Google doing what it's doing. That's probably a good approach.
Well, once we get personal space weather stations, thousands of them, we want to see where they are.
Yeah, yeah. All right, so thank you very much, everyone. We are back for the formal session. This is the last session of the day. So oral session 4, citizen and professional space science results. So we're going to start off with David Smith, Whiskey 6 Echo Yankee from Utah State University. He's going to talk to us about using amateur radio to validate model-based properties of Earth's protective shield. So go ahead, David.
Awesome, thank you.
You're welcome.
Is my screen sharing available now?
It should be. You should be able to screen share. And we can see your screen and I can hear you.
Excellent, thank you very much. So good to be here today. It's been a lot of really good information, and hope it will continue with what I've got to present here. So yeah, I'm Dave Smith, Whiskey 6 Echo Yankee. My collaborator Jan Soika and I here at the Center for Atmospheric and Space Sciences have been doing some interesting things, in particular concerning polar cap absorption events. We've been looking at energetic proton transport, how that affects the D region, and ultimately HF absorption. So just to give a little practical application of why we've been looking at these things. This shows a polar projection of a Great Circle route, a polar route that an airliner could take from New York City to Hong Kong, for example. The red indicates where there is VHF usability. The yellow indicates HF requirement, and everywhere outside this white circle, SATCOM is available below 82 degrees north. So as the plane is traversing from New York to Hong Kong, at the beginning and at the end, there's a lot of HF coverage, but for a stretch here as it goes over the pole, it's either got to be HF or SATCOM, but once it crosses over the 82 degree north latitude, relies solely on HF communications. So during polar cap absorption events, that path may not be available due to ionospheric conditions. And as we note down here, it costs an airline many tens, if not $100,000 if they have to reroute due to communication concerns. As of about 2007, annually there's about 7,000 transpolar flights. So this is, it's an important consideration, being able to monitor, being able to predict space weather, its effect on communications. And this is one application. And so we'll be, that was kind of one of the motivations behind our study. This is what the SWPC, Space Weather Prediction Center, their D-region absorption predictions model. This is a picture of what they would show for absorption over the polar region. The scale on the bottom is the frequency in megahertz that is experiencing up to 10 dB absorption or more. And so we can see here right over the pole, 35 megahertz. And as it goes equatorward, the discrete bands here are lower and lower frequency. So this is just an indication of what a map would look like that DRAP produces during a proton event. This was during an event back in September of 2017. So that just kind of gives a picture of what's going on. We've seen this picture before, but just to review really quickly, the D region of the ionosphere is at an altitude of about 50 to 100 kilometers. Primarily, the D region absorbs HF radio waves from about 3 to 30 megahertz. And those of us who are active on HF, we experience that. Listening to AM radio during the daytime versus the nighttime, you're experiencing that. And the D region usually exists only during daylight, very driven by X-ray emissions from the sun, Lyman alpha, etc. But during polar cap absorption events, enhanced ionization from solar protons can occur throughout the day and night. And according to the literature, generally 1 to 20 MeVs, and that's a measure of energy, mega electron volts, 1 to 20 MeV protons are most responsible for PCA events. This little chart we put here, it's a log plot on the x-axis of the proton energy going from 1 up to about 100 MeV. And this shows the penetration depth or the optical depth of an energetic proton. The shaded region represents the bulk of the D region. And you can see that protons of about 10 to 20 MeVs penetrate down to the lower base of the D region. Higher energy protons usually go past it. So what we are most interested in is as we're looking at these proton trajectories, how they affect the ionosphere, we're primarily looking at these 1 to 20 MeV protons. So one question we ask, can these solar protons reach any location? And how do we study them? So let's look at that first. What we use as our tracing model is the Saigon-Yanko geomagnetic field model. The version in particular that we use is the 1996 version. It's a semi-empirical best fit model. It's based on a large number of satellite observations. And what we use it for specifically is field line tracing. We also used this as a paper or a presentation that's coming right after us. We used it to do some modeling of the open-closed boundary. And we also use it to provide the vector components of the geomagnetic field as we're moving protons through Earth's geomagnetic field. The internal field of the model, we use the IGRF, and the external field is the 1996 version of the Saigon-Yanko model. Here's an example. I mentioned previously the open-closed boundary. This is an example of, here we have Earth in the center. The black line, this would represent a closed magnetic field line. It has a foot point in the northern hemisphere and a foot point in the southern hemisphere. The two purple lines would represent what could be considered open field lines. They have a foot point, in this case in the northern hemisphere, and then the other foot point is out into the solar wind. And so it's on these open field lines that protons, being charged particles, they're able to, in essence, grab onto this field line, and then they're able to follow it down into the polar region. And so as we examined this, we were trying to determine what's the furthest latitude equatorward that a proton of a particular energy would be able to get down to the D region. Here's a nice colorful cartoon. The sun would be out here on the left of the screen. You can see all the different field lines emanating from the Earth, coming from the south up into the North Poles. Notice that some of the field lines are open and they connect out to the interplanetary magnetic field. As protons are propagating from the sun, they can, in essence, grab onto these and propagate down into Earth. Closed field lines, typically protons will be trapped, such as the radiation belts. Good. So then the question of, can they reach any location? There's a, oops, sorry, there we go. The proton energy cutoff latitude. That describes the lowest latitude to which a solar proton can penetrate. And that cutoff latitude is variable depending upon the proton energy. All things being equal, a proton with higher energy will be able to reach a lower latitude. It also depends on local time. It also depends on the geomagnetic storm conditions. And one of the interesting things that we've seen as we study our model results, there's also a universal time component. What we have here is a sample of an allowed trajectory. Now, I'm not going to go into a lot of detail, but we use what's called a reverse engineering process to calculate the trajectory. Rather than starting all out here and trying to find a proton that would have an allowed trajectory and make it to the Earth, you start with an oppositely charged proton, in this case, a negative proton, and we start it at a location in the D region, and then it propagates out. If the proton escapes, then that's considered an allowed trajectory. If the proton is trapped and just continues to propagate along the magnetic bottle in here, then that would be a trapped proton, which would mean it could not have originated outside of the geomagnetic field, so it would be considered a forbidden trajectory. So that's kind of how we determine these. Now, what we looked at is we tried to determine for each universal time, along each 15 degrees of longitude, we tried to determine where would be the cutoff for this latitude for various energy protons. So this particular graph here represents the cutoff latitude at 0500 Zulu under quiet geomagnetic conditions, and we're using geographic coordinates. We also plot these in geomagnetic coordinates, and we also plot them in invariant latitude coordinates, but we're using geographic coordinates here. So this line, it represents two important things. Number one, the equatorward extent of 1 MeV protons. So for example, on the 240 degree line of longitude at 0500 Zulu under quiet conditions, we modeled that a proton would be able to reach a geographic latitude of about 65 degrees, okay? But this also represents the foot points of all of the different magnetic field lines that support 1 MeV protons propagating along them and reaching the Earth. So this is for a 1 MeV proton. Notice it's a fairly elliptical shape. We also would have to consider that inside that circle would be a region of enhanced absorption, because within this region, you're having these protons, they're colliding with neutral constituents, they're ionizing, they're creating free electrons. And so within this region, we would experience enhanced absorption. Okay, here we have the cutoff latitude for 100 MeV protons. Notice, number one, it extends quite a bit equatorward in all directions, which would be expected. As we said at the beginning, higher energy protons are able to penetrate to lower latitudes. And so we again would understand that there would be this region of enhanced absorption in here. More absorption, more protons, more ionization taking place here. And as we progress farther outward, less. But again, it's within inside this oval where the enhanced absorption is taking place. But it's not really a discrete thing. What we're looking at is what would be called the upper cutoff latitude. Literature says, and we've seen it in some of our studies, that really even past that initial cutoff latitude, there still is a range of protons of a particular energy that are still going to be able to have allowed trajectories. And so there's going to be an area of the first forbidden trajectory. And then there's going to be some kind of gray area where there's a gradient where fewer and fewer protons are able to have allowed trajectories, until eventually you'll reach some point where a proton of a particular energy can no longer make it down to that latitude. So instead of having these discrete lines, and I should note, this is just illustration only, it's not drawn to any scale. It would be more like this, where there's going to be an enhanced region, and then as you move farther away from it, kind of a grayscale thing. Now, let me get back. Sorry. So a couple of movies here. On the right, this is DRAP model data, again, for this proton event from 2017. Notice as it's spinning around that you have this very symmetrical looking area that seems to be dependent really only on local time. The sun, and you'll notice on the chart on the left, the sun is following at the same time. So this is influenced by the sun here. This is our data. We found that the high energy 100 MeV proton stayed pretty much in a very static location. A little bit of variation, but pretty much just like this one here where we see the purple line, pretty much stayed in one area. In the center though, however, the 1 in particular and also 10 MeV energies had this variability that, in addition to the location of the sun, also just based on the universal time, which would perhaps be an indication of the configuration of the magnetic field. We had recently published a paper about model-based properties of the open-closed boundary, where we were able to show a UT-dependent variation, again, based on our model results. So it made sense to us that there could also be this UT variation in the cutoff latitude. And so here we have a plot. This is for 1 MeV proton, quiet condition, and we just selected 4 universal time configurations, 500, 1100, 17, and 23. And notice that at each of these, there's a different configuration. It's not, as the DRAP animation showed, it's not this really symmetrical shape. It varies a lot.
4 minutes.
Thank you. During severe conditions, as would be expected, these boundaries extend equatorward. And the kind of some important stuff about absorption, I'm just going to get to this equation right here. We know that absorption is proportional to n, which is the electron density, mu is the collision frequency, and 1 over the square of the frequency. So as we get lower frequencies, we'd expect to have a greater amount of absorption. So this is important because, number one, commercial and military aviators rely on up-to-the-minute information about what's happening in the polar regions as far as radio wave absorption, particularly for HF is concerned. Again, here's our path from JFK over to Hong Kong. And if we superimpose the 1 MeV boundaries over here for the various UTs, we can see that it may, depending on the UT that it's transiting through here, it may encounter the boundary sooner or later. It may leave the boundary sooner or later, depending upon the UT. And this would show for severe conditions. Here would be a flight for Tokyo from JFK. There are times where it would be within the boundary. There are times where it's outside of the boundary. And so being able to understand how this UT modulation takes place would be very helpful. So what I plotted here were several paths, not so much concerned about airlines transiting through these paths, but possible amateur radio paths where they would be inside or outside of this, because a really difficult thing in validating these results is you have a location, a fixed location, it's going to be at one spot, and as the Earth rotates around, it would be very difficult to isolate, is this a local time effect due to the sun? Is it a universal time effect? But if we were able to have many different data points, that could provide a signal for us to see, is there some modulation taking place in this open-closed boundary due to this universal time effect? And so I'll just skip through these, would be with severe conditions. And again, we can see that some paths take it right into the heart. Others, bypass it. So as conditions were changing, we would perhaps expect to see that some UTs, there would be an open propagation path. Other UTs, perhaps the same path wouldn't be open. And especially during, let me go back here, especially during enhanced conditions, we could see something happening. So what we're thinking would be a very useful application of some of these ham radio processes and experiments coming up over a period of weeks, months, even years, to be able to analyze many, many different data points near these polar region boundaries, to be able to see how, is a propagation path open certain times during the day, not just because of a diurnal, day nighttime effect, but just because of the configuration of the magnetic field. So again, we've been able to model this UT effect, and it's important for transiting polar regions, modeling D region characteristics, and also HF absorption. We think that WhisperNet, the personal space weather stations, have a lot of potential to being able to help to validate these results, which of course would lead to enhanced understanding and improvement of PCA events. So again, thank you very much for your attention. It's wonderful to be able to speak with everybody today, and I would be happy to field any questions if we have time. Thank you.
Thank you so much, David. I really appreciate it. Let's take, is there one question that someone would like to ask?
Nathaniel, this is from Tom Lockness. Sorry about your last name, Tom. He comments that maybe a receiver station close to the pole will be interesting, for example, in Svalbard. So I don't know if you have any comments, David, about that.
Yeah, in fact, I'll just zip back through here. That's LYR, that would be Svalbard. And the interesting thing about that one is if the path was opened or closed, that's going to give us some indication of the level of activity there. But, as I was listening to some of the talks earlier, and all of the different, like in Canada, all of those different receiving stations or ionosons and everything that were up here in the polar region, since those are spread over several meridians, several time zones, something like that could probably be very helpful. Plus any other stations or whatever around this zone, so that we could see in real time over many different longitudes, how does the how does the cutoff latitude change? That would be really helpful. And we really believe that somehow taking advantage of citizen scientists and amateur radio community could really help with that. So thanks for that question.
Yeah, and Tom is actually a geophysicist in Norway that often does field work in Svalbard, and he's been wanting to field a radio receiver up there for ham radio. So that's a potential collaborator for you there, David.
Excellent. Yeah, that'd be great.
Wonderful. All right. And if you need his email, I can put you in touch later. So next, I'd like to welcome Rachel Frizzell, W2RUF, and she's going to be talking about the the statistical study of the open-closed boundaries using ULF wave observations from Antarctica, automated geophysical observatories, McMurdo Station, and South Pole Station. Now, this is going to be coming from Antarctica, but it has some potential application for what we're doing, because as David just showed, we do have interest in that open-closed boundary as you go from the equatorward area up into the poleward area across the auroral zone, the boundary of open and closed magnetic field lines. Rachel's study is potentially interesting for the Personal Space Weather Station project because it shows a technique that you can use ground magnetometers for detecting that open-closed boundary. So this is a potential method that we could use for the ground magnetometers in the Personal Space Weather Station, instead of using it in Antarctica, using it up in, say, Canada and the higher Arctic in the PSWSs that we deploy up there. So take it away, Rachel.
Thank you very much, Nathaniel. Okay, working on feedback. And it would just take me a second to get, Nathaniel, can you mute yourself?
I'm muted.
Okay. Let me see, and I'm sharing the screen. Okay, can everyone see my presentation?
Yep.
Okay, fantastic. As Nathaniel said, I'm going to be talking about the statistical study of open-closed boundaries using ULF wave.
You are in presenter view. There you go.
Okay. All right, sorry for the technical difficulties. Can everyone hear me? Okay.
Yes, doing great.
I'm going to talk about the statistical study of the open-closed boundaries, referred to as OCBs, using ULF wave observations from Antarctica AGOS, McMurdo Station, and South Pole. So to follow from the last talk, once again, I'm just going to talk a couple minutes about the open-closed boundaries. And this is very similar to what you saw on the last talk, defining the geographic North Pole, geographic South Pole. As you can see on the image on the left-hand side, you can see the magnetic field line as they originate in the South Pole and end in the North Pole. Once again, that boundary between those open and closed field lines is what I'm interested in right now. And once again, the other image shows the solar winds, and it's labeled once again to open closed boundary. So basically, the knowledge of the location and dynamic of the magnetic field open closed boundary provides insight to space physics processes such as substorms, particle precipitation events, and the magnetospheric configuration. Prior studies have shown that determination of the OCB location can be made by examining the ULF wave power and data from a latitudinal chain of ground-based magnetometers extending from the rural zone deep into the polar cap. So the locations of these AGOs, here's a view from Antarctica. You can see AGO 5 is deep in the polar cap, and then AGO 5, 1, and 2 are along a similar line as with AGO 5, 4, and 3. Now, part of my work was finding spectrograms during the cardinal quiet time months, which I'll discuss shortly. But in order to determine the quiet time, there's a couple different measures. So one measure is DST, which is a measure basically of material injection. And then KP is a measure of the magnetic field lines. Very unscientific ways to say how much they wiggle. So what I did in order to find the quiet times of the cardinal dates, plus and minus 30 days, I would kick out any time of disturbance. So you can see there on the screen, the red circle shows some sort of disturbance. So I would not include that during the quiet time spectrograms. And once again, this is a 3-month. I'll be highlighting the time of 2017 and 2007. And like I said, the cardinal months with 30 days plus or minus, that's why I'm showing the DST of those 3 months. Okay, so in order to determine the open-closed signatures, a very simple way to imagine the open-closed boundaries, if you take a guitar string, you clamp at both ends and you pluck it, it vibrates. That's very similar to a closed field line. Now, if you snip it, then it becomes an open field line and you're not going to see those ULF waves. So looking at these two figures, on the upper left is March 2017, it's AGO 5, which is deep in the polar cap. In the polar cap, you will expect to see the open field lines. So once again, there's no signature of the waves. Now, if you look at AGO 3, that shows some sort of signature of the ULF waves. And I also, in my charts, as I mentioned before, you can see the x-axis is MLT time and the y is period in minutes. AGO 3, L is approximately 10, and for AGO 5, L is approximately 300. L is defined as basically the equator distance out from the Earth. And we also are beginning to see the blue dotted line in the lower right-hand figure shows the swooping U, and the swooping U is from the day-night variation. So continuing on about the swooping U pattern, once again, the two figures, the one in the upper left is AGO 3 from September 2017. And as I might not have mentioned, these are the spectrograms of the quiet times of plus or minus 30 days around the equinox or solstice. So 30 days before September 22nd, 30 days after. Now we can see more ULF variability along the swooping U patterns. So if we take a look at the AGO 3 of September 2017, the black lines are the standard deviation. So we notice right around the swooping U pattern, we see the standard deviation is about 0.4, and it's higher there than it is more at like hour 20. So like I said, we see the variability, the UF variability along the swooping U patterns. And the cause of that is thought to be from the polar cap variations. So the next slide, I'm going to talk about the greater ULF energy is observed at the lower magnetic latitude sites during equinox condition. So first, to explain this slide here, on the left-hand side demonstrates the equinox, and the right-hand side is the solstice. So beginning at the upper left-hand side, we have March, then below that is September. Those are two equinoxes. And then on the other side of the screen is the solstice of June, and followed by December. So with that said, we see the greater ULF energy is observed at the lower magnetic latitude sites during equinox conditions. So if we look at the equinox condition, that has higher variability than the solstice. We speculate this is associated with the enhanced magnetosphere-ionosphere coupling efficiencies associated with the dipole tilt, which is the angle between the geomagnetic dipole axis and the geocentric solar magnetosphere, the z-axis. Through the exact physical mechanism of this coupling is open, it is reasonable to assume that enhanced ULF energy on closed field lines would be associated with enhanced solar wind coupling. These next two slides are a bit of an eye chart, and they are similar in the fact that we have the solar minimum from 2017, and a solar minimum happens every 10 years. It will be the solar minimum of 2007 on the next slide. The way these are organized are by magnetic latitude. So we have the higher magnetic latitude at the top of the screen and the lower magnetic latitude at the bottom. So AGO 5 is at the highest magnetic latitude and AGO 2 is at the lowest. Up going from left to right, we have spring, hemisphere winter, fall, and southern hemisphere summer. And these are the quiet time ULF climatologies during the cardinal months. Now, there seems to be greater variability in the ULF data on the dusk midnight section. So let me take another step back and explain this a little more, because there's a lot going on these next two slides. So a couple things that are overlaid on this slide. I also use the Siganinko model. I use Siganinko 89, and I had a couple little issues with it. It worked well for AGO 5. So a X at the bottom of the screen means it was a open field line. And then once again, I apologize for the eye chart, a little harder to see at the bottom of the screen. A absence of an X would indicate a closed field line. And then I'm going to flip to the next slide, which is a solar minimum. And I went from 2006 to 2009. There was some missing data, so I had to pull data from a couple different years. And once again, we see greater ULF energy is observed at the lower magnetic latitude sites during the equinox condition due to the dipole tilt. So in conclusion, we were able to use spectrograms to determine the OCBs from the magnetometer data. Now, to reiterate from Nathaniel's introduction, one advantage why this is so, one reason this talk is important to HAMS and in particular the personal space station is by including magnetometers, if with the magnetometers in the personal space station, if they are deployed up through Canada, then we can have a better idea of those areas of the open-closed boundaries. So in terms of my work with looking at the ones in the Antarctica, bearing iridium transmission issues and AGO power system concerns, this technique shows great potential for locating the OCBs all year long with an array of relatively simple instruments. The greater ULF energy is observed at the lower magnetic latitude sites during equinox conditions, and we see more variability at the dusk-midnight section, likely due to ULFs as seen in Matt Cooper's paper 2019. That's my last slide, and there's probably some time for questions.
Thank you so much, Rachel. I really appreciate it. See, are there any questions for Rachel?
I wanted to ask how the feature set of the magnetometer that we've laid out compares to those that you're talking about using in testing. Are we covering the same features, or are there other things that we should be looking into?
Can you please repeat that question? My microphone, I could not hear that.
Okay, I'm sorry. I hope you can hear me. I wondered how the magnetometers that we're looking at making for the personal space weather station compare in features to the professional ones that you have perhaps used in the past for these measurements.
I don't have those specs on what the magnetometer capabilities would be for the personal space station.
I can jump in there for a minute to help out if you want. They'll be similar. Certainly the ones that Rachel has been using, they're actually the same magnetometers that Hyomin uses as part of the NJIT team. One of the main differences is they're going to be more sensitive in terms of nanotesla detection. So they'll be able to detect, fractions of a nanotesla instead of, say, have a 10 nanotesla resolution. Now, in terms of the type of work that Rachel's doing, I think that there are certain ULF waves, and that's what Rachel's looking at here, ultra low frequency waves. There are certain ULF waves that will be big enough that the personal space weather station magnetometer will be able to detect. As you get farther away from the auroral zone and the ULF waves get smaller, the personal space weather station will be less sensitive to it. But I do believe that even with a 10 nanotesla resolution, we will be able to detect a certain amount of ULF waves.
Well, just to add, what Rachel was showing was mainly high latitude phenomena. And we are talking about, I guess, mid or low latitude phenomena. So, I mean, it's not totally different regime, but basically what we're trying to measure is going to be a little bit different from what Rachel was reporting, because that's very high latitude phenomena. So in terms of wave activity, in terms of the amplitude of wave activity, the spatial extent will be different. So we are not trying to do the same thing that Rachel is trying to do. Although, I mean, conceptually, this is very similar.
Well, I think one of the things is when we've been framing the personal space weather station project, we've constantly been thinking in terms of design of the mid-latitude region. And that's because that's where most of the people in the United States live and most of the people involved in this project live. However, we are starting to see involvement from amateur radio operators up in Canada and up in the high Arctic in Canada and up in Alaska as well. And some of those people, I've had more than one person from Alaska or Canada come to me and say, we want to put up a personal space weather station too. We're interested in this. So for those people, this particular technique could potentially be useful.
Great point. Sorry, yeah.
Nathaniel, I've got one more quick question before I know we have to move on. Shuling Shi from the chat said, Rachel, can you clarify how you determine open and closed boundaries using ULF power spectra? So if you have like just a brief statement, just repeating what you had said at the beginning about how you define the boundaries. Rachel, can't hear you.
I would look at the spectrograms. So basically looking at one of those eye charts, when I saw the presence, because there's that gray region of like AGO 5 is always going to be open, but it's that gray area of like the AGO 2, 3 that it shifts. So I would look for the presence of the ULF wave, seeing that, for lack of a better word, that like red blur.
Right, so Rachel, when you see that red blur, yeah, Rachel, when you see that red blur, that means that it's a closed field line if you see the red blur?
Correct. A closed field line, you're going to see that red blur. That's going to be the ULF wave.
Right, and the reason for that is when you have a closed field line, it's of a particular length, so it can resonate with a certain frequency. Just like if you have a guitar string stretched across a guitar, you pluck it, it can resonate since it's got that tension, those nodes. So same thing here, a closed field line, it is able to support the resonance of frequencies, and that's when you see that ULF wave activity there.
And just like Nathaniel mentioned, if you have magnetometers at high latitude region with more densely spaced configuration, then you should be able to see this type of OCB temporal change of OCB in more detail. So that's our hope.
Great,
I don't see any more questions, but that was great.
Wonderful. Thank you so much. Thank you very much, Rachel, and thank you for everyone's questions. Okay, and what we're starting to see here is Christina, mentioned earlier over the break, we need to start putting together methods of analysis or science questions, techniques we can apply to the personal space weather station data to pull science out. And so we saw some of those techniques from the radio side earlier when we heard Phil Erickson's talk and Steve Serwin's talk, and now Rachel's talk starts to speak to what is one possible method we can use to analyze and utilize the magnetometer data, especially in this case, if the personal space weather stations are located in Canada, close to the auroral zone. Again, the auroral connection theme for the HamSCI workshop this year. Okay, so again, moving along with the auroral connection theme, we have another speaker, a scientist, Dr. James Wagan. He's going to talk about the temporal and spatial development of total electron content enhancements during substorms. And again, for total electron content, you can think of that as the total number of electrons in the ionosphere between the ground and a GPS satellite in space. So that will very much affect radio frequencies. And substorms is a very specific type of auroral activity or auroral enhancement. So James, take it away.
Can you hear me?
Yes, I can.
Super. I will try and share my screen. Okay, can you see my screen?
It's starting.
Can you see my presentation?
I can.
Yes.
Awesome.
Perfect, you are set to go.
Okay, so I don't have my camera on. There's a picture of me in the lower left corner, so you know what I look like. You don't want to have my camera on anyway. I'm sitting at home. Okay, so my talk is on TEC enhancements. Many of us in the space physics community say that TEC enhancements disrupt communications or GPS systems. This is important because we don't want to have these types of disruptions, but many of these disruptions occur in the higher latitudes, potentially due to particle precipitation into the ionosphere. And before I get started into this, I just want to define TEC as total electron content. It is the number of electrons per square area along a column of the atmosphere. In this case, 1 TEC unit is equal to 10 to the 16th electrons per square meter. And what I'm showing here in the lower right corner is one of these TEC enhancements that occurred within Alaska during a substorm. You can see this very large jump here of about 10 TEC units. And so this is a very large jump indeed. And what is not really well known at this time is where these enhancements occur within the auroral oval, as in what type of current system do these TEC enhancements occur. And so what I'm going to basically try and show you today is that the TEC enhancements I see are associated with region 1 current system or high latitude current system within the auroral oval. I was asked to define what a substorm is because this is when I'm seeing these TEC enhancements. The substorm is basically a release of energy in the magnetotail, dumping energy into the ionosphere. And so here we're looking at the Earth. Over on the left side of the top figure, towards the sun is off to the left. And when the plasma expands off the sun, it stretches the Earth's magnetic field, and those stretched magnetic field lines can reconnect, dump energy from the magnetic field into the particles. Those particles can rush towards the Earth, follow the magnetic field lines, and dump energy into the ionosphere, creating this bright aurora that you see down here in the lower right corner. And so the talk today is going to cover several different sources of data. One is that I'm using a number of auroral onsets determined from all-sky image data observed in Canada. I'm trying to show a mosaic of one of these all-sky cameras arrays up in Canada. You can see the aurora here going from Alaska all the way across Canada to eastern Canada. You see a substorm occurring within or a sudden brightening within the aurora occurring in central Canada. The red line here is indicating local midnight. Substorms typically occur just before local midnight. And the coordinate system here we're looking at is a geographic coordinate system. One of the other data sets I'll use is an ionospheric current pattern, a two-dimensional current pattern across North America, and I'll talk about that more in a minute. I'm also looking at TEC maps covering all the world. These are provided by the module data set, and I'll talk about those more in a minute. And then the final data set that I'm looking at is the DMSP, or Defense Meteorological Space Program spacecraft, particularly the precipitating electrons and ions and the magnetometer data. Defense Meteorological Space Program is important because typically in these orbits, we have one crossing from pre-midnight from pre-noon to pre-midnight, which is exactly where these substorms occur. And then nowadays, we actually have two within the same orbit. And so we can have one pass before a substorm and one pass just after a substorm and look at the change within the precipitation in the magnetic field. And so I just want to talk about these other data sets. One is this ionospheric current system. What I'm doing is I'm using magnetometer data from 11 different arrays across North America and Greenland up here. Typically, I have data from about 60 to 90 stations contributing to two-dimensional patterns of the ionospheric currents, which I'll show in a second, but I have the potential of getting data from 150 different magnetometers. The resolution of the currents that I'm going to be looking at, specifically the current amplitudes, which is a proxy for the theodolite currents or currents that come into or out of the ionosphere, is 1.5 degrees by 3.5 degrees. And the temporal resolution of the currents I produce is 10 seconds, but I can go as high as 1 second resolution. And so in this plot here, what I'm trying to show is a quick look picture of the different current patterns I can pull out. First, in the upper part of the plot, you can see the equivalent ionospheric currents. These are horizontal to the ionosphere. The dots here indicate where current has been determined. The direction and magnitude of the vector indicate the direction and magnitude of the current. Key is in the lower right. Each star here indicates a magnetometer that has data that was good for that particular day. And I've plotted here or indicated here the westward electrojet starting over here in eastern Canada, going across Canada and ending over here in Alaska. And the bar here marks again local magnetic midnight. Down below that is the current amplitudes. These are currents that are perpendicular to the ionosphere or proxy to the theodolite currents. You can see blue is downward current coming into the ionosphere if you're looking down on the Earth. Red is coming up out of the ionosphere if you're looking down on the Earth. And I've indicated two different current patterns, region 1, the blue, and region 2, the red. And this is very typical for the dawn side of the auroral region. And just quickly to plug my own data set here, I've been producing these currents now for over 10 years. I have about 10 years worth of data online. If you want to use it, please feel free to use it. If you're trying to determine open-closed field line boundaries, the upper or poleward version of the region 1 current system is a good way to indicate the open-closed field line boundary. And these currents can also provide context for what you're looking at in terms of scintillations or TECs. Now quickly to go through the TEC measurements. So to get TEC measurements, you use a GPS receiver on the ground and you use one of the GPS spacecraft. In this case, you're looking at a radio wave from the transmitter down to the ground, and you're looking at how that radio waves change in speed as they pass through the ionosphere. And if you know the distance to between your receiver and your transmitter, and if you know the frequency that's being transmitted, you can actually pull out the electron content along that column of atmosphere you're going through. And typically that's initially called a slant TEC. Then you can rotate that based on the angle between the transmitter and the receiver to get what's called a vertical TEC, so something vertical to the surface of the Earth. And down below here, I'm showing a map of those TECs. The red portion here indicates the day side. So 180 degrees away is the night side in North America here. You can see the auroral region is green band at high latitude. The blue part here is called the mid-latitude trough, where there's a depletion in the electrons in the ionosphere. And down below that in South America here, you can actually see what's called the electron fountain. The day side electrons can be pulled up high into the ionosphere. As those electrons move into the night side of the Earth, they actually kind of rain back down along the magnetic field lines, which you know is a dipole configuration, down onto the ionosphere, creating this kind of two-banded effect over here in the night side. So what I want to do first is go through one particular event, then I want to go through some statistics, and then we'll all be done. What I'm looking at here is a specific substorm event that occurred in October 14th, 2012. I'm looking at 4 different snapshots of the auroral mosaics across Canada. You can see the different all-sky image cameras here. Plotted on top of that is the current amplitudes, where red again is the upward currents, blue again is the downward currents, and then local midnight is indicated with the red bar here in the upper left corner. I've also plotted the DMSP F-17 spacecraft sitting here right within the aurora, just before the substorm occurrence. In the upper right corner, you can see the substorm has occurred in central Canada. F-17 has moved out into the Pacific. F-16, which is following along the same orbital path as F-17, is approaching that substorm onset. Down in the lower left corner, you can see now F-16 is sitting within the auroral onset, and the currents around that onset have actually intensified. In the lower right corner, you can now see that F-16 has moved along the same trajectory as F-17 and moved out into the Pacific Ocean. And so if I have these two spacecraft, I can actually begin to look at how the particle precipitation changes for that single event. Before I do that, what I'll look at here is quickly the TECs. They are not as informative as I had hoped, but we can quickly see some features here. Here we have a TEC map over North America with a geographic coordinate system. The star here indicates where the auroral onset occurred. You can see a lot of gaps here because we just don't have enough GPS receivers in Canada. In the next plot on the right over here, you see the TECs after the onset. You can see some enhancement in northern Alaska, some enhancement just around the region of the star, but it's not very convincing. And so what I do in the next plot is I look at the median of the TECs scattered around this auroral onset location to try and bring out this TEC enhancement. What we're looking at here in the bottom portion of this plot is the VTEC or median TEC values around the location of the auroral onset. I've defined the area here in the upper left portion of the plot. The dark black line in the center indicates when the onset occurs. And you can see the TECs are low before the onset and then jump up a few minutes after the onset. Above that, I'm plotting the BX component of the magnetic field, the magnetometer closest to the auroral onset. And I'm just plotting this here because this sharp drop in the BX component after the onset is a very good indicator that an auroral onset or substorm has occurred within the auroral region. So now let us quickly look at the particles. This is particle and magnetometer data from F17 that occurred before the substorm. From the left to right, we're crossing from the dawn side of the aurora down into the pre-midnight sector. The top, the dark black line is indicating the cross component magnetic field. I've indicated here the different current upward or downward for the different dark changes in the magnetometer. Over here on the left side, you can see what's associated with the dawn and upward and downward current. And then we can see over on the right side, the down, up configuration, which is associated with the pre-midnight current system. In the second, the bottom and bottom panels, we're looking at the electron precipitation and the ion precipitation. First, the electrons are plotted from low energy to high energy on the y-axis, and the ions are plotted from high energy to low energy. So it's kind of like a butterfly distribution. What's important here is that you see the electrons are what's associated with closed magnetic field line precipitation across the entire time span. And this dashed line, vertical line here on the far right side, indicates the closest approach of the spacecraft to the auroral onset location. And what I see is a very typical pattern for closed field line precipitation. The ions, unfortunately, are contaminated, and so we don't get a very clear picture of what's happening here, but you can see that there is some closed field line precipitation of the ions occurring. In the next plot, we're looking at DMSP F16. This occurred right after, about 8 minutes after F17 passed through the aurora. At the top, you can see almost the exact same arrangement of the currents. You have the up-down associated with the dawn side and the down-up-down configuration of the currents associated with the pre-midnight region. Again, in our electrons and ions, we see very similar precipitation occurring where the dark line indicates when the onset or the substorm onset has occurred, but then this dotted line here indicates the closest approach of the spacecraft to the auroral onset location. And what you see is a very bright red enhancement within the electrons. And I'll go back to the F17. You can see the dashed line is not much going on. And then we go back to DMSP F16. There's this sharp enhancement that occurs within the electrons. And maybe a little bit in the ions, but it's not entirely clear.
4 minutes.
So, thanks. So the those are nice to show the enhancement as a nice pretty picture, but what we really want is numbers. And so what I'm looking at here is the differential energy flux at each one of those dashed line locations for F17 on the left side and F16 on the right side. And what we see here is that there is a jump in the differential electron flux for these two different time spans on the order of a factor of 100. And so the electron fluxes have increased considerably during this single event. What I want to do now is look at the statistics. And by doing this, I'm going to combine many of those auroral onsets that I had and make a two-dimensional superposed epoch analysis. What I use is the epoch onset time as 0, 0 epoch time, and the epoch, the onset location is an epoch 0 location. And I take all the onsets between 22 and 23 MLT, and I rotate them or shift them up and down in latitude, and I'll line them up on top of each other to create one median picture of the currents and the TECs. So what I've done is combined about 40 events here to create a picture of what I see in the field line like currents. I've got a two-dimensional plane flattened to the north magnetic pole. I'm showing things oriented with midnight at the bottom, noon at the top, dawn side on the right, and dusk side on the left. And what I see is a very typical current pattern before the auroral onset, where blue is downward current, red is upward current. The little dot here indicates my epoch 0 location. Over on the dusk side, we see upward current and downward current from high latitude to low latitude. And the first two upper left plots show the currents before the onset, whereas the far upper right plot shows the currents at the auroral onset time. And you can see that the currents here are beginning to enhance. Then when we drop to the bottom left corner, we can see these currents really begin to enhance. They actually begin to expand poleward, eastward, and westward, just as we would see with the aurora. And as we move from 5 minutes after the onset all the way over to 20 minutes after the onset, the currents have really intensified. And so now these changes that I've done to the currents, these rotations left, right, up, and down to line up the currents is exactly what I've done to the TECs. And so the same thing has been done in both cases before the onset, during the onset, and after the onset. Now what I've done is I've plotted contours from the currents on top of the TECs, with the TECs of the colors in the background. And the contours here are the currents blue downward, mauve upward, and white indicates my epoch zero location. And you can actually see the auroral oval here within the TECs before the onset in these upper two left. And after the onset has occurred, you can see this sharp enhancement in the TECs. And so really the question for you in the audience is, do these sharp enhancements during substorms disrupt radio communications? Is this something that is observed by you in the HamSCI community? And I'd love to know. I've never seen any study indicating what this actually happens. If we look at the bottom though, here we can see this enhancement continues on for at least about another 20 minutes. You can see it expand both poleward, a little bit equatorward, and actually to the east and west. And what you can see also from all these plots here is that this enhancement is occurring within the region 1 current system. Region 1 current system is associated with the plasma sheet in the magnetotail, whereas the region 2 current system is associated with the inner magnetosphere. And so the picture I'm trying to flesh out here is I think I see TEC enhancements within the onset, within the first 10 minutes of the onset. I see these enhancements within the region 1 current system. They last about 40 minutes in length. And then when we looked at the single event, what we seem to see is that the electron precipitation enhances by a factor of 10 to 100. And this seems to be associated with monoenergetic or broadband electron precipitation, which I just didn't have time to discuss. So thank you very much for listening to my talk. I'll take any questions.
Thank you very much, James. I really appreciate that. Let's see. I think we have to move along here in terms of time, but I do want to say I think we had some good discussion in the chat window explaining some of the things you're looking at, and that trying to figure out what's going on from a radio propagation perspective along that poleward gradient during the substorms is definitely going to be something we will continue working on. I've started working on that with a student this semester, but things we just didn't get far enough along. But still in that vein, the next person who's going to present is Diego Sanchez, and Diego is an undergraduate student at Essex County College. Also does work in, he also works with us at MJIT, and so I've been working with him for about 2 years now, and he's also working with Gareth as well, and he's going to be looking at traveling atmospheric disturbances using reverse beacon network and WhisperNet data. And some of the techniques that you see in his presentation are also going to be comparing that data to TEC data. So you'll see the TEC data again. And some of those techniques, we're going to try and extend them to higher latitudes to see if we have the ability to help answer James's question as well. So go ahead, Diego.
Hello, can you hear me?
Yes, we can.
Cool. So I hope everyone's doing well. Let me share. Go. Can everyone see my screen?
Looks good, Diego. We can see and hear you.
Yes, we can.
Good. Yes, so I'll be giving my talk, parting the very long title, large-scale traveling ionospheric disturbances observed using HamSCI amateur radio, SuperDARN, GNSS-TEC, and ionosondes. So like Nathaniel said, this is a continuation of our work, and a lot of stuff I will be talking about here will have already been reinforced in past talks, so I'll go quickly. So traveling ionospheric disturbances, they are quasi-periodic variations of F-region electron densities. There are different types. We're primarily going to be looking at large-scale TIDs. So anything greater than 1,000 kilometers wavelength. And primary data sources that I've used for here, ham radio, reverse beacon network, and weak signal propagation reporting network. The majority of our plots, it tends to lean more towards WhisperNet data instead of RBN. But we also use SuperDarn, the GPS, TEC, NASA Omni data, and FOF2 data from Ionosans. All right, so this first image is just showing what happens to HF propagation when the ionosphere is perturbed. And you could see as the ionosphere becomes perturbed, the distance refraction decreases, and therefore the distance of the transmission increases. And to show, this is a simulation using of SuperDarn of how a TID would be imaged with SuperDarn. So we could see. Can everyone see my cursor?
Yes.
Okay. So we have image A here, the various beams of a SuperDarn array. In this case, the Fort Hayes East, and we're focusing on beam 7 right now. And in the background, you could see the simulated perturbed IRI ionosphere. In the middle image, you could actually see, now let's see if this works. No, apologize for that. This is supposed to actually be a movie, but yeah, this middle image here would have shown the change in the distance of the HF ray as the ionosphere changes over time. And you see that as the backscatter power, the power strength, the high backscatter power strength, as the ranges change, that's how the ionosphere is actually, the refraction through the ionosphere is changing over time. So this is how we would actually see the TID represented in a SuperDarn plot, as we could see in this next one here. So this is for the 3rd of November, a TID that was going through, and we have 3 very distinct wave structures, or peaks in this case, that, these plots, we can see the slant range, the backscatter power on the right-hand side, and UT time on the bottom. And this is an example of the TID plots that Nathaniel has been making. So first, down here, this is the actual plots using the ham radio data. We have the range of the spot, the distance from transmitter to receiver. On the right, the density, the spot density. So every, you can see color coded, the more yellowish is the higher spot density that there is at that given moment. And we were primarily looking for geomagnetically quiet and solar flare quiet days. So that's these 2 top areas up here using KP index and SIM-H and the GOES X arrays. Now, November 3rd, we have fairly quiet. So these wave structures that we see through the TID data over here, it's very probable to be a TID. Now, we took this and compared this to the GNSS TC data. So the shorter the range that we see in the ham radio data, would correlate to a more total electron content. Therefore, refraction would increase, and we would see that here. This is a movie. This first section from 1500 hours to 1800 hours, you'd see an initial ballooning of the area, and then back as the ionosphere becomes more charged, we'd start to see more reddish colors. So I'll play this real quick. Not as noticeable, but you see more bluish colors as it's coming out down here through the wave. And then back more red colors as it comes here towards 1800 hours. So we actually see the wave structures that we're seeing in the ham radio data is actually lining up very well with what we're seeing with the GNSS TC data. And one of the primary focuses that I've been doing recently was finding other days with potential TIDs in them. And this is one of the candidates that I found November 23rd, 2017, and comparing this with GNSS TC data. So we could see here these first waves. And I have the next slides taking specific spots at each of the peaks and just showing the change in the total electron content with the TC data on the right-hand side. So we start off, 530, and as we go, the distances are increasing in the ham radio data. Therefore, presume that the ionosphere, total electron content of the ionosphere is actually decreasing, and we could see that in a change here down as the areas become more blue. So it goes, more reddish blue, and then as we come up to another peak where the distances have decreased, it becomes red again in the TEC plot, indicating again increase in total electron content, and then back to blue. And we also found this for a second day that I found, January 26, 2017. You see these two major waves. And again, first indent, as we reach the peak, this one's way more dramatic. We see a much sharper decrease in the range of the spots. And we see a much greater change in total electron content. And as we expect, as the distances increase again, we would see a decrease in total electron content. And then again, as distances decrease, an increase again in TEC, total electron content. Now, another data set that we've been comparing to using ionosondes, tried to find or use ionosondes that were relatively close to larger concentrations of the radio spots. So you could see up here, the one for our European plots, the Julius Rue in Rügen, Germany, relatively close to the concentration. And in the US, using the Boulder ionosonde in Colorado. Now, I primarily using the FOF2 data from the ionosondes. So FOF2 is the highest frequency that the ionosphere reflects back to the ionosonde. And so we expect the higher the frequency that is bounced back from the ionosphere, the higher the electron density would be. And we could see that the two plots, our ham radio plots, line up very well with the ionosonde data. So the higher the FOF2 frequency would correlate to a higher electron density in the ionosphere, therefore a decrease, more refraction and a decrease in distances between transmitter receivers with the ham radio spots. And then again for September 27, we see this time over Julius Rue in Europe. Again, they line up very, very well, same times. As the FOF2 values go up, we see a decrease in the actual distance of the ham radio spots. So basically finding that ham radio, they're very coherent across the continental US and Europe, where the majority of our spots are. Very consistent with Super Darn, GNSS, the TC data, as well as the Boulder and Julius Rue Ionoson data. RBN and WhisperNet can serve as tools for monitoring LSTIDs day and night. However, the majority of our spots were from 14 megahertz and not 7, primarily using 14 and 7 megahertz spots. But 14 megahertz were kind of, we barely would get any data for nighttime. And yeah, from here, trying to find out what is the actual source of these detected LSTIDs. That's it. Any questions?
Thank you so much, Diego. Yes, are there any questions?
Oh boy.
You're doing great, Diego.
Thank you.
Let's see, Jonathan Rizzo, my other student here who's presenting tomorrow, he says, is it possible that sudden ionospheric disturbance data from monitoring phase and amplitude of VLF transmitters might be useful in detecting MSTIDs? I'm not sure. Phil, do you have anything?
VLF transmitters are normally often, I mean, these are these are lower frequencies. They have very, very long paths, usually reaching between one hemisphere and the other one along magnetic field lines. The signal for, the signal might be pretty weak for an MSTID embedded in the VLF signal, but I'm guessing here.
The other issue might be that VLF doesn't get very high into the ionosphere. It probably doesn't get up to the F2 region at all.
Well, actually, it will leak out of the higher latitude portions of the ionosphere and end up in the other hemisphere. The Stanford group in the 1960s worked on that. The difficulty is that it's kind of something like Carl said, it actually goes through the ionosphere pretty fast. I mean, it's of its long path, only a portion of it is in the ionosphere. So that would be my thinking on that one. By the way, Nathaniel, we have one more question that's actually in the Google Doc. This is from Dr. Liz McDonald, who says, "Great talk." By the way, there you go, Diego.
Thank you.
She says, "What would be your ideal number of observers to quantify the large-scale TIDs? Do you need more or stronger events? What would be on your wish list?"
I mean, from all the plots that I've made, it seemed it varied. Sometimes I would get very pronounced or very observable TIDs with like less than 60,000 spots. But then other times have a known TID with over, for example, 300,000 spots and not be as defined. So I'm not actually sure.
Yeah, it's a really good question, and it's one I know Nathaniel and Diego and I have. I specifically remember a long ride from Hamvention last year back to New Jersey, where we talked about, how many spots would you need and how many receivers would you need, and whether or not we could simulate it and stuff. It's a really good question. I think some of the interesting stuff that I think Diego's examples of Central Europe really show about the value of a density of spots, in my opinion, at least. But then, as Diego says, you get those odd cases where you don't need as many spots and you still can pull out the structure. So it's a really, interesting question to me, at least. It's a good question, a good thing to look at too.
I think something for the ham radio evangelists out there. We need, I think the thing over the US and over Europe, we have pretty good coverage. And actually, I have a copy of Diego's presentation here, so I'm gonna
just move back to, sorry.
Let's see. I was gonna say, go to your slide, just go to your slide 20.
20.
I'm gonna play with the annotation tools here. Actually, go to the next slide because it shows both the US and Europe. Okay, right. So like, you can see how there's so much more spots over on the east coast of the US than there is on the west. So certainly trying to get a little bit more spot density out here, I think would help. You can see how concentrated everything is over Europe. So one thing so we're thinking that this is where our instrument, if you were, is most sensitive. So I think trying to get more distributed receivers in other parts of the world to increase the observations, even down in Africa and in Russia and all of these other places, and then trying to get more ham radio operators out there participating in WhisperNet or CW contests or the PSK networks, trying to get this sort of coverage in more parts of the world would be a really big deal and would really help us. So Tim Duffy and Ward Silver, if you're out there listening, if we can do things to motivate more people to become ham radio operators and to set things up to increase the coverage of this on a more global nature, I think that would really help the case.
I will point out also that the South Africans have a particularly strong amateur radio society, and Nathaniel and I have been contacted before when they noticed the HamSCI collective, a year or two ago. And so there are places where there are already people seeing if they can sort of contribute to this. So we have footholds in various other places which don't have a lot of coverage right now. And as Nathaniel said, a good idea would be to try to expand those.
All right, thank you very much. Well, we are up to our last presentation. So once again, I want to thank Diego, who's done a great job with this. And I have to point out, I really want to point out that, it's very challenging for students to learn how to do this sort of work. I mean, it's challenging for me to do this sort of work, but certainly for people who are just learning what do all these terms mean? We're creating a glossary. How do you create these plots? You have to learn a programming language. There's so many layers to doing this sort of research and giving these kinds of presentations. So I really want to give a special recognition to all of the students at all levels who've participated, including Diego and Rachel and Magda and Aiden and Christina and anyone else I might have missed. Frankie Bonte, who's starting to participate. I think it's just very commendable that all of you are doing this, and keep it up, because I know it's not always easy, but you're doing a great job. So we are now going to hear from one of the big guns, as they were in the amateur radio community, Tim Duffy, K3LR, very, very well-known contester. He has a modest ham radio station out in Western Pennsylvania on the Pennsylvania Ohio border, and he is also now the CEO of a ham radio company many may be familiar with, DX Engineering, and he has won many ham radio contests, and by knowing things about the ionosphere, by having some contest strategy, by building teams of operators to staff his station. And so I asked him in this talk, I said, Tim, are there things that you have seen over the years in your contest operation that, maybe you don't understand, but, maybe the HamSCI community could help answer? And so that was the question I asked him when I asked him to put this talk together. So he came up with the title saying, let's push the exploration of the ionosphere to the next level. So with that, I would like to introduce Tim Duffy, K3LR.
Thanks very much, Nathaniel. It's great to be here, and thanks very much for your kind invitation. I'm here at the studios and transmitters of K3LR this evening, surrounded by 13 towers that we go from 1.8 to 30 megahertz here. And after that, it's a vast new world above that. But I really am excited about the talks that we saw today. And those talks certainly surround the SDR projects that are going on. And just to dovetail on a little bit of what Diego was doing, the real key to getting more of these skimmer sites that can be used to help feed some of these networks like the RBN and WhisperNet is cost and then availability to the internet. There are so many holes in Africa, in Asia, certainly South America. These are places that would really benefit the data that we're able to collect if only they were there and they had connectivity to the internet. But I also want to focus a little bit on some things that I didn't hear talked about today, and that is some data that's available that might be able to be used by the HamSCI committee or group, maybe to find additional things about the ionosphere. And what these are logs from from the largest DX contest on the planet. And I'm talking about the CQ Worldwide Phone and CW contest. And I want to give you some statistics just from last fall. So this was in October of 2019. This is the CQ Worldwide Phone Contest. There were 7,700 logs of QSOs that were submitted to the CQ committee for checking. In those logs contained contacts made by 46,000 different stations from 215 countries. And those 46,000 stations made 3.1 million contacts in that weekend. Conversely, the CW weekend, which enjoyed better conditions, better solar weather, there were 7,800 logs there. 33,000 stations participated from 198 countries, making 4.5 million contacts. And the great thing about these logs is there are 14 years worth of public data available right from the CQWW.com website. And so if there were data mining programs that could go in, and obviously we know what the solar weather was during those two operating events, and we know what it was actually for all 14 years, I think that that's another level of data that could be used by HamSCI to figure out more things in the ionosphere. It's right there. As part of WWROF, we have been funding drives that have been used to actually record the contest on 1 terabyte drives at 10 different sites around the world. So in the adjudication of these contest logs, we can actually go to the actual contact that was claimed to have happened on the air from these 10 different locations. And we have several years worth of data like that for both the CW and phone contest. Again, that might be very valuable to HamSCI as we take a look at things within the ionosphere. That integration real time with solar weather that comes out of NOAA and other places, really, if it was combined real time with what's going on the WHISPER and the PSK reporter and the RBN and even the NCDXF beacon network, I think that that would be a very interesting integration to actually leverage multiple sources together in real time to try and give people, whether they're in education, whether it's commercial, or whether it's amateur radio, a better picture of how to utilize the frequency spectrum that amateur radio operators have, that commercial operators have, and really integrating those things, I think would be fascinating. Another fascinating thing here at K3LR, we have several arrays of stacked antennas that allows us to vary the vertical takeoff angle, depending upon what combination we feed those antennas at any given time. And for instance, on the 14 megahertz band on 20 meters, we have 4 Yagis that are in a stack, and they start at 230 feet and go down to 50 feet. Well, there are 10 different combinations that I have given the operators here the ability to use, which all develop 10 different takeoff angles. And of course, those takeoff angles vary with the terrain that is presented in front of the azimuth of those arrays. But having even something as simple as a Raspberry Pi programmed to actually sit there and run against the RBN in real time and do the switching to determine what is the best combination of these antennas at any given time, I think would also open our eyes to some of the things that are going on in the ionosphere. The other thing that I think, when Nathaniel posed that question to me, I thought I would love to have a predictor. And what would be the predictor? Well, it would basically take a look at the propagation that is going on up to 2 or 3 days before a particular contest event. And of course, this could be used for commercial applications and educational applications as well. And what I mean by that is actually taking and churning through the RBN data and getting a knowledge of a trend, or using the Whisper network to get trends on what times various bands open to various areas of the world. In DX contests, it's very valuable to have QSOs with Europe, and knowing how the European opening may have occurred in days leading up to it can be very, very valuable to amateur radio contests. But you can see by the sheer number of QSOs that goes on. I mean, when I think about the whole personal space weather station project, and thinking about that there are some 300,000 active HF stations worldwide. Now, many of those are small stations. They might have a vertical antenna or a wire antenna. And from a transmitter standpoint, they might only be 100 watts. But that's a lot of stations. And even in the US, there are well over 100,000 US HF stations that all could be leveraged by the HamSCI project. And some amount of them will be. And I really think that there'll be a lot of momentum as you start to roll out the personal space weather stations. I think that is just an absolutely fascinating project. And amateur radio operators by nature want to help and want to contribute. And what better way? I mean, you can get on the air and have a lot of fun when you're transmitting and receiving, but there's certainly a lot of dead time. And I've had discussions with Nathaniel and saying, the antennas here at K3LR could really be used for research. We've got a big internet pipe here. For about 4 months out of the year, we are contributing to the RBN with a full suite of Perseus SDR receivers. However, I can't wait to upgrade those to the Tangerine. I'm very ready to do that. And we'll actually dedicate one Tangerine to each one of the HF contest bands. And so I'm very hopeful as soon as those are ready to do that and make it a real cornerstone for the HamSCI contribution to the great hobby of amateur radio. So in closing, I want to thank all of you for your contributions to science, your helpful interest in amateur radio, your professionalism, and I look forward to tomorrow to hearing more fascinating talks. I mean, I have only been away from the computer for a few minutes today, and it's just been nonstop. It is definitely like drinking from a fire hose, though, because some of the, and I'm going to go back and take a look at the recorded sessions, just because there's so much value here. And I promoted this conference on the CQ contest reflector this morning so easy because you could click on the YouTube link. And I got a lot of good reaction back from that. And that went to over 4,000 people around the world. So I'm sure people come and go. I'm sure some of them will take a look at the recordings. And wow, you know, you almost say, why do we need to get together in person when you can do this? This has been just phenomenally successful. So Nathaniel, congratulations to you and your team and all the presenters. And if there are any questions, I'm available here, and that's it for tonight.
Thank you so much, Tim. I really appreciate that. And I see virtual clapping in the comments there. And first thing I want to say is I think your suggestions are really fantastic. Phil Erickson was pointing out that he really liked your idea of you know, potentially steering in real time your station based on incoming data. So these are things these are ideas that we'll have to you know, work on over the next few years. Okay, so with that, yeah, why don't we open up the floor to people who'd like to ask Tim questions? And we aren't as pressed for time now too, so go ahead and ask some questions.
Tim, this is Phil Erickson. I wondered if you could make a little extra comment. You know, I know that super contest stations like you know, it's quite a friendly competition and you all work together quite a bit. And so, for example, you and W3LPL and other people who operate a station at that level of capability, it sounds to me like from your comments, it wouldn't be that much of a stretch to get people to sort of buy into the kind of things that you've already been talking about doing in terms of kind of using the station when it's not in active contest mode as a directed remote receiver. And I wonder, knowing that community intimately well, what thoughts you have about that.
Phil, I think that it would be an excellent opportunity to share. You know, I've been to Arecibo several times, and you see that the scientists come and go all remotely, and you know, sign up for time with the various antenna to do research. And you know, this is no Arecibo here, but we've got some tremendously large antenna systems, and of course, Frank W3LPL has also got a lot of you know, just superior antennas that could be used for research as well. And in fact, Phil, after every competition, we actually, between Frank's team and the K3LR team, we actually trade logs very soon after the contest is over to actually dive deep down in the weeds and see just how propagation and various nuances of operators plays into how the contest unfolded and why things happened the way they did. You know, why did W3LPL have a better opportunity to work European stations on 15 meters, for instance, in this past contest? And it all ties back to the ionosphere and the solar weather conditions. So, but you know, there's so much dead time, Phil, that you could really, you know, spin this thing around and really do some valuable research.
Yeah, thanks for the comment. And before I let other people talk, the other thing I know that you have developed is an intuition. You know, you wouldn't be this successful unless you had a feel for what things work during what time. And I think there are frankly clues in even just the tribal wisdom and the conventional feel that you have based on sitting in that chair about what works when, that we could translate into hints, kind of, you know, okay, there may be something here. We hadn't thought about looking in that space. Maybe we should go look there. So even collecting that wisdom and getting into the collective here, I think would also be a really valuable thing.
It really would be, Phil. If I take a look at the 3 best QSOs that have ever been done from here, and this station has existed for 33 years. We've been in these multi-mega category contests for 27 years. The #1 QSO just happened here in January on the 160 meter band, where we worked Mongolia. And of course, it was a big station on the other end, but that's a very, very hard contact to make. And I believe that opening lasted less than 5 minutes. Another one of my favorite contacts was long path on 10 meters, So this was done at 150 degrees azimuth. So you're going over the south tip of Africa on the way to Malaysia. And it wasn't during the sunspot peak. And in fact, Carl and I corresponded about that. And he had some very good insights about that. And then the other one, which was a difficult contact because it was on what we call the bent path, where you go into the South Pacific, and it, we worked China on 75 meters. And that's a very, very hard path. But if these things that have happened, this intuition that you talk about, because once it happens, it's in my head and it's in the operator's head, but that's all the farther it goes. And we'd really love to share that.
I think it's a really great thing to share too, because it's really nice to go from that stage of intuition to that stage of, okay, we're actually testing this in a scientific manner, getting it written down and putting it into the literature. And that is a big step, trying to go from that hypothesis or that hunch to actually getting it shown in the literature. And I think this is a really good place where we can make that happen.
In the comments, I will point out that Liz McDonald points out, citizen scientists is where the scientist listens to the wisdom already out there in the community. And that's just what we've said.
Yeah. And I think it's another really nice thing to note is that along those lines, scientists, we are so used to looking at things a certain way. So we have some sort of implicit filter on. So being able to hear the experiences of the experienced people who use, the ham radio operators who use the propagation on a regular basis, they have a different perspective, and it can really open up new ideas.
Terry W0ASP with a question.
Go ahead, Terry.
Yeah, I'd like to ask Tim, what other geophysical data do you use to correlate your propagation data?
So I'm very fortunate that on the team we have a great engineer. It's N2NC, John Galome, who has really made it his passion to research what is going on with solar weather before, during, and after the contest. And he looks at a lot of different things to get his intuition around what's going to happen. And a lot of it is out of NOAA. And it's also even as simple as the WWV numbers. But he has a list of about 4 different websites that he watches during the weekend, and he helps steer us. He is so valuable on so many fronts. But so we sort of have an onboard scientist as part of the team that is really fascinated with propagation, and he uses the information on the web to really give us some insight into things we should look at.
Okay, thank you. Thank you for your answer, and thank you for providing high quality products to the amateur radio community.
Thank you.
Are there any more questions for Tim?
Yeah, I had one.
Go ahead, Aiden.
Yeah, so one thing I was wondering, do you have a sense of what kind of data presentations or what kind of either visualizations or results or things might be most useful? Because I imagine the science community has their preferred way of looking at things. But if we're talking about giving hams a way to look at what's happening at their station and tune their results, short of putting on some magic goggles where you can look up and see the ionosphere in real time, what kind of presentation would be most useful to you to show?
That are not, and then really strip it down into the real time. Tell us about absorption pass, and that's a very risky test. The polar pass gets shut down, and therefore you don't hear anybody from Finland, from Norway, from Sweden. And as you go lower in frequency, it becomes even more. Thank you very much for your question. And I really think it's real time that focus in on the amateur radio meters and 20 meters and 10 meters, etc.
To talk with I had lunch with Tamitha. I think it was at AGU this past year, developing some of these real-time graphs could be really important. So we had her on, be working with her and with you over the next couple years, we could develop some of those sorts of things. So I was talking with Tamitha, maybe we have other more of these operations be the theme of next layers look like, especially as we try to develop the personal space weather. Yeah.
Nathaniel, I'm on now. Be patient. But since you brought me up, I guess, did I hear you correctly? Your station goes up to 1.8. Are you talking gigahertz?
No, it goes down to 1.8 megahertz.
Okay, what in the world? I was thinking, good night, what kind of antennas are you using? Okay,
Well, it's a pretty good 1.8 megahertz large.
Okay, got it. One of the things I was curious about is obviously, as Nathaniel had alluded to, I'm very interested in the whole concept of, you try to get up the nowcasting, because I think the whole community, what the capabilities are. You always have to kind of have the torch and clear the path and march forward before people can actually see. And then they go, oh, I get it now. But you have to put all the pieces and actually have a working, model and a demonstration in order for that. So yes, I'm very with you on this, on the whole nowcast. One of the things I'm curious about, though, and because I talk, all of operators talk to people all over the world, but as I'm trying, I also have people that are all over the world, and just like localized as anyone who works in the, what I would love to see and ping you about a sister station somewhere else in the world. Could there ever be anything like that where you actually partnering with people in Europe or another moderately similar, so that with similar setup, so that when you do all your ionospheric sounding, obviously the world rotates and the world turned, a space weather event or something rotating, let's say to the night side, and your local time is totally different kind of space weather, but the space weather fascinating is still happening on the day side, let's say. So how do you, is it ever conceivable in, I don't know, the not too distant future to consider trying to set up stations that are global monitors, very similar to the way we have, for instance, solar telescopes that are, global, that as one rotates away, the next one takes over, and they're kind of intercalibrated, and you understand my point, hopefully.
Yes, and I think it's very possible because there are large amateur radio stations in many countries, the size that K3LR is or W3LPL, there are several scattered around the world, and with the help of the internet, all of that data could be accumulated in real time, and then it's up to the scientific community, led by HamSCI, to actually write software that can process that in real time. And your vision is spot on. And so that could be a great predictor, because if it's, going on the other side of the world, eventually it's going to get here. And so I'd love to know, that gets me very excited.
Tim, on a related note, this is Bill Engelke, AB4EJ. I'm going to be doing some of the software, some of the visualization software they're talking about. I'd like to get with you offline sometime and talk through some ideas on some of that stuff. We have some ideas already, but to get more feedback from practitioners is always enormously helpful.
Yeah, I think that's very important. The personal space weather station, part of it is for the science, and part of it is to make sure that we are helping the amateur radio community too. So we really want to get feedback from people who are really, really active amateur radio operators telling us what's going to work for them and what won't.
Nathaniel, I thought you had a question from our friend Angel down in Puerto Rico.
Oh yeah, thanks. Yeah, so Angel down in Puerto Rico at Arecibo, he was asking you, Tim, if you wouldn't mind sharing those websites that you use to look at the at space weather for the contests.
Yes, so I will send those, so you can get them up on the Google Drive area, and so we'll put all that together and make it available to everybody.
Thank you very much. And Angel says hello. WP3R.
Yes. Hello, Angel.
Well, I think we are coming to a good spot to close for the day. So I want to thank all of our presenters and all of our attendees and all of our panelists and everyone who's really come together at the last minute to really make this what I think is a smashing success. And I think, you know, not only this has been a very good workshop for a number of reasons. One, because I think it was just a fantastic space weather, space science, and amateur radio workshop. And two, I think we're really doing something, you know, we're in a bit of a leadership capacity here, leading in a world where things are not looking so great right now. So it's really nice to be in a position where we're able to keep going with our lives and we're able to do something very positive, even in the midst of difficulty. And really, this would not have been possible without all of you. And I'd like to especially recognize my science and program committee. I know that I'm often the voice of the organization for all of this, but I've been working with Phil Erickson and Liz McDonald and her program project manager, rather, Laura Brandt, and Bill Lyles, and a few other people, Catherine Mitchell, you know, to really pull together the ideas to really make sure that this workshop is a good workshop and it flows smoothly. And so I could not have done it without them and without many other people here at the University of Scranton, just many, many people. So with that, I'm going to close the workshop for today. We will reconvene using the same webinar link tomorrow. The YouTube link may change, but I will post that tomorrow when I have that new YouTube link. And so we'll meet again. I'll open the session up around 9:30 a.m. tomorrow. I'll give another brief review of what amateur radio is and how we're connecting it to the Aurora. And then tomorrow is really our Auroral Connection Day, especially in the morning, where we're going to be hearing from Dr. Liz McDonald and Dr. Jim LaBelle and Dave Halliday, all talking about how amateur radio and the Aurora are connected together and auroral science and radio science are connected together. And then in the afternoon, we'll have the e-poster session. Again, we have part focused on the Aurora and then also a number of great HamSCI posters as well. So with that, I will close out the session and I wish everyone 7-3. I'm looking forward to seeing all of you tomorrow. So thank you so much, everyone. 7-3.
Thank you. 7-3.
Okay.
We'll talk to you then.
Talk to you then.
Great job, Nathaniel.
Thank you so much. Have a great night, everybody.
Yeah, thank you, Nathaniel. Have a good night.
Thank you.
Hear you tomorrow.
Thanks. And yeah, panelists, I'm going to put the webinar back in practice mode for a minute. So if you can just sign back in about 5 minutes, 2 to 5 minutes or so, we'll just have a quick debrief off recording. So 7-3, everyone.
See you in a minute. Thanks.
Thanks.